Tired of memorizing endless LeetCode solutions and feeling stuck in interviews? Well, you're not alone. Whether your goal is to get hired at Google, Amazon, Microsoft, Meta, Netflix, or maybe you just want to get hired by a great company, big or small, then this crash course is tailor-made to help you get there. But before we start, I need to tell you that for the first time, we've opened up our exclusive Discord community to the public. Join over 500,000 students learning together, asking questions, and staying motivated. Click the link in the description down below to get your free access. Now back to the course. We're going to break down string and array problems. These are the sorts of questions that get asked in almost every coding interview. From easy to difficult examples, you're going to develop the problem-solving skills to answer them with confidence. Guiding you is Andre Nigoy, ZTM's lead instructor and founder, and Yihua Zhang, a senior developer who has worked for some of the world's biggest tech companies and has received job offers from FAANG giants like Google and Amazon. And if you want to go beyond string and array questions, then check out their full FAANG interview bootcamp course, where you'll learn about things like hash maps, queues, stacks, and so much more. One last thing, if you enjoyed this crash course, please help me show Yihua and Andre some love by dropping this video a like and leaving a comment with your questions, thoughts, or feedback down below. That's it from me. Let me hand it over to Yihua. Enjoy.
Hello everyone, and welcome to our first interview question. This question is going to introduce our section on arrays, and this is just an easy array question. But this is a great question because it really helps us understand how arrays can show up inside of our interviews, as well as it gives us a good chance to walk through the process of how to tackle and answer these questions. This is also the exact interview question that Google has posted on their YouTube channel to demonstrate how they expect candidates to interview for their software engineering positions. Before we begin, I want to walk through how these questions are set up. What I'm going to do is I'm going to walk through the question and help you understand what the question is asking you to accomplish, and then we're going to walk through the different steps that I have laid out that best help you actually come up with the correct answer, but also interview in the best way during your technical interviews. So first, let's understand what the question is asking us. The question reads, given an array of integers, return the indices of the two numbers that add up to a given target. What this means is that we are going to receive two different arguments. The first is that we are going to receive an array of any number of different integers. Integers in this case mean that they're whole numbers. They are not decimal-based numbers. The next thing that we're going to receive as our second argument is a target, which is also an integer. We need to figure out what two numbers in the array, if they exist in the array, can add together to give us this target value. In this particular case, when we look inside the array, we see that the values 9 and 2 add together to give us the target value of 11. As per the question, we want to return the indices of these two numbers. And as we know with arrays, indices are going to be the values that represent the index of every value. These indices start from 0 for the very first value, and they increment by 1 for every subsequent value. What this means is that if the answer is 9 and 2, then what are the two indices we want to return? They're going to be the index numbers right underneath them, 3 and 4. So this means that the correct answer for this question is an array containing 3 and 4. So now that we understand what this question is asking us, how do we solve this question? Well, before you even start solving the question, you have to do this first step. And this is a very crucial step that your interviewer is expecting you to do, which is to verify the constraints. Now, what are constraints? Constraints are ways where you can understand the question better so that you know what kind of edge cases you need to consider, as well as all of the different variables that might impact how you solve the question. And this usually comes in the form of a dialogue, which means that you want to ask your interviewer certain questions in order for you to answer and figure out what these constraints are. So let's walk through some great questions for this exact question. The first question that we want to ask is, are all of the numbers positive, or can there be negatives? This is a great question to ask when you're working with integers, because depending on whether or not the integers are positive or negative, this changes the approach and the solution that we come up with. In this particular case, though, our interviewer may say to us that all of the numbers are positive. Don't worry about negatives. So this means that the array we receive, we guaranteed that everything is positive. We will never receive an array that contains any negative integers at all. The next question we might ask is, are there duplicate numbers in the array? Meaning, are all of the numbers inside the array we receive unique, or can there be duplicates? In this particular case, we'll say no, there are no duplicates. So this means that when we receive the array, we don't need to account for what happens if the numbers are duplicated. We will never receive a possible array where any of the numbers occur more than once. Another good question that we want to ask is, will there always be a solution available? Meaning, given the array and the target, will we always be able to find two numbers in the array that will add up to this target? Here, the most common answer to this question is no. There may not always be a solution. So the code solution that we come up with needs to be able to figure out whether or not there actually exist two numbers in that array that add up to the target. So this means that we can receive a target of 25. But we might receive an array where no two values add up to 25. But this is not the only possible edge case that this can occur. We might also receive an empty array. In an empty array, there are clearly no values that will add up to 25. Similarly, because we're looking for a pair as per the question, if we receive an array which only has one value, this can also never produce a correct answer for this question. So this is a great question to ask in any question case when we're doing our interviews. A good follow-up to this will be, what do we return if there is no solution? Do we want us to return -1? Do you want us to return an empty array? What do you want us to return? Here, they'll say just return null in this particular case. It's really up to your interviewer to determine what they want you to return if there is no solution. But this just demonstrates that you're thinking about all these edge cases and you're giving that onus on the actual person that's giving you the task to figure out what the constraints are in this particular case. So another question we can ask is, can there be multiple pairs that add up to the target value? Here we'll say, no, only one pair of numbers will add up to the target given. What this means is that if we're given the target of 11, we'll expect that only two numbers in the array will add up to this value. We'll never receive an array where there's multiple pairs that add up to that target. So in the first one, we see that only 9 and 2 add up to 11, whereas in that second array, we see that there's 9 and 2, but there's also 7 and 4. So we don't need to worry about our solution coming up with a case where we need to consider multiple potential solutions. So now that we understand all of these different constraints that we verified through these questions, we want to be able to combine them all together into different test cases. Test cases are just different combinations of the inputs that we could receive. So different combinations of the array and the target that we could get that will best capture all of these different edge cases that our solution wants to account for. This is a process that you can work with your interviewer on, where you ask them, is it okay if we come up with some test cases together that best capture these different questions that you've helped me answer for our constraints? This is what we're going to do together in the next video, but I want you to think about some of these different test cases that could occur from the different constraints that we've just answered. So once you've done that, join me in the next video and let's write out some of these test cases together. Hello everyone and welcome back. In this video, we are going to come up with some of the test cases that will capture all of the different constraints that we verified when we asked these different questions in the last video. So here, let's switch over to the tablet where we're going to walk through and write out these different test cases together. Remember, there's a lot of different constraints that we need to make sure we capture in multiple different test cases. But the first test case that we begin with is known as the best case test case. At least that's what I'm going to call it. And this is a test case that we know for sure what the answer will be for the given inputs that we receive. So here, we're going to just reuse that array that we first saw. So we're going to receive 1, 3, 7, 9, and 2 as the array, and the target that we receive is going to be 11. In this particular case, the answer that we return will be 3 and 4, which represent the indexes of these two numbers that we know are the correct answer that when added give us the target of 11. Now, we need to think about those other different test cases, or edge cases where we might receive an array and a target where there is no possible solution. So let's do that now. The first thing that we want to think of is let's repeat this same array, 1, 3, 7, 9, and 2, except our target is 25. We know that there's no possible answer inside of this array where there's two numbers that added together give us the target. So what this means is that we want to return null as per our questions and what our interviewer told us to return if no possible solution exists. Another different edge case that also captures this null case is going to be what happens if we receive an empty array as well as any target value. We can even say a target of 1. In this particular case, we'll also return null because there aren't even two values to add together to find the target for. Similarly, we want to do the same thing where we receive some array with one value. Let's say it's 5, and we also receive a target. Let's even be more explicit. Let's say the target is also 5. In this case, the answer should still be null because we need two numbers that when added together will give us that target. Even though one of those numbers, 5, plus nothing could give us the target, this is not what the question is asking us. So in this particular case, we also return null. Now for our very last test case that we come up with, maybe we just figure out one where it's low-hanging fruit and a really obvious answer, where there's only two numbers inside of the array we receive, and the target is going to be the sum of those two values. So 1 and 6 added together gives us the 7. In this case, we'll return 0 and 1 as the answer. So this is enough for our edge cases to help us actually start coming up with the solution. So this will bring us to the next step, which is step 3, figure out a solution without code. This is a very crucial step that we have to make because what we're doing here is we are thinking about coming up with a working solution before we get bogged down by any technical details. So I want you to not even think about the code implementation. I just want you to think of a working, logical solution for how you might solve this question if you were just asked this question out of the blue. So if there's no code involved, you don't want to think about for loops, while loops, variables, any of that stuff. All you want to think about is, if I were to approach this problem critically and logically, how would I ensure that I have a working solution that works for all of the test cases that we just came up with? So let's do this together. We're going to come into the tablet again, and here I have brought up our best case test case that we come up with. In this step, we also don't want to think about optimal solutions. We just want to make sure that we have a working solution because a working solution is way better than a non-working optimal solution. So let's come up with a working solution. How do we make sure that we know whether or not there exists a pair inside of this array that adds up to the target? Well, the most obvious way is to try every single possible combination of pairs that exists inside of the array. If none of those pairs add up to the target, then we know that there is no existing pair because we've tried all of them. That's a very sensible way to solve this. So what we can do is we would think, okay, if I want to try every single possible pairs of numbers, how would I logically do that? What you would probably do is pick one number first, so the 1. What are all the possible pairs that involve 1? You would try 1 with 3, 1 with 7, 1 with 9, 1 with 2. And if all of them added together don't equal 11, then you know that there's no possible solution that involves 1. Then you would do the same thing with 3. You would say, okay, with 3 plus 7, 3 plus 9, or 3 plus 2, do any of these equal 11? If not, then you also know that there's no possible solution that involves 3. The moment that you do find a match, however, you know you have the correct answer. This is a very sensible way that you would logically solve this question without thinking about any code. So here, what you're really doing by keeping track of one number and then trying out every other possible combination is you are logically walking through what is known as the two-pointer technique. So the two-pointer technique is a very common technique that you'll use, and it's very simple. You initialize one pointer that points at some value. So let's say our first pointer points at the very first value in the array, so the 1. What you're going to say is that I want to keep P1 pointed at 1, because I want to test every possible combination that involves 1. What other number is involved in that combination is going to be determined by P2, the second pointer. How you move these pointers and where you put these pointers depends on how you're trying to use them. But all the two-pointer technique says is that we have 2 pointers and I'm going to move them based on some specific logic that I want. In our particular case, what we're saying is that, okay, P1 tells us the number that we're testing. P2 is the other number that we're trying out so that we can ensure that all possible combinations that involve P1 are fully tested. Now, how do we know whether or not we have the correct pair? Well, this is where we need to come up with some kind of formula. So here what we can say is that the number to find, which is the number that we're looking for, is equal to our target minus the value at P1. Or in other words, we can say nums at P1 because nums represents our array. In our particular case here, what is the target equal to? It's equal to 11. What is nums at P1 equal to? It's equal to 1. So 11 minus 1 is equal to 10, which means that the number that we're looking for is 10. This is what P2 is going to try and find. It's going to scan through the rest of all of the numbers to the right of P1 and see if any of them are equal to 10. So P2 here starts at index of 1. What's the value here? 3. Is 3 equal to 10? No, it's not. So we want to move P2 forward by 1 space because we've just tested for that value. Is 7 equal to 10? No. So we also want to once again move P2 forward. Is 9 equal to 10? No, it's close, but it's not 10. So we move P2 once again. Is 2 equal to 10? No, it's not. So we've reached now the end of the array. There's no more numbers to test. What this means is that we know for sure there's no possible solution where 1 is part of the final answer. So what this means is that we are certain that P1 cannot possibly be at this position. So what we do is we move P1 over and we reset P2 as well. So now that we've eliminated 1 from contention, we want to test the remaining numbers and pairs. So P1 is now at 3. So we want to recalculate our formula and say that nums at P1 is now 3. 11 minus 3 is equal to 8. So the number that we're looking for with P2 is now equal to 8. So P2 is equal to 7. 7 does not equal 8, so we move P2 over by 1. 9 is not equal to 8, so we move P2 over by 1. 2 is not equal to 8. So once again, we've hit the end of the array. We know that there's no possible answer that involves 3. So what we do is we want to move P1 over by 1, and we also want to reinitialize P2 immediately beside it. And we now know that there's no possible answer that involves 3. So then once again, we recalculate with our new position of P1. So our target stays at 11, but now nums at P1 is equal to 7. 11 minus 7 is equal to 4. So the number to find is 4. Here, what we want to do now is say, okay, the position at P2, what's this number? 9. Is this equal to 4? No. So move P2 over again. Is 2 equal to 4? No. So once again, P2 has hit the end. We know that there's no possible answer that involves 7. So we want to cross out the 7, move our P1 over, reinitialize P2, and now recalculate our number to find. What's the new value of nums at P1? Well, this is equal to 9. 11 minus 9 is equal to 2. And here, when we check, P2 is 2. 2 is equal to 2. We have found the position of the pairs that we need. P1 and P2 are pointing at their exact indices, which means that we can just return as an array P1 and P2. which of course is going to be equal to 3 and 4. And this is our working solution. Now that we have an idea of how to approach the problem and we have a valid logical working solution, what we want to do is actually move on to our next step, which is write out this solution we came up with in code. So I want to challenge you to take what we've just done and figure out how to code that out yourself. This is going to be challenging if it's the very first question you've ever done. And this is just good practice because it gets you thinking about how to convert this logical solution into code as the next step. But you've already figured out the logic, so you don't need to worry too much about that. You just need to make sure that the code properly captures this solution. So try this out yourself, and we'll do it together in the next video. Welcome back, everyone. In the last video, we came up with a logical solution to this problem. In this video, we're going to convert that logical solution into a code solution. So let's go back to our tablet. And what I'm going to do is I'm going to show you the general format of how you come up with this code solution. Oftentimes, it's going to take the format of a function, and this function is going to receive the 2 arguments as its only arguments. And you want to be very explicit about what the name of this solution function will be. So I'm going to name it const find toSum. And the toSum in this particular case is representative of the 2 numbers in the array that sum up to the target. So it's going to be a function, and it's going to receive our 2 arguments, the nums array and the target. The next thing that we want to do is we want to think about how to capture what we did with P1 and P2. Remember, P1 starts at the very first position, and P2 started at the position immediately to the right of it. So here what we're going to do is we are going to capture this by creating 2 for loops. This is actually the easiest way to loop through all of the elements from left to right, starting from some index of your choice. In my particular case, I'm going to start and initialize our first for loop by saying let P1 equal 0, as long as P1 is less than nums.length. Then P1 increments. The next thing to do is to calculate out that number to find. This is where we're going to capture our actual number to find formula. And here I'm just going to say const number to find is equal to target minus nums at P1. So there's nothing here that's different from what we've already written as far as our formula goes. Now what I want to do is I want to initialize P2 with another for loop. So here I'll say for P2, and the initial value of P2 is dependent on the placement of P1. So here I want to say P2 is equal to P1 plus 1, because we're 1 position to the right. And P2 is also going to keep incrementing and scanning through as long as it's less than nums.length as well. And then P2 plus plus. Once we're inside of our for loop with P2, now it's very simple. What is it that P2 is doing? P2 is checking if this current value right here is equal to the number to find. So that's all we're going to do. We're just going to say that if the number to find is equal to nums at P2. The moment this happens, we have our answer. So we can just return an array that contains P1 and P2, which, as we know, are just pointing at the indices throughout this array. And this is all we need, because once we found it, we just return it. If this is not equal, we just let P2 continue iterating through the remaining indices inside of the array, and we're just going to keep checking those values until we find it. If nothing here is found, then we know that for this current value of P1, it's not going to be part of the answer. So this loop is going to end, and there's nothing we want to do afterwards. We just want to let P1 move on to the next index and continue this same process all over again until P1 hits the end of our nums array. The moment that that happens, we know that at the very least, that this portion of our code contains the solution for if a solution exists. If a solution exists, this part of our code will find it. If it doesn't, meaning that if we received an array that doesn't have two numbers that add up to our target, then when running the solution, we're just going to pass by this double for loop and reach the end here. So if it reaches this part, we know that we have not found a solution. And if that's the case, then we can just return null, because we know that if our code ever reaches this second return statement, there must be no existing solution in the given array. This will also capture what happens if we receive an empty array or an array of one element, because it's just going to pass through this code block as well and reach this final return statement. So here, we'll see that this section actually represents what happens when we receive inputs that have no solution. And that's it. We now have this brute force solution that we came up with without any optimizations, but at least it's a working solution. So once we fully coded this out, you want to take this time to move on to the next step, which is step 5, double check for errors. So here, what we need to do is we need to make sure that we didn't make any spelling mistakes, we didn't make any typos, our variable names are consistent wherever we use them. We want to make sure that all of our cases are correct. We also want to make sure that we're closing all of our loops and we're closing all of our functions if we use them. The main key here is just that you want to do the due diligence check to make sure that your code is exactly how it should be for it to work properly. Essentially, you should be able to copy this letter for letter, word for word, character for character into a IDE, and the code should run perfectly. So at this point, this is often where a lot of people get tripped up because they're not used to writing code by hand. Usually we rely on our IDEs as a crutch, and this is why this practice is good. Because by practicing and doing this double check for errors, you'll often find that you catch yourself for little mistakes that you would have made if you were using an IDE as well. But the difference is that the IDE catches it for you. Your interviewer is definitely looking for these mistakes, and they're trying to see if you are a careful and cautious coder. So it's important that you double check for errors. Once you see that your code is all correct, then we move on to our next step, which is step 6, to test the code that we wrote with our test cases. So let's do that in the next video. Welcome back, everyone. At this step, what we're doing is we are testing the solution we wrote against our test cases. The reason why this is a very crucial step is because your interviewer is going to ask you to do exactly this. They want to make sure that you understand what every step of the code you wrote is doing. And the only way that they can verify that is by asking you to walk through your solution using one of these test cases. So they want you to keep track of all the variables you're setting and how the code is going to flow and your logic. So this is very important for you to practice, because if you're not practiced with it, you will get stumbled upon having to walk through this code so rigorously. So let's get some practice together. Here you'll see that I have initialized our best case test case. The nums array that we're receiving is going to be this array of 13792, and our target is 11. What happens is we're going to walk into our code and we're going to initialize our for loop. Here we're going to initialize our P1 value, which is going to start at 0. Then we're going to move into the next line of our code where we're going to calculate and initialize this const of number to find. This is going to be equal to the target minus nums at P1. Target is equal to 11. Nums at P1 is equal to 1. So 11 minus 1 is 10. So I'm going to say NTF for shorthand because I don't have enough space here. So this is equal to 10. Then we're going to move on to our next line and initialize P2 in our for loop. P2 is equal to P1 plus 1. So 0 plus 1 is 1. So I'm going to say P2 is equal to 1. Then we're going to step into our for loop and we're going to do our check. And we're going to see if number to find is equal to the current value at P2. Number to find is 10. P2 is at 1. So this is 3. 3 is not equal to 10, so this ends, and what happens is that P2 is going to increment to 2. So we're going to go back in and we're going to check once again. Is number to find of 10 equal to P2 at 2, which is 7? No, 10 is not equal to 7. So once again, we are going to hit the end of that loop and we're going to increment P2 to 3. 3 is at this value of 9. Is 9 equal to 10 as per our check again? No. So once again, we are going to increment P2 to 4, and then 4 is equal to 2. Is the number defined at 10 equal to 2? It's not. So that means that we are going to try and increment P2 to 5. At this point inside of our for loop, we're going to see, is P2, which is 5, less than nums.length? Nums.length is equal to 1, 2, 3, 4, 5. Is 5 lesser than 5? No, it's not. So that means that this loop closes, we reach the end of this for loop, and we now end this iteration. So now what happens is that P1 is going to iterate to 1. So once again, we're going to step back into this new iteration and redo all those steps. So we're going to recalculate our number to find. And number to find here is now going to be equal to the target, which is 11, minus nums at P1 at 1, which is 3. 11 minus 3 is 8. Once we've initialized this number to find value, we're going to step into our for loop again. P2 is equal to P1 plus 1, so P2 here is equal to 2. Then we're going to do our check. Is 8 equal to nums at P2, which is 7? No, 8 is not equal to 7. So what happens is that we hit the end of this loop, and we are going to increment 2 to 3. Then we're going to check. Is 8 equal to the P2 value at 3? No, 8 is not equal to 9, so therefore we hit the end of the loop, we increment P2 again to 4. Now that P2 is at 4, is 8 equal to 2? No, it's not. So we are now going to increment P2 again. Once again, 5 is not lesser than 5, which is the nums.length. So we hit the end of this for loop, we exit out of it, we hit the end of this for loop, and once again, we increment P1. P1 is now going to be equal to 2, and we repeat this process. So now number to find is equal to target, which is 11, minus nums at 2. 2 is 7, 11 minus 7 is equal to 4. So then we're going to step into our second for loop, and P2 is going to initialize at P1, which is 2 plus 1, which is 3. And now we're going to step through our iteration again. Our number to find is 4. Is this equal to nums at P2, which is 3? 9 is not equal to 4. So that means that we hit the end of this check and we increment P2 to 4. Once again, we do this check again. Is 4 equal to P2 at 4, which is 2? 4 is not equal to 2. So once again, we increment P2. 5 is now once again no longer smaller than nums.length, which is 5. So that means that we've hit the end of this for loop and we reinitialize these values, and P1 is going to increment. So now P1 is going to increment to 3. So once again, we're going to step into this current iteration and we're going to say number to find is equal to target of 11 minus nums at P1, which is 3. So 9. 11 minus 9 is equal to 2. Then we're going to initialize P2 at P1 plus 1. So we're going to initialize it at position 4. So now when we do our check, is number to find, which is equal to 2, equal to nums at P2 of 4? It is. We're going to see that it's 2. 2 is equal to 2, so that means that we return our valid answer, which is an array containing P1 and P2. As we see, P1 is equal to 3, P2 is equal to 4. And as we know, this is indeed the correct answer for this test case. So this is how our interviewer is going to expect us to extensively walk through this process. It's very arduous and there's a lot of steps. So the more you practice doing this, the better, because you're going to eat up a lot of your interview by doing this step. But it's a very crucial step for your interviewer to understand that you know how your code works and that you're not just memorizing solutions. And now that we have this solution, what they're probably going to follow up to do is ask us to test some of our null cases. So let's quickly run through that. Let's run through two cases where we know we have our null cases. The first is where we receive an empty array. What's going to happen is that when we walk through our code, we're going to initialize this P1 value. P1 is going to be equal to 0. What happens though is that we're going to say, is P1 less than nums.length? Nums.length is equal to 0. 0 is not lesser than 0. It's equal to 0. So that means that this for loop automatically breaks. And that means that we hit the end, so we're going to return null, which is the correct answer because there's no two pairs we could get. Similarly, what if we had a different case where we received our nums value of 5? I'm just going to keep target the same because we know that it doesn't matter in this case. But what happens is that we're going to step in, and once again, we're going to initialize P1 as 0. But now when we check, 0 is less than nums.length because nums.length is equal to 1. 0 is lesser than 1, so we can continue with our calculation. We're going to get our number to find, which is our target, which is 11, minus the value at P1, which is 0. So 11 minus 5 is 6. NTF is equal to 6. But when we step into our second for loop, we're going to initialize P2 as equal to 0 plus 1. So P2 is equal to 1. But 1 is not lesser than nums.length because nums.length is 1. So that means that this for loop is going to break. We hit the end of this first for loop, and we increment our P1 again. Now P1 is going to be equal to 1. And 1 is no longer less than nums.length. So this means that this for loop is also going to break. We hit the next line, which is our return. We return null, which we know is also the correct answer for this test case. So here we see how we have to walk through all of our different test cases using our solution. And you can see how this can get very expensive in terms of the time it takes out of your interview. So once again, just practice so that you don't stumble here and you don't make mistakes when you're keeping track of these variables. Because for you to backtrack, you're just eating up more and more time in your interview. So once again, practice makes perfect here. Now that we've done this, the next step for us to do is to analyze the space and time complexity of this solution. So I want you to try and figure it out yourself first before moving on to the next video where I'll show you. And once you've got an idea of what you think it is, check with the next video and we'll do it together. Welcome back, everyone. In the next video, we're going to analyze the space and time complexity of our solution, but now I find it's a good time for me to show you how LeetCode can help us with our interview prep. LeetCode is an aggregate of all the different technical interview questions that are submitted by people who have done the technical interviews. Here, this is the equivalent question that we just did, which is twosome. Throughout this course, I'm going to link you to the correct question in LeetCode for each question we're doing. You'll find in your resources folder this twosome link as well as a link to the REPL that contains the code that we just did. I want you to copy and paste that code into the right-hand side here in LeetCode. Then when you submit this solution, which is that button right here, you will run our solution against every different test case inside of LeetCode. Here you'll see the performance that we've done in our space and time complexity against every other solution submitted. You'll notice that we're scoring somewhere around the 50th to 70th percentile, depending on which one we're looking at. But I want you to understand that these numbers are relatively arbitrary. The percentages and the time and the space will change quite a lot, even on the exact same code being submitted numerous times. It's just a weird thing that they're having problems with on their server. But LeetCode is still a great resource because you'll be able to test your solution against all of their test cases to make sure that your solution accounts for everything. Another great thing is that because it's an active community, every question has that free discussion tab that you can check to see how other people have solved the question, and you can compare your solutions against theirs when you're doing your prep. For a lot of our questions, you won't need to because I will be walking through them so extensively, but it's still a good place for you to get some practice. So now that you understand LeetCode, feel free to use it throughout the rest of your prep, and let's move on to space and time complexity. Hello everyone and welcome back. In this video, we are going to discuss step 7, which is analyzing the space and time complexity of our solution. When you're analyzing space and time complexity, you're trying to identify the relative relationship of how much of the time and space resources your code will consume based on the size of your inputs. Meaning that if you have inputs that scale, which they generally always will, In our particular case, the only argument that will scale is our nums array, meaning that this array could get really, really long and really big. How much more time and space resources is your code going to take? What is the relationship between the size of this nums array and the amount of resources your code needs to consume? So when you're thinking about that, let's start with time complexity. With time complexity, you're thinking about how many more iterations does your code have to run if this nums array were to get bigger. So here, when you're thinking about iterations, the main part of our code that has iterations is the 2 for loops. The first for loop is going to loop over every single element in the nums array. So here you can see that if our nums array grew by 8 elements, then we're going to run 8 additional loops. So this means that this has a time complexity of n. Inside, we have another for loop. And this for loop is nested in the first, which is a hallmark that tells you that combined, these 2 for loops is probably going to run in O of n squared time. So why is this the case? Well, when you look at this second for loop, generally speaking, there are instances where this loop is going to touch the majority of all of the elements inside of the array. So let's just say that it runs in O of n time. We're going to break this down a little bit further, but for now, let's just focus on the fact that it's O of n. Because for every single iteration of the P1 for loop, we're going to run every single for value inside of this loop. This means that we're running n iterations for every single iteration in this first for loop. So it becomes n times n. N times n is equal to n squared. That's how you end up with n squared for a nested for loop. But you might be wondering, Yihua, this second P2 for loop doesn't touch every single value inside of the array every single time. So why is this still n? The reason for this is because we are trying to identify the relative relationship. When you think about a relative relationship, you're thinking about it relative to the size of the input as it grows. So let's imagine that we had a case where we had P1 equal to 2, and then P2, of course, equal to its next value, which is 3. So here, what you're noticing is that P2 is never going to touch any of the elements to the left of P1. It's only going to touch the elements to the right of P1 in this particular instance. So this is less than half the size of the array, and yet it's still n. Why is that? Well, when you think about it when it comes to this relative relationship, imagine that this array had 4 more elements in it. It doesn't matter what those elements are, but just imagine there were 4 more elements at the back of this. What happens is that this first for loop is going to get 4 more iterations. This internal for loop is also going to get 4 more iterations for every single iteration. What this means is that you are getting at least 4 times 4 more iterations, if not more, because for every previous iteration before it, you're also getting plus 4 for all of those n previous loops before, not just the 4 that got added on after. For this reason, you can see how this is indeed a quadratic relationship. So this quadratic just means any value, so n, and then squared. The squared part is the quadratic side of this equation, and we'll talk more about this after. But here you can see how this nested for loop does give us a O of n squared time complexity for this part of the code. Everything else runs in pretty much no scalable time complexity, so the time complexity of our solution is O of n squared. But what about the space complexity? As far as space complexity goes, the only thing that we're doing is we're setting variables, which is P1. And this is a static variable. It doesn't consume any scaling space. And this number to find is the exact same. They're pretty much just pointing to single integers. So this means that our space complexity runs in O of 1 space, which is really good. This is as optimal as it can possibly get. At this point, after calculating your time and space complexities, the question you want to ask is, can I optimize my solution? Here we know that space of O of 1 is as good as it gets. But what about our time complexity? Which different complexities are actually good and which complexities are bad? We know that O of 1 is really good, but what about n squared? Here I want to draw your attention to this chart. You might have seen this chart before if you've done any research into big O notation. This is just a graph that compares all the different complexities against each other in terms of performance, and it's color-coded in such a way that gives you a rough idea of what's good and what's bad. But what I want you to notice instead is actually that anything above n log n, according to this graph, is considered bad. But that's not necessarily always the case. This does give us a good idea in terms of a hint about what's good and bad, but there's actually a different way that we can categorize all of these different complexities. The first categorization is polynomial. This captures complexities such as log of n, which is logarithmic complexity, O of n, which is linear, n log n, which is linear rhythmic, n squared, which is quadratic, which is what we have in our current solution, and n cubed, which is cubic complexity. All of these are considered polynomial, which is better than the alternative, which we'll discuss later. But what makes these polynomial is the way that we can break down what's inside of the brackets. Here, I want you to see that there is a base and there is an exponent. It doesn't always have an exponent, but there's definitely always a base. And this base is always n, which means that if there is a dynamic element inside of this complexity, it's in the base and not in the exponent. What you'll notice is that in the quadratic and the cubic time complexities, these have the exponent, whether it be the 2 or the 3. But what you notice here is that those values are static. They don't change. The dynamic part of the O of n squared and O of n cubed complexities is that the dynamic part is the base, the n. These are all considered polynomial time and space complexities, compared to the alternative, which is exponential complexities. This is where you have exponential 2 to the n, factorial, which is bang, n, and then there is another exponential, which is n to the power of n. In this particular case, all of these complexities scale with the input at the exponent level. The key here is that the exponent is the dynamic variable. Even though you can end up with cases where you do have a base that's also dynamic, as long as the exponent is dynamic, this is considered an exponential complexity. But you might be wondering, Yihua, what about factorial? Factorial doesn't even have an exponent. Why is this still considered exponential? Well, here let's take a look at an example. And let's just focus on the basic 2 to the power of n exponential complexity first. If we had n equals 5 and we looked at 2 to the n equals 5 means that it's 2 to the power of 5. 2 to the power of 5 is equal to 2 times 2 times 2 times 2 times 2, or 2 multiplied by itself 5 times. If you looked at factorial, what factorial represents is that you have bang to the n, which is just bang to the 5, which is equivalent to 5 times 4 times 3 times 2 times 1. It's whatever n is multiplied by every subsequent value all the way down to 1. What you notice in both of the exponential cases and the factorial cases is that as n grows, we're multiplying more values overall, which is why all of these growths are considered exponential growths. So if you were to categorize these two different sets of complexities, exponential should be the biggest sign that your solution definitely can be optimized. But if we go back to this chart, it also does mention that n log n and n squared is also considered bad or horrible. But as we saw, both of these are considered polynomial times. The reason for this is because it does vary based on the kind of question you're solving. Certain problems end up having their most optimal solution falling in either n log n or n squared time. So this is one thing that I do want you to know, that it does vary. Oftentimes, though, those questions are very complex. But we'll definitely learn how to solve them and identify them later in the course. For now, with our simple array questions, we can trust this chart. The fact that we have a time complexity of n squared tells us that we can optimize this further. But this actually helps bleed into our next step, which is step 8, can we optimize our solution? This is what we're going to cover in the next video. But I want you to take a second, look at our solution, and think of a way that you can improve it. And then in the next video, we can do this together. Welcome back, everyone. In the last video, we learned about space and time complexity, and we discovered that our time complexity of n squared is not the best for our given problem. What we want to do is figure out how we can optimize this, and one good hint that you can have is when you look at your two complexities, if one of them is drastically better than the other, such that our space here, for example, is O of 1, which is the best complexity you can possibly have. Here, this is actually a good hint that maybe you can consume more resources in the one that's much better in order to bring down the other complexity. In our case, can we utilize more space in order to bring down the time complexity? This is actually exactly what we're going to do. We are going to try and utilize some type of data structure that will consume more space in order for us to bring down our time. And in order for us to bring down our time, we need to analyze what is consuming up this time complexity in our code. For us, we know that our time complexity lives in these two for loops. So is there a way for us to identify what these for loops are doing so that we can remove one of them or even potentially combine them together? And this is one good hint that you can have when it comes to improving your time complexity. You want to figure out if there's a way that you can merge your two or multiple different pieces of code that are taking up multiple iterations and figure out if you can combine them together. So let's break this down. Let's break down what these two for loops are doing. Now, when we're trying to figure out what each for loop is doing, we want to keep track of it on the side just so that we understand what's happening. So logically, what this first for loop does is initializes some pointer p1, and using p1, it calculates the number to find, the number to find being the opposing pair. So here, we can see that what it's doing is really just figuring out the opposing NTF value that we need in order to designate that we found a valid pair. What does the second for loop do? Well, the second for loop compares the value at that value, so nums at p2, and it checks if it's equal to NTF. So if they're equal, then we know we have a valid pair and therefore an answer. But let's think about this second for loop. The only reason we need this second for loop at all, other than to perform the check, is because our number to find only lives in this instance iteration of the for loop. We don't actually keep this number to find value once p1 moves on because we recalculate it. This means that as long as the number of find is active inside of this loop, we want to check to see if it exists in the remainder of the array. And this is actually very wasteful. Instead, what we want to do is we want to leverage a hash map in order to store this somewhere so that our P1 can move on without us having to do all of these additional checks, because now we actually have this number to find that we calculated stored somewhere. So let's do that now. Let's utilize a hash map. And the reason we want to utilize a hash map is because hash map lookup, which means to get something from the hash map, runs in O of 1 as long as we have the key. And here, what we want to set the key is equal to the number to find. So when we are performing this logic, I don't want you to think about the code, just think about the logic. What we have is this hash map, and inside, what we're going to do is we're going to initialize the P1, and what P1 will do is it will try and capture both of these together in conjunction with our hash map so that we're actually able to perform the two purposes of the two for loops into one. So first, we want to calculate the NTF. P1 is equal to the value here, which is 1. And we're going to do the same calculation. Number to find is equal to target, which is 11 minus 1, so it's 10. So we're going to store 10 inside of our hash map as the key. Once again, the value we're going to think about later. What we're going to do now is we are going to say, OK, now that I have this number to find, I'm going to move on. What I'm going to do is check to see, oh, is this value here equal to anything inside of our hash map? No, it's not. So what I'm going to do is I am going to calculate NTF then, because our second check, which is to see if this value is equal to NTF, failed. So then we want to calculate the new NTF for 3. So what we can do is we can just calculate the same thing. 11 minus this value of 3 is equal to 8. So we're just repeating our formula, and then we're going to iterate and move P1 over. We're going to do this check once again. We're going to see, is there any value inside of the NTFs equal to the current value of 7? No, 7 does not exist as either of our keys. So what we're going to do is we are going to, once again, repeat step 1, calculate the NTF for this value. 11, which is our target, minus nums at this value, so 7 is 4. So we're going to put 4 inside of our hash map, and we're going to continue and iterate P1 over again. Now we're going to do this check. Is 9 equal to any of the values inside of our NTFs? No, 9 is not in here. So once again, we calculate the NTF for this value. 11 minus 9 is 2. So that's what we add as another key. Then we are going to iterate our P1 over again. And here we're going to check, does 2 exist inside of our hash map of NTFs? Yes, 2 exists. So there we found a matching pair. Now, this question is asking us to return the indices of the 2 matching values. So how is it possible for us to actually do this if we now have a hash map? We don't have this second for loop anymore that's keeping track of P2. Well, this is where the value of the hash map can help us. What we can store for the value is the index of the number that gave us this NTF. So the NTF of 10 was calculated from 1, which is at index 0. So the value of 10 is going to be 0. So NTF is the key, value is the index of the number that gave us this NTF. 8 was generated by 3, which is at 1. So that means that 8 is going to have a value of 1. Similarly, when we moved over P1 to this position of 2, and we did this check, we saw that we didn't have anything equal. So we took this 7 and we generated the NTF of 4, and we store this index of 2 as its key. Similarly, when we moved to 9 and we did the check, we didn't see 9 exist in any of these values. So then we generate the NTF, we store it as the key, and then we put the index as the value, which is 3. Now, when our P1 moved over and it did this check of 2, is there any NTFs that equal 2? Yes, there is. What is the index of the opposing pair that gave you this value? It was at index 3. So now all we return is this value and the current value of P1, which is at 4. And that is how we end up with the same answer. And you can see by how we were able to leverage a hash map in order to eliminate this unnecessary second for loop. This is a significant improvement. So my challenge to you is to try and code this out. It's actually really straightforward. You just need to leverage a hash map or an object or a library in your respective language. And then you need to figure out how to utilize just one pointer and then capture these 2 steps together. This is my challenge to you, and let's do that in the next video. Welcome back, everyone. Hopefully you got a chance to try and figure out how to convert our optimal solution into a code solution. Here, I'm going to do it with you. And what you'll notice is that I laid out just our general best case test case, as well as this hash map that reminds us of what the format will be. We want the number to find that we generate to be the key, and we want the index of the number that helped us calculate that number to find to be the value. When we are writing out our function, this just stays the exact same. This part never changes. And what we want to do now is we want to make sure that we're able to access this new hash map throughout the entirety of our solution. So here I'm going to declare a variable, a constant variable, and I'm going to call it numsMap, because that's really what it is. It's a hash map of all the numbers that we generate. And this is just going to be an empty object. Next, what I'm going to do is I am going to implement the for loop that captures the 2 for loops we had in our previous brute force solution. I want to combine the logic of both of these for loops together into the one that we came up with in the last video. So here what I'm going to say is that for let p, so just one pointer, because we now only need one for loop, equals 0, p less than nums.length, and then p plus plus. Inside, now the first thing that I want to do is I want to see, does this current value at p exist already inside of the nums map? Meaning, have we already generated this number to find? What I'm going to do is I'm going to capture it inside of a variable as well, just in case I need to use it more than once. So here I'm going to say that const current map val is equal to nums map at nums at p. Now, if the value exists inside of our nums map, then we will get back the index. If it doesn't, we're going to get back undefined because it doesn't exist yet. We're just going to look for a key that isn't actually in the nums map if we haven't actually calculated the correct one yet. So here what I'm going to do then is to check, do I have the correct index? And here I'm just going to write an if statement. And this is important to remember. When you're using JavaScript, let's say the value that you get back is 0. Because it's very possible that we generate an index that is in the correct pair for the final answer from the very first value. And the first value is index 0. 0 in JavaScript evaluates to falsy when you're using a conditional. So if you're doing an if check, which checks the Boolean conversion value of something, in JavaScript, 0 is falsy. So that's a thing that you got to keep in mind. So instead, what we're going to say is that if the current map val is greater than or equal to 0. If it is, then we just want to return as our answer the current map val as well as the current pointer index inside of an array. And that gives us our correct answer. Now, if it doesn't exist, then what we know is that we need to generate a new number to find and set it in our nums map. So here, I'm just going to do that right now. I'm going to say const number to find is equal to target minus nums at p, the exact same formula that we have been looking at. And then all I'm going to do is just set nums map at number to find equal to p. So I'm setting this inside of our nums map. Then I close it off. And this represents, once again, if we have a valid solution, this code block right here. If our code runs past this for loop and it doesn't actually hit this return statement, we're ensured to know, once again, that no solution exists. So here we would just return null. And this is it. This is our optimal solution. Now, what we have to do once we say, OK, we have our optimal solution coded, is once again, double check for errors, make sure that everything lines up. We make sure that our nums map is called the same way throughout all of our code. We also make sure that all of our variables are named correctly. We make sure that we don't have any spelling mistakes. And we want to just make sure that we close all of our functions. These are the most common places where we might make mistakes. But looking at it, it looks pretty good. The next thing that we need to do, as we did before, is repeat the step where we run through some of our test cases with what we have. So I actually want to leave that to you to try first. Take our test cases and run them through the new solution, going through that extensive process. And then let's do it together in the next video while also analyzing space and time complexity. Welcome back, everyone. In the last video, we coded out our optimal solution, and in this video, we need to run through our test cases. So I'm going to start with our best case test case. Once again, I know this is a very tedious step, but you have to practice this step. What we're going to do is we are going to step into our code and we are going to initialize this nums map. So I'm going to put this up here like so. Once we've initialized this empty object as our nums map, we're going to step into our for loop and initialize a variable p. P is going to start at 0, and we're going to step into the first iteration of our for loop. We're going to need to calculate this current map val. So I'm going to set it as CMV. This value is going to be equal to nums map at nums at p. P is 0, so nums at this value is 1. This object is empty, so there's no keys, which means that we're going to get back undefined when we look for it. So when we get back undefined, this is going to get set as the CMV value. When we do our conditional check, we're going to compare undefined to be greater than or equal to 0. If you perform a greater than or lesser than check of any number to undefined, you will always get back false. So for this reason, this is going to fail, and we're going to step into our else block. Inside of our else block, we're going to set a new number to find value. So I'm going to call it NTF. And this is going to be equal to the target, which is 11 minus nums at p, which is 1. So this is going to give us 10. Then we're going to set this in our nums map. So the key of 10 is going to give us p for the value. So p, of course, is 0. We're going to then hit the end of the for loop, and we're going to come back up and increment p by 1. So we're also going to reset our values. P going up by 1 sets it to 1. And then we're going to recheck. Current map val is equal to nums map at nums at p. Nums at p is 3. 3 does not exist as a key. So once again, this is undefined. We're then going to do our conditional check again. Undefined compared to any value is going to give us false. Going back into our if statement, number to find is target of 11 minus our current value, which is 3. 11 minus 3 gives us 8. We're then going to set 8 inside of our nums map equal to the current p value, which is 1 for the value. We're then going to re-increment all of our values of p, and p is going to go up to 2. 2 coming into this iteration, we're going to once again check. Is the value at 2, which is 7, exist as a key inside of our hash map? No. So that means that CMV is once again undefined. Then we're going to step and check. Is the undefined value greater than or equal to 0? No. We're going to go into our else block. Number to find is 11 target minus 7. So this gives us 4. We're then going to set 4 as the key, and the value is going to be 2, which is our current p value. We're going to hit the end, and we're going to go back up to our loop and reinitialize all of our variables. We're also going to increment p to 3 and do this check again. P at 3 is equal to 9. Does 9 exist as a key inside of our hash map? No. So CMV is once again undefined. Doing our check again, undefined is always going to return us false. So number to find is target of 11 minus 9. This gives us 2. And we're going to set 2 as the key inside of our hash map and give the value equal to 3, which is p. We hit the end of the loop, and once again, we reinitialize our values, and we increment p to 4. Stepping in now, when we do our check, nums at p of 4 is equal to 2. 2, when we look inside of our hash map, exists. We have this key of 2. This means that CMV is equal to the value, which is 3. Then, when we do our check, is 3 greater than or equal to 0? Yes, it is. So what we're going to do is return the array containing both the CMV value of 3 as well as the current p value, which is 4. And as we know, this is the correct answer. So just like that, we see that walking through our code, we have the correct answer. What about a null case? So let's reset this, and let's just look and walk through a case where we have an empty array as our nums array. So I'm just going to erase these as well. In this particular case, our nums map is going to get reinitialized as an empty object. And then when we do our for check, we're going to set p equals 0. But p, of course, is no longer lesser than nums.length, which is 0. 0 is not lesser than 0. So that means that we're going to exit out of our for loop, and we're just going to return null, which we know is the correct answer. Similarly, if we only had one value inside of our nums map, or our nums array, sorry, and we step in, once again, we're going to reinitialize our empty object. We're going to set p equals 0. Current map val is going to check. It's going to see if there is any key of 5 inside of here. No, there isn't. So CMV is undefined. We are going to step into our if condition check, undefined greater than 0. No. So that means that number to find is equal to our target of 11 minus 5, which is equal to 6. 6 is going to get a value of 0 for p. We're going to break our loop, and we're going to step back into our next increment, and p is going to increment to 1. At this point, though, 1 is no longer lesser than nums.length, which is 1. 1 is not lesser than 1, so we're going to exit, and then we're going to return null once again, which is the correct answer. So here we can see by walking through all of our test cases that our solution accounts for all of the edge cases that we came up with. Now we want to think about the space and time complexity after walking through our solution. So when we look at our code now, when we think about time, we only have one for loop, and this for loop will only loop over at most every element once in the array. In the worst case, assuming like we saw, it was the very last value. So this means that we have a big O of n, which is a much improved time complexity over our previous solution. What about space though? We have a nums map, and in the worst case, we calculate a key for every single value inside of the nums array. For this reason, our space scales at O of n as well, because it never gets any larger than the number of elements in the array, meaning that we never generate more than the number of elements in the array for the key value pairs in our hash map. But here we see that we were able to increase our space complexity to bring down our time complexity, which is a great optimization. And this is actually a very good solution. At this point, you'll ask your interviewer if they're content with your solution. Most likely they'll say yes. So with this, we have optimized our very first array question. All of the techniques that we've learned are going to be expanded upon, and this practice and these principles is what we're primarily going to work with alongside learning all of the algorithms and data structures and how they subsist into our interview questions. But the main key is how you tackle these questions and the process of working through the questions, through the steps that we've laid out. That's very important because that shows your due diligence as a developer, which is a very key thing that they are testing you for in your interview. And make sure that throughout this process, you are also very clearly communicating, just as I am when we're coding out our solution together or thinking through our problems. It takes a lot of practice, and that's why practice is so key to your prep. But this process and these steps that we're taking is also going to help accelerate you to help you land that dream job. So now that we've done this, let's jump back into LeetCode and see how our code performs. Hello everyone and welcome back. Back into LeetCode here with our two-sum question. You'll notice that I've already pasted in our solution inside of the solution space. So before we submit, I do want to mention that there will be some weird behavior, but we'll walk through it once I hit submit. When you look at this number, this is why I say not to pay too much attention. You'll notice that the runtime is 92.47%, which is good. We're doing better than a lot of other solutions. But if you look down here at the memory usage, you'll notice that it's pretty bad. Why is that? Well, the reason for that is at line 10, where we set current map val equal to the value from our hash map. If there is a value, we store it. If there is no value, we're just going to return undefined. But either way, we're storing it inside of a variable, which is a best practice. We do this because we end up using this current map val a couple times in our code. We actually use it inside of line 12 and at line 13. This variable actually only has a space complexity of O of 1 because it's a static variable that we're setting. It's not going to scale at all, even if the value of our nums array increases. That has no impact on whether or not this value will grow either, because once again, it's a static variable. For this reason, you will be docked no points in the interview for setting this variable. As I mentioned, it's much more legible and a much better practice. This just happens to be one of the quirks when you're doing your comparisons in LeetCode. But just as an example, let me show you what I mean. Let's get rid of this, and any place where we're using current map val, let's insert in our formula. Now, if we run submit, what you'll see is that our memory usage went up, but for some reason our runtime got worse. And this is once again that weird quirk of LeetCode, where multiple submissions could end up with different results. Here you see we did end up with a much better runtime than before. This just has to do with LeetCode servers. It has nothing to do with your code. As you can see now, our memory usage also is better than that 22% we saw earlier. But once again, these numbers I don't want you to focus too much on. Honestly, as long as you're performing better than 70, 75%, or even yet, let's say LeetCode servers get worse, one important thing that you really want to just analyze is the actual space and time complexity of your solutions. Don't focus on those numbers as much as you want to. You really just want to compare your solution against other people's solution. And you can do that through the Solution tab or the Discussion tab and looking at other solutions. But the key of analyzing space and time and the performance of a solution lies in deeply understanding whether or not you're consuming scaling resources with space and time with your solution compared to what other optimal solutions are out there. So even if the servers aren't working, you can easily compare your solution against other people who have posted their optimal solutions inside of either that little details tab, the solution tab, or the discussion tab. And you can just see where your solution ranks after analyzing the space and time of your solution versus the space and time of their solution. That's the best way for you to not only get more practice with space and time, but also not get thrown off. So now that we understand this, let's move on to our next question. Hello everyone and welcome back. We are going to build upon what we have just learned in our previous array question with this new harder array question. This question is going to flex our critical thinking a little bit more when it comes to coming up with a good solution. The question asks, you are given an array of positive integers where each integer represents the height of a vertical line on a chart. Find two lines which together with the x-axis forms a container that would hold the greatest amount of water. Return the area of water it would hold. Now I know this question seems a little bit confusing at first, but let's visualize what the question is asking us. Imagine we're given this array. This array becomes this bar chart where the value of the element is the height of the vertical line. Each element maps to its corresponding line in the order that it appears in the array. We are tasked with picking two lines that would form a container with the bottom x-axis that holds a certain area of water. Now, what does that mean? Well, in this case, the greatest area is actually from the 8 and the 9. What we have to imagine is that if water were to be poured into this, it would fill up a certain amount of water, which is equal to the shaded area that I've shown here. What we'll notice is that the area only goes up to the 8, because if this were some container and water were to be poured in here, even though the right side 9 is taller, the water would spill out over the left side of the 8. So what we need to do is return the area that this container holds when it comes to the water. And as we know, area is calculated using length times width. In this case, the length would be the height of our container, which is the smaller of the two sides, so the 8, and the width is the distance between our two lines on the x-axis, which is 3. This gives us an area calculation of 8 times 3, which yields an area of 24. So that is the maximum area that we can form from any two lines forming a container in this bar chart. Now, before we go into figuring out a solution to generate this, let's verify the constraints. The first question we might ask is, does the thickness of the lines affect the area? Meaning that if the lines cut into the area in any way that we have to account for when it comes to our area calculation, in this case, no, we can assume they take up no space. They solely represent the height of the walls of our container. The next question we might ask is, do the left and right sides of the graph count as walls? And the answer is no, the sides cannot be used to form a container. So what does that mean? Well, let's imagine we're given this array, which becomes this bar chart. We cannot, for example, take this 7 and form a container using any of the walls on the left or the right side of our bar chart. We have to use a value inside of the array in order to form the other wall. In this case, the biggest container would be formed from the 7 and the 3. So now we know that we must form a container using two values in this array. The next question we might ask is, does a higher line inside our container affect our area?
they'll probably respond, no, lines inside a container don't affect the area. What this means is that if we were given this array, the greatest container we could form is using the 7 and 6, which would fill up this amount of water. Well, notice though that this 8 is taller and sticks in the middle of our container, seemingly breaking our container into 2 parts. The answer though is that we don't have to worry about this at all. In fact, just assume that none of the lines inside of our chosen container affect the area calculation at all. So now that we have our constraints, we can take these constraints and start thinking of some test cases. And that's what we're going to do in the next lesson. Hello everyone and welcome back. In our previous lesson, we learned about figuring out how to form the constraints for this question. In this lesson, we're going to come up with some test cases as well as the expected answer our solution should produce for the given array. So the first thing we have to actually identify is what is the best test case? So here let's just think of an array where it's really obvious what the answer for us will be. So if I put 7, 1, 2, 3, and then 9, we know for certain that we need to use these 2 values in order to form our container. They're the greatest and they're the furthest apart. So we know that the area calculation is length times width. And we know that from our evaluation of the question, the length is going to be from the smaller of these 2 elements. So here, length will be 7. Because if we use 9, well, as we remember, our container would look something like this being the 9, this being the 7. If water were to fill and any more were to come in, the water would simply spill out. So that's why we use the 7. But what about figuring out the width, which is the distance between these 2 elements? How do we get this value? Well, this is easy by just subtracting the indices. So here, if this is 0, 1, 2, 3, 4, we simply subtract 4 from 0, which gives us the distance. And we can justify this if we look at this on our chart. If we drew this out, oh, this is a little bit too high. We can tell that there is a space of 4 units between the 7 and the 9. So using this index calculation, we can now figure out the width between our 2 walls. So once we have this value, we know that what we're expecting is 28, 7 times 4. Now let's think of some other test cases that we can have to make sure our solution covers. One might be that if we have an empty array, we want the max area returned to be 0. Another is that if we have an array of 1 value, we also want a max array of 0. So in both of these cases, no container can be formed because as we know from our constraints, we can only form a container if there are 2 elements in the array. So both of these cases, we have to return 0 because there's no max area computed. Let's come up with one more example. Let's come up with an array where it's not as obvious what the correct answer is. So let's say we had 6, 9, 3, 4, 5, and 8. Here, we don't know if the correct answer is the 6 and the 8 or the 9 and the 8. But as we know, we can calculate the max area to figure it out. So let's take our numbers, 8 and 6. We take the lesser of the 2 as the length, and then we need the width. And the width calculation we get from the indices. So let's just say that for this one, it's 5 minus 0. So that gives us 5. And this gives us an area of 30. But what about these purple values, 9 and 8? So first we take the lesser of the 2, which is 8. And then we get the distance, which is 5 minus 1, which gives us 4. And 8 times 4 gives us 32. So it's actually the 9 and the 8 that is the correct answer. So this is just something we have to keep in mind as a good test case to make sure that our solution will probably cover, but also that when we're thinking about our solution before we even write any code, that we account for this as part of our logical steps. And now that we have our test cases, let's think about a logical solution before we write any code at all. Hello everyone and welcome back. In our last lesson, we came up with our test cases. In this lesson, we have to come up with a solution without any code, which is a logical solution. But the nature of our question is going to be a little different from what we're used to in the last array question that we solved. Let's just quickly go over it because it's going to be important. In the last question that we solved, our question asked us, given an array of integers, and return the indices of the two numbers that add up to a given target. I'm certain everyone remembers this question. As we remember, the question simply asked us for a solution the moment we found one. This means that if we were given a target of 4, and then we were given this array, if we were to find our answer using our brute force solution, let's just take our logical solution. We pick the 1, and then immediately we pick the next number, 3. We see that 1 and 3 added together give us 4, and automatically we found our solution. We just take the indices here, which is the 0 and 1, and we return our answer. Our code is done, our solution is found. This question did not require us, after we found the 1 and the 3, to check any other possible combination of numbers, because our question was simply asking us to return the indices of two numbers that added to a given target. The moment we found our target, we didn't care anymore. Our current question, on the other hand, is giving us a very similar array of positive integers, but here we need to find two values, which represent two lines, that form a container that would hold the greatest amount of water. And then we return that greatest amount. So here I want to focus on this word greatest. This is a maximal value question, which means that we're looking for an answer that is the greatest amongst all of the possible answers that we can come up with. Unlike our previous question, which was where the moment we found an answer, we were done. We could return that we had two values that added to a target. Here, it's different. We find two values that form a container. That does not mean that it is the best possible container. The best container can only be determined if we have every single container first. So that's a very key thing to remember about this type of question, where we're looking for some specific max value. There's a chance that we might get a question that wants us to find a minimum value, which, if you can imagine, we had a same question, but instead of the greatest amount of water, we were looking for the least amount of water that a container could make. Either way, the only way that we know we have the greatest or the least amount of water held by a container is if we calculated every single other container first. And then from amongst all the possible solutions, we picked the one that was the smallest, or we picked the one that was the greatest in the case of this question specifically. So this is a very important thing to remember when it comes to coming up with our logical solution. And this is a very common type of question. Just like our previous question, there's a difference in how we approach the solution, because we have to remember what we're looking for changes how we even solve it in the first place. So this is one thing we need to keep in mind. So let's take our first test case that we came up in our previous lesson and use it to come up with our logical solution. We know we need to calculate every single container, but with this test case, at the very least, we know that the correct answer is created using the 7 and the 9. So let's go over what we need in order to come up with max area. So max area is calculated using length times width. The length, as we remember, is the lesser of the two values we've selected. So let's say that we're using A and B as the variables that hold A being the left, B being the right value. So left, as we remember, is the minimum between A and B, because it's the lesser of the two. Width, as we remember, is the index of our rightmost value, so B, and we can represent it as BI, minus the index of our leftmost value, which is A. So here it's AI. This is going to be our general formula for area, and as we spoke about this question, we need to use this formula with every possible combination of pairs of elements. So let's just do what we did in our previous array question, where we had 2 pointers. The first pointer, which we'll designate A because that's really what it will be anyways. Actually, let's use a different color, just to be more clear. A is our first pointer. B is our second pointer. And B is our value that moves along and checks. And as we remember, this works because B also happens to be the rightmost value. So now that we know what we're doing with A and B, we are just going to calculate max area for these two numbers that we've selected. So let's also keep track of max area. So here max area initializes at 0. Because max area, when nothing's calculated, we can't return null. We just say max area, which has to be a number, and the smallest number is 0. Now we run our formula against the two elements we've selected. So we get the min value between 7 and 1, and then we multiply this by B of I, which here we can see B index is 1, minus the A index, which is 0. So minimum between 7 and 1 is 1, and 1 minus 0 is also 1. So this means that our max area, 1 times 1, is 1. Now we compare our current max area of 0 against 1. Which one's greater? Our new 1 is greater, so we replace the current max area with our new max area. And then we move B forward. So let me just erase all of this. And now we need to recalculate. We need now the minimum value between 7 and 2. And then we multiply against the B index, which is 2, minus the A index, which is 0. The minimum between 7 and 2 is 2. 2 minus 0 is 2. 2 times 2 is 4. Once again, we compare. Is our current max area of 1 greater or our new area of 4 greater? Well, our new area of 4 is greater. So we're going to set our new max area to 4, and we're going to erase our calculation, and then we're going to move B forward to 3. Then we do it again. We get the minimum between 7 and 3. We multiply it by B of I, which is 3, minus A of I, which is 0. And this gives us the min of 7 and 3, which is 3. 3 minus 0, which is 3. 3 times 3 is 9. 9 compared to our old max area of 4 means that 9 is greater. So once again, we return a new max area of 9. We erase this, and we move B forward once again. Now we redo our calculation. We get the min value between 7 and 9, and we multiply it by B of I, which is 4, minus A of I, which is 0. The minimum of 7 and 9 is 7. 4 minus 0 is 4. 7 times 4 is 28. 28 compared to our current max area of 9 says 28 is larger. So once again, we update 28 as the new max area, and then we redo our calculation. Now at this point, we have to shift A forward, and we have to move B back to the first rightmost value of A. So in this case, it's 2. And then we do our calculation again. So here we're going to plug these numbers back in. We're going to get the minimum between 1 and 2. And we're going to multiply it by B index minus A index. So the minimum between 1 and 2 is 1. 2 minus 1 is 1. So 1 times 1 is 1. And we're going to compare it against our current max area. Is 28 greater or is 1 greater? 28 is greater, so no changes happen. B then gets shifted forward, and we erase our previous calculation, and we redo this calculation again. Is the minimum between 1 and 3 multiplied by 3 minus 1, since 3 is the index and A index is also 1. So here, the minimum between 1 and 3 is 1. 3 minus 1 is 2. 2 times 1 is 2. Our max area of 28 is still greater than this new 2, so when nothing changes, B gets shifted once again. Now we do our new calculation. We get the minimum between 1 and 9 multiplied by B index of 4 minus A index of 1. Minimum between 1 and 9 is 1. 4 minus 1 is 3. Max area is 3. Our current area, 28, is still greater than 3, so nothing changes, and we reset our A and B because we've hit the end with B. A now gets initialized at 2. B initializes at 3. And then we restart our calculation. We get the min of 2 and 3. And we multiply this by B of I, which is 3, minus A of I, which is 2. The min of 2 and 3 is 2. 3 minus 2 is 1. This gives us a max area of 2. Compared to our 28, 2 is smaller, so our max area doesn't change. B will move forward, and we need a new calculation. Now, we redo our calculation. We get the min of 2 and 9, and we multiply this by 4 minus 2. The minimum of 2 and 9 is 2. 4 minus 2 is 2. Area is 4. Our max area of 28 is still greater, so once again, our max area doesn't change. And now we reset A and B again. A instantiates at 3. B instantiates at 4. We do our calculation. What's the min of 3 and 9 multiplied by B of I, which is 4, minus A of I, which is 3. Min of 3 and 9 is 3. 4 minus 3 is 1. Area of 3. Max area 28 is still greater. We've hit the end of our calculation. 28 remains. And there's no other cases left to test since we move A over. And there's no B that can be initialized. So we have our final answer of 28. So now we have our step-by-step logical solution. What I want you to do is actually try yourself first to see if you can turn this into a code solution. I'm going to show you in the next lesson, but this is a good chance to practice every single time. So give it a try and see what you come up with. Hello everyone and welcome back. Hopefully everyone got a chance to try and code out the solution we came up with in our last lesson. But if you didn't, that's perfectly fine. This is how I would do it. I've essentially moved over that test case that we had written and we're testing against, and I've just written the function that we remember for our area calculation that we came up with. Here I've just initialized the function. I'm calling it getMaxWaterContainer because that's what we're trying to do. And what gets passed in, which is this array, I'm just giving it the variable name of heights, because that's what they are. Each one is the height of a line. Now, inside, we need to keep track of that max area variable that we came up with. So here I'm just going to use the let to say that this is a variable that can change. The difference between const, which you've seen me used, is just that const can't change in JavaScript, whereas let means that this variable value can actually change. So that's just a little quirk in JavaScript if you're unused to it. So I'm going to say let max area, and I'm going to initialize this value at 0. Now, you remember that we needed 2 pointers, P1 and P2. So let's actually just do the same thing we did in our previous array question, which was the double for loop, because that is pretty much the same pattern of how these 2 pointers are moving throughout the array and giving us their respective values. So here I'm going to initialize my first for loop and say let's P1 initialize at 0, while P1 is less than heights.length, then P1 increments. Now, before we move on to our second for loop, we need to think. Do we do anything with the value at P1 that doesn't need anything at P2? Do we need to initialize anything or create any variables? We don't. Our solution is purely based on P1 and P2 together, so we don't actually need to do anything inside of our first for loop. We can just immediately step into our second for loop. So here we want every single value to the left of P1. So I'm going to initialize P2 equal to P1 plus 1, the same way we did in our previous array question, and then everything else is the same. We want P2 to traverse up to the end of our heights array, and then P2 increments the same way. And now that we have P1 and P2, remember our actual area function. What we want is this calculation right here. We want to get the minimum value between A and B. So inside of your language, there's probably some shipped math min method by default. You have to figure out what yours is. In JavaScript is math.min. I'll show you how it works. So first what we want to do is we just want to initialize some value called height. And here I'm going to pass in math, which is just this object that ships in any JavaScript execution context. And on it are all these different methods that can do some kind of math-related functionality. So here it's math.min that I want. And what you can do to it is you can pass in any number of integers. So let's say I pass in 1, 2, 4, 7, 3. What this method gives me back is it just returns me the value that is the least. So here it just gives me back the 1 right here. So that's all this math.min does. Every language has their own version of this, I'm pretty sure. You just have to find it. So here what we want to pass it is we want to pass the heights value at P1 as well as the heights value at P2. So that's what we're doing. This is the exact same as what we were doing here. Except instead of A and B, those values are at P1 and P2. That's the only difference. Once we have our height, we also need to calculate our width, which as we remember is just the index at B minus the index of A. So the index of P2 minus the index of P1, which is P2 and P1 respectively. So here we can say const width is equal to P2 minus P1. And that's all we need for height and width. Now what we need is we need the area. So here, if we remember, it's just the multiplication of those two values. So we can say const area is equal to height multiplied by width. Next, what we need to do is we just simply compare our existing max area against our newly calculated area. And remember, we want the maximum between these two values. So just as you might suspect, there was a min that we just used right here. That means that there must be a max, most likely as well in the math object. And in our case, there is. So it's very important that you do find that method. What we can now do is we can say that the max area is equal to math.max between the current max area and our newly calculated area. And then we just close our brackets. So let's close our second for loop, and then the for loop right after. And then we just return our max area. And now we also close our original function, and this is our solution. So it looks relatively similar to what we had in our previous array question, because the way that we were moving through this array is pretty much the same. So let's just now double check for any spelling mistakes, make sure that it's all working in case we have any typos. And to me, it all looks okay. This is a good chance for you to just double check your code and see if everything's okay. And now that we have a working solution, or what we believe to be a working solution, we have to run it against our test case. So here what I've done is move the code we just wrote into its own REPL file. We're going to test it against our test case that we've been writing here. And we see we get the right answer of 28. This is what we were expecting. What I want everyone to do, though, is make sure that every line of our function is doing what we came up with in our previous solution. So just make sure everything works. Also, test it against all those previous test cases we came up with, and make sure that this solution is a valid solution. So everybody take a crack at it using either this REPL code or your own handwritten code, and in the next lesson, I'll walk through it as well. But I just want everyone to take the challenge and do it themselves for practice. And I'll see you in the next lesson. Hello everyone and welcome back. Hopefully everyone got a chance to step through the code that we wrote step by step using this test array. If you did, you noticed that this is pretty much the exact same step-through process as what we did in our logical solution before we even wrote any code. Pretty much a one-to-one map of the logic we came up with. So I'm not actually going to do that with this question and this test array because it's not going to be that different from what we've already done, and I don't want to waste your time. Instead, what we'll do, though, is walk through one of our cases where max array returns 0. So let's just say we have an array of one element. Here we know that a container can only be formed with 2 elements, so theoretically, let's see why our code causes this max array to return 0. In fact, if we run it, we'll see that what we get is 0, so let's just justify this. What we do is we first console.log the max area. We also want to console.log p1 and the value of p1, which is heights at p1. And inside, we also want to console.log p2. Now, we know we should never step into this for loop's value and log p2. The reason for this is because of our logic. We see that p1 starts and initializes at 0. What will happen is that p2 gets set at the value of p1 plus 1. So it's 0 plus 1, which gives us 1. That's what p2 gets set to. 1 is not less than heights.length, because here heights is an array of one value, meaning length will return 1. 1 is not less than 1, which means that it should never step into this for loop. And if we run our code, we'll see that that's what happens. We do log max area, which starts at 0, and then p1, which is our value of 5. p2 never gets logged because it doesn't actually step into our for loop. So then automatically it returns our current max area, which is 0, which is what we see right here. So that's the logic of stepping through one of our 0 cases. Now that we've done this, let's actually think about the big O. What is the space and time complexity of this function? So just by looking at this, we can probably tell that this is very similar to what we came up with in our original array question. We have 2 for loops, and as we know with 2 for loops, our time complexity is a big O of n squared. So here, we see that nothing has really changed. We still have 2 for loops, and the logic inside doesn't really scale with our heights increasing. The main thing that changes is that we have to perform more operations for our first for loop and our second for loop. So based on that logic, we know our scalability is n squared. What about our space complexity? Well, with our space complexity, we're also not storing any scaling thing in our memory. Here we see that yes, we calculate height and yes, we calculate width, but these are all static values that don't change. Max area gets updated, but the size of max area, in the sense that the quantity of information we're storing, also doesn't change. So here we have a very similar situation where we have a time complexity of n squared and a space complexity of O of 1. So as we remember from our previous lesson, what we want to do is optimize the space by using up more of it so that we can bring our time complexity down. So that's going to be very similar to what we're trying to do again in our optimized solution. But before we do that, let's actually run our solution against LeetCode just to see. Exact question in LeetCode is number 11, container with the most water. And I've pasted our code that we just came up with into it, and let's submit and see how we do. So here we see that our memory usage is fantastic, 97%. We expected this though. We have an O of 1 space complexity, but our runtime is pretty bad. 22.39% is honestly really bad. But we expected this. We know that we have a suboptimal time solution. And we also predicted that our space would be great because it's O of 1. So how do we level this out a little bit more? Well, let's do that in the next lesson. We're going to actually explore a new technique with these 2 pointers that is going to really help us level up with our array questions and our understanding. So let's do that in the next lesson. So now we reach that crucial step where we ask, can we optimize our solution? Going back to our code here, we know that we have a time complexity of O of n squared and a space complexity of O of 1. The n squared is formed by our double for loop, and when we did this in our first array question, we were thinking of ways to increase our space in order to decrease our time. But we need to rationally think about this. Is that same approach going to help us here? And this is a very important thing because we need to actually think about what this question is asking us and how our solution attempts to solve it. What are we doing? We are storing the max area that we've come across so far of every area that we calculate using P1 and P2. So this double for loop does not separate because we need P1 and P2 together in order to figure out the area. And that's why we have no step in between these 2 for loops, which means that there's actually no additional caching that can happen for P1, this first for loop. What about the second for loop? Is there anything we can do with memory in order to improve this process or even eliminate this for loop as a whole? Well, what we do is we calculate the height and width using these 2 P's, and then we get the area. Then we essentially just check against the max area we've got so far, and we see if we need to update it. But there really is nothing here that we're doing that would consume more memory because the moment that we're done with this area, we don't need it anymore. If we needed it and it was greater than what we had, then we would have stored it already. But there's nothing here that we can do in order to scale our memory in order to improve this process. So what we did last time is not going to work here. And that's a very important thing because we need to really rationally think about this problem. So what we do need to do that can improve this is actually learn a new technique, which is known as shifting pointers. And let me show you what that is. So here I have generated a new test case for us, and I switched the pointers from P1 and P2 to A and B to better match what we have in our formula. And I want us to really think deeply. Now, this new test case will help us understand this new concept, but I also want to build upon the knowledge that we've gained so far from both our previous array question as well as what we've just done with our 2 pointers in our non-optimal solution. Let's first think back to our original array question, the very first one we did. If you remember, we were given some target value. Let's say using the same array, that value was 13. We know that when our first pointer is pointing at this value and our second pointer is pointing at this value, 4 and 9 add together to give us 13. And there we had our solution. The key difference here is that the distance between A and B didn't matter with that question. A and B being on the opposite sides of the array has no impact on how we come to the solution for finding our target. In fact, this is easily demonstrated that if our target changed to be 6, this means that in order for our solution to work, B needs to be in this place here. But this has no impact. A and B being anywhere in our array doesn't change how we find our target. But this is not the same case as our current question. We know that with our current question, the width has a direct impact on the actual area. We know that by looking at our equation, we can see immediately that the distance between A and B has a direct impact on the value of the area that comes out of it, because that's the nature of multiplication. The other thing we need to note, though, is that we don't really know whether or not it's increasing or decreasing that will change this area outcome, because it varies from a case-to-case basis. It's not a guarantee that as long as A and B are greater distance apart, then somehow our area goes up. That's not the case. We can actually see that directly in this current example. Let's do the calculation for the area now, using the placement of A and B right here. So the minimum between A and B is the minimum between 4 and 9. So 4 is the minimum value. As for B index minus A index, that's 5 minus 0, which gives us 5. So 4 times 5 gives us 20. But what happens if we move A forward by 1? So let's move A forward and do a new calculation. We'll keep the 20 as a reference. A moves forward to 8, and now we have to recalculate. The minimum between A and B, so 8 and 9, is 8. And B of I, which is 5, minus A of I, which is 1, is 5 minus 1, which gives us 4. 8 times 4 gives us 32. So automatically we can see that by shrinking the size of our width, we actually ended up with a larger area. So this leads us to our second point, which is that if we really think about what just happened, the outcome of the area is impacted by the lesser of the two values of A and B. We saw that by shrinking the distance between A and B, we somehow ended up with a larger area, which tells us that the only value in this part of the equation that has some impact on the outcome of the area is the smaller value. So let's just go back to what we had before. We saw earlier what happens if we were to move our smaller value. By increasing it, we saw a direct transformation where the area got bigger. But what about the larger value? What about B? Let's say we move B inwards. What are the only possibilities that could happen for B? Well, B either gets larger or it gets smaller. So let's explore these two cases. Let's say B got larger first. So instead of 3, just imagine it was 12. When we were to plug this into our area calculation, what happens to the min? It's still going to be 4 against 12, which means that the number that comes out of this is still 4. This means that even though B got bigger, there was no direct impact on our area calculation. So now we know that if the larger number gets larger, it doesn't matter. We don't even care about it. But what happens if the larger number gets smaller? So instead of, let's say, the 12, let's say it becomes the 3 in the place that it is right now. So now the calculation becomes the min of 4 and 3, and now our min changes. Our min becomes 3. So here we actually see that our area would have been smaller in this case, because not only did we decrease the value on this side, we've also decreased the value on this side. So we know that for the larger value, the only case is that by changing its placement, we have somehow decreased our total area. And we don't want that. We only want to figure out if we can maximize the area, if there's a way for us to increase the area possible. So now let's put these two ideas together. We know that the only thing that really matters when it comes to moving either A or B is trying to move the smaller value forward and try and see if that somehow yields us a larger calculation. And that's going to be the real crux of this optimal solution and this new technique, which is known as the two shifting pointers. So what we want to do is exactly what we have here. We want to initialize 2 pointers, but we want to initialize them at the opposite sides of the array. Because what we're doing is we're maximizing this value right here. We want to get the biggest calculation possible for width because it does have an impact. And we also want to make sure that as we shift our values, there's no possible way where the values on the outskirts, meaning the opposing sides of our variables, could possibly give us a larger container. So we just got to make sure of that. And how we make sure of that is just by starting on the ends. So now our calculation becomes, what is the smaller of these two values? We're going to calculate the area first of A and B. So we did this calculation already, but let's just do it again. But we're also going to keep track of the max area that we find so far. Very similar to what we did before. And let's just say it's max and which starts at 0. So the minimum between 4 and 9 is 4. And 5 minus 0, which is the indices, is 5. So 4 times 5 is 20. And that's bigger than our max area, so let's update that. Next, let's move A forward, because A is the smaller value, and as we mentioned, we only care about the smaller value. A moves forward, and now we get the min between 8 and 9. So this value is now 8. And the distance is 5 minus 1, which is 4. 8 times 4 is 32. And we have a new max area of 32. Now we have to shift the smaller over once more. So A comes over, and we do our calculation once again. The min between 1 and 9 is 1. 5 minus 2 is 3. The area here is 3. 3 is not bigger than 32, so nothing happens in terms of our max area, but we shift our values over again. And this time, we do our calculation the exact same as we did last time. The min between 2 and 9 is 2. The distance is 5 minus 3, which is 2. So this gives us an area of 4. 4 is still not larger than 32. So we do our A shift again, which is because it's the smaller number. And now the min between 3 and 9 is 3. B and A is 5 minus 4, which is 1. So once again, we get another container area of 3. 3 is still smaller than 32. So our max area now is done. We have no more room for any of our pointers to move because they've just come up against each other. So now we have our answer. 32 is our maximum area. The other thing that we'll notice is that we've also only touched each element once. This means that we've managed to bring our time complexity down to O of n, which is a drastic improvement from O of n squared. Every element will only be operated on once. And then after that, we are definitely moving one of our 2 pointers. We don't know which one, but one of them is moving, which means that at most we performed n operations on this array. So this is the thing about 2 pointers. The main key with the 2 pointers is that we have to think about how we move these 2 pointers, when it's considered done moving, and also what is the rationale between determining which of them to move in the first place. We were able to figure this out because we were able to see from our area calculation that the minimum value between these 2 was the only one that actually directly had an impact on an area getting bigger. The other thing was that we were able to see that the width had some factor to do with it, because in some ways, when the width changes, these 2 values must change. One of them has to change. So we just had to figure out which one of them to change, and by looking at this minimum value and how it affects the area, we could see that by moving the minimum value, that was how we could possibly end up with a larger area. So then the optimization just became, okay, let's shrink our width on every operation, but then conditionally based on which value was smaller would be the one that we shrunk, and along the way we just calculate the area and store the max area the way that we've been doing before. So I know that a lot of that is really new knowledge. And this process of breaking down this equation into the rational steps to do this is going to be one of the key things in critical thinking that we need to work on. And really thinking deeply about these things that seem at first very basic. Because within them lie the chance for optimization when combined with these technical tricks such as this 2-pointer style of problem solving. And this course is really going to focus on these 2 things. We're going to learn some of these technical tools that we just saw with the 2 pointers, but also how do we build up a mental framework so that we can rationally break down what the rules are and how we can best utilize these tools in order to deliver us an optimal solution. So what I want you to do now is take what we've just seen and try and code it yourself. It's going to be a little different from what we did with the for loops, but it's still good to give it a try. If you can't figure out how to do it, no problem. That's what we're going to do in the next video. So let's code out our optimal solution. We know that what we're utilizing is the two-pointer technique, but here we actually have to use a new coding pattern in order to capture what we're trying to achieve. So we're going to initialize 3 values first. The first is P1, and this P1 is going to start at the beginning of the array, so it's going to start at 0. We're also going to initialize P2, and this is going to start at the end of the array, which is heights.length minus 1. Because remember, the length is going to be a number where it's not indexed at 0, but we want the last index, so heights.length minus 1 gives us that last value. Then we also want to keep track of max area, and let's make it 0 to begin with. Now what we're going to do is we're going to use a while loop. And what we're going to say is that we want to check while P1 is less than P2. Then we want to run some logic, and at the very end we need to decide whether or not we want to move P1 towards the center or we want to move P2 towards the center. So inside of our while loop, the code here is going to be the same as our previous, which is get the area and then compare it to the max area and store the greater one. So here we're going to do the same thing we did last time, which is we're going to get the height, and it's going to be math.min of our heights at P1 and our heights at P2. Then we want to get our width, which is also going to be the exact same. It's going to be P2 minus P1. And then we want to get the area. And the area is going to be height multiplied by the width. And now our max area is going to update also. We're going to get the math.max between our current max area as well as our newly generated area. This logic of the comparison, getting the area, exact same. But here we're going to do that check where we're going to see which value was greater. So we want to say, if the value of heights at P1 is less than or equal to the heights at P2. So let's just account for the fact that if the numbers are equal, we're going to move the left one. It really doesn't matter where the equal side of this goes, but we're just going to say that as long as it's lesser than or equal to, then we want to move P1 forward. If this is not the case, then what we want to do is move P2 towards the center. And this is pretty much all the logic we need. So here, let's just make sure to close our while loop. And let's also close our actual function. But first, we got to return. We got to remember to return our new max area. And this is our function code. So now that we've coded out our solution, let's step through the code and see what's happening. So here I've moved the code we just wrote into its own REPL file. You can use this REPL file, which is always in your resources folder, or you can use your own handwritten code. And what I want you to do is actually try first. Pause the video and try it yourself. Just take our array that we were working with and run through this code and see if you understand what's happening at every step. Once you've done that, you can come back and either go to the next video if you're fairly certain you understand what's happening. Otherwise, I'm going to walk through it myself. So here inside, let's just console.log out our initial values that we've initialized for P1, P2, and max area. Once we're inside our while loop, we want to console.log the P1, P2 index values because we just want to see what's happening. And then down here, I'm going to console.log out both the height, the width, and the area calculations. Then we're going to console log what our new max area is. And here we don't need to console.log the if statement because P1 and P2 are being logged up here anyways, so we're going to see what happens. At the very bottom, we'll return the max area, which is getting console logged out anyways, so we'll see when our function ends. And now if we run our code, we'll see that we initialize P1, P2 at 0 and 5, which are the indices of the start and the end of our arrays, respectively. Max area, of course, initializes at 0, and we step into our first instance of our while loop, logging out the same P1, P2 values of 0 and 5. Now, once we hit this log here, we see that the height calculation is 4, because the lesser between 4 and 9 is 4. The width then is 5, because 5 minus 0 is 5, and then the area is 4 times 5, which gives us 20. So these are the same steps that we did when we did our logical step through before we did the coding. Here we see that our new max area gets set to 20, and P1 increments, because height at P1 is less than height at P2, since 4 is smaller than 9. So P1 moves over by 1, P2 is still 5, and then we calculate new heights. The new lesser height between the 8 and the 9 is the 8. So width is set to 4 because it's 5 minus 1. New area is 32, and our max area is 32. P1 then increments to 2, which now points at this 1. And now height is set to 1, as we are seeing. The width is set to 3 because it's 5 minus 2, which gives us 3, and then the area is 3 times 1, which gives us 1. Max area is still 32 because 32 is greater than our area of 3 that we've calculated, and then we shift P1 over to 3, which is now this 2 value. P2 stays at 5, and then height is 2, width is 2, our new area is 4, max area stays the same. P1 is going to increment one more time to 3, and then P1 is 4, P2 is 5, new height on our P1 is 3, width is 5 minus 4, which is 1, the area is 3, and our max area doesn't change, and then finally we return with our max area of 32. So here we see that our code still works for this, and let's just double check to make sure it also works if we have an empty array. We see it returns 0, and if we input just one value, we still return 0. So all of our code still works for all of our edge cases. So here we are back in LeetCode, and I have pasted our optimal solution into this answer space. It's still the same question, number 11, container with most water. And here if we submit, let's see how we do. So we see that our time is now 40 milliseconds, which is in the 99.97th percentile of speed. Our memory says 35.6, but this is one of those nuances with LeetCode, and it's less the fact that our memory actually got much worse. If you actually think about how the memory storage works, as I mentioned in terms of scalability, none of our variables that we're storing in memory actually scale with the size of the input, so this is definitely O of one space. Don't look at this space percentage here and think that you're actually doing something wrong. This is just one of the quirks of LeetCode, but the main thing is the actual evaluation of how your space consumption is in your function. This is a very crucial thing because we are really trying to work on our ability to understand what our time and space complexities are versus just looking at these percentages and then judging how well we're doing off of it. The key here, though, is that we need to look at the space here. We know that everything is pretty much just a static variable. It doesn't actually grow any larger. We're not using any arrays. We're not using any growing objects / hash maps. So theoretically speaking, everything here is O of one space. That's just a little caveat I want to mention about this percentage. If you see that, don't let it throw you off. Again, just evaluate by your code. So now that we have our optimal solution for this question, we've got a pretty good understanding of a new technique, which is the two-pointer technique, as well as a rational framework of thinking about how to move those pointers when it comes to looking at a question and then thinking deeply about what impacts the solution of that question. Let's apply this to a harder question now. We noticed that this question we just did was a medium question. The first one we did before was an easy question. And the next question we're going to do is a hard question. I don't want you to let these throw you off too much. It is a good guideline for what level of question you should work on. But at the same time, a lot of these ideas, I want to show you that they build upon each other and they're compounding. So don't let the difficulty throw you off from taking a chance at trying and thinking about the question, because that's what we're going to do with the next one.
Welcome back, everyone. So far, we've done one array question and one medium array question. Now we're going to do one hard array question. And this is going to be a great question because it's not going to bring together everything that we've learned in our previous two questions, but it's going to push them to their furthest limits and really test how well we can problem solve and apply our critical thinking. Now, I actually really love this question because of this exact reason. It really makes us have to flex our abstract thinking in order to understand how to come up with a good logical solution before we even do the coding part. Because the hardest part of these questions is always the portion where we have to figure out how we rationally solve this question, whether it be for the brute force first solution or for the optimal solution. In fact, it's very often with the optimal solution that it feels like it's almost like a brain teaser, that there's some kind of mental trick that we have to step outside of our comfort zone and think outside of the box in order to get to. And that's actually kind of what it is. It is almost like a critical thinking puzzle where you have to look at the basic information that's in front of you and see if you can think deeply and derive some patterns and hints that will guide you towards knowing what technical tricks or what data structures and algorithms to apply in order to solve the question. And this question really demonstrates that. I know that this is a hard question and it seems like we're going a little fast, but I don't want you to be intimidated because we really need to be able to apply our critical thinking through challenging questions. Because the more challenging the question, the more we actually glean once we solve it. Okay. That's enough talk from me. Let's just move on to the question. So this question asks, given an array of integers representing an elevation map where the width of each bar is 1, return how much rainwater can be trapped. Now, don't let the elevation map term confuse you. This is very similar to our last question. In fact, we'll see it in an example here. Imagine we were given this array. How this looks like is going to map out into this bar chart here, which is very similar, if not identical to our previous question. The only difference is that the width of the bar is 1 here, which means that it plays a role into the actual question. What we also need to notice is that these elements are now pushed together, whereas in our last question, there was some inherent distance between the bars themselves. Here, the only distance is when the element is 0. You can see that throughout this bar chart, there are some gaps in space at the very bottom, and that is when an element in the array has 0 in its value. Other than that, there is no actual distance between our bars. Now, what we have to imagine is that given a chart like this, if rain were to fall down onto this chart, how much water would get trapped? Well, here I've visualized it for you as these blue boxes. And all we really have to do is just count the number of blue blocks here. And we'll see that in the first, there's 1 blue box. In the second blue area, there are 3. And then in the third blue area, there are 4 blue blocks. So you just add that together, 1 plus 3 plus 4, which gives us 8. And that's what we would return as the answer. There are 8 units of water. So this question, when we visualize it, looks actually very simple. But when we actually have to solve this logically without some kind of visual aid, it becomes more challenging. But the first step, as you know, we have to do is verify our constraints. This question's a little bit more clear, so there's not as many constraints here, but it's still good to ask some. The first one we should ask is, do the left and right sides of the graph count as walls? We asked this question with our last graph, we should ask this question with this graph. We'll get pretty much the same answer. No, the sides are not walls. And we can actually see this demonstrated in this example we looked at earlier, where we saw that this area here didn't have a blue block. Well, that's because we couldn't form any container using the left wall of the chart and the first block in our actual array. So here we know that the sides cannot be used to form anything that will trap water. The next question we can ask is, will there be negative integers? And here we can say no, assume all integers are positive. And that's actually all of the constraints that we need in order to figure out this question. It's actually a pretty straightforward question because we have a visual idea of what we're looking for, and there's not much here that could really affect how we might think about edge cases. So let's move on to the next step, which is where we write out some test cases. So for our first test case, let's actually just use that same array that we had when we first came up with an example. So here I'm going to say that it's going to be an array that gets 0, 1, 0, 2, 1, 0, 3, 1, 0, 1, 2. And remember with this one that the correct answer was 8. And we'll explore it later as well when we actually think about our solution, but this is going to be our best case test case. We also know that we want an array where we get something like an empty array, and then the answer will be 0. And also if we get an array of one value, let's say it's 3, we also get 0. And just for good measure, we'll also say we'll get something like this, where it's 3, 4, 3. And here we'll also expect 0. Because if we were to chart this one as a graph, we would see that if we assume that these were our tick marks, 1, 2, 3, and 4, that this would look something like this. Which, as we can see, can trap no water. Because we can't use this wall in order to store any water here, and then any water here would just essentially fall off. And this is actually enough test cases for us to move on to our next step, which is to come up with a solution without code. I'm going to challenge you to do this step yourself because this is a very important way for you to really figure out how to work your critical thinking muscle, even with the brute force solution. This is a difficult question, and it has enough similarities to what we've done before that you might actually be able to figure out a way yourself. Once you have a solution, you can compare it to mine. But if you're a little bit confused, no worries. We're going to cover it in the next lesson. Hello everyone and welcome back. Hopefully everyone got a chance to try and think of a solution themselves. If you haven't, that's perfectly fine. This is a pretty challenging problem. What I'm going to do is I'm actually going to highlight some of the similarities to how this question ties to our previous question of the water container. But I'm also going to highlight some of the new abstract thinking that we need to have in order to understand the differences and how those differences can help lead us to coming up with a solution. So one of the first things that we notice is that this question, unlike the previous question, requires us to actually use the entire array in order to generate the solution. In our previous question, we were only required to find any two elements in the array that would add up to some greatest container of area of water. Whereas in this question, it's almost as if we're trying to figure out how much area of water could in total be held in the entire array itself. And this is much more clear with this visualization. But this question does share some logical similarities to our previous question about finding the maximum container of water. In fact, if we were to just focus on this section here, this little container of water formed by the 1, 0, and 2. If we look here, we'll notice that there's some similar logic in the sense that the smaller height of the two walls that form this container is the actual one that determines how much water can be held. Or at the very least, what's the maximum amount of water that can be held? Because we know that the height of water here can never exceed the height of the smaller of the two walls, particularly this one. So keeping this in mind, let's see if we can take that logic and see if there's any differences with a different body of water. Let's look at this 2, 1, 0, 3 area here. Here we see that it's the same in the sense that between the 2 and the 3, which form the container of our body of water, The 2 is the one that actually determines the maximum height that the water can go up to. Now, the next thing that we do have to realize, though, is that inside of this body of water, this section right here, the 1, cuts into how much body of water we have. This then tells us that not only is the smaller of the 2 walls that form the container determine the height of the water, but also that the heights on the inside of the container also affect how much water is inside. This becomes really apparent if we move over and look at this container here, the 31012. We know that between the 3 and the 2 is the smaller side, so the maximum amount of water that can be contained can only be of height 2. But what we also know is that the 2 ones inside between the 2 walls also reduce the amount of water that can be captured within this container. So this kind of changes how we would approach this if we were to follow our original question of container of water that we just did. Because in that one, as long as we had the 2 sides, yes, the smaller side was the one that affected the area, and yes, the width also mattered, but we didn't have to account for this additional blockage here. So here we're seeing that we're actually breaking up this problem into much smaller problems. Instead of focusing on the array as a whole, we're trying to focus on smaller sections so that the logic is easier for us to figure out. In fact, we can even go a step further. Then what we want to do now is actually focus on individual elements, and based on those individual elements, try and figure out if we can determine how much water can be stored at any given element. Meaning that if we were to look at this element right here, this 0, what we notice is that the container is formed by not the immediate walls to the side of our value of 0. It's not the 1 and the 1. In fact, if you remove this 1 and 1, just imagine that these were both 0. This container would still be formed because some value to the left and some value to the right of our current value of 0 is higher than our current value. The 3 and the 2 are both higher than 0, meaning that a container can be formed. But let's sub these 1s back in. So imagine it's exactly what we see here. We don't form the container for just this value of 0 with just the first values that are higher than 0. This can be very easily demonstrated with a different diagram, which I'm going to draw for you. So let's look at this graph that I've just drawn for you here. And what I want you to focus on is this 0 value with the P under it. If I were to ask you how much water is above this value, what you would probably do is you would rationally think, okay, what's the container size? Well, here, the container we can visually see is formed using the 4 and the 5. And the logic here is that the 4 is the greatest value to the right of our P, and the 5 is the greatest value to the left of our P. There are values in between, but they don't form the actual walls of our final container. It's going to be the greatest values, the max values left and the max values right. With the 4 and the 5 then, being the walls of our container, we take the smaller of the 2 sides, which is this 4, and then we subtract it from our current height of 0. So 4 minus 0 gives us 4. And that's how much water is above this P. And just like that, we realize we've actually just come up with the formula for calculating how much water is above any single point in this array. And we can actually test this using another pointer. Let's just point at the 3 instead. So looking at this 3, we do the exact same thing because our container hasn't changed. We go all the way to the right and we take the maximum value, which is the 4. And then we go all the way to the left and we take the maximum value, which is 5. We take the lesser of these two, which is 4, and we subtract it from 3 to get 1, which we know is that there is 1 block of water above this 3. So here we've pretty much proven that this is going to be what we need to do in order to calculate the area of any element in the array. And how we can say this as a mathematical formula, or at least some kind of formula that we can use to keep track of, is that the current water for the current area that we're in is going to be equal to the minimum between the max left and the max right.
subtracting our current height. So that's what CH is. CH stands for current height. And just like that, we now have a general formula to calculate the water at any element in the array. So if we wanted the amount of water for the total number of elements in the array, then we just apply this formula to every single element, get the water, and add it to some total that we keep track of. By the end, when we've applied the formula to everything, then our total will be the final answer, which is going to be the total water inside of this array. So let's try it with our original diagram, which is this array. Just ignore this diagram for now. What we'll need to do is we'll need to keep track of some values. We'll also need a new pointer here. So let's initialize it on the left side. And what we'll need is a total water. So I'm just going to call it total. We also know that at any given point, we need to make sure that we have the maximum left value and the maximum right value as we discussed. So let's get a max L and a max R. What we'll do then is initialize the total at 0, and the max left and the max right will also be initialized at 0. So what we need to do here is we need to start at P, and we need to say, okay, are there any values to the left? No, there aren't, so max left stays at 0. What are the values to the right? Well, first we have a 1. 1 is greater than 0, so then we would switch this for 1. Then we move right again. 0 is less than 1, so then 1 stays. 2 is greater than 1, so 2 becomes the new max. Then we move right. 1 is less than 2, so we keep the 2. 0 is less than 2, so we keep the 2. 3 is greater than 2, so then we replace the 2. And then we move right. 1 is less than 3, we keep the 3. 0 is less than 3, we keep the 3. 1 is less than 3, 2 is less than 3, so we keep the 3 as our max R. We take the minimum according to our current water formula between the left and the right value, so 0, and then we subtract it from our current height, which is 0. 0 minus 0 gives us 0. Adding it to the total, total doesn't change, it stays at 0. Our P then moves forward, and we have to reinitialize our max R. So here P moves forward, max R is 0, and we do that calculation again. We go left. Is 0 greater than 0? It's not, doesn't matter anyways. 0 is our max left. Then we go right. 0 is not greater than 0, so it doesn't matter. 2 though is greater than 0, so we replace this 0 with a 2. 1 is not less than 2, so we keep the 2. 0 is not less than 2, we keep the 2. 3 is greater than 2, so we now increase this to 3. 1 is not greater than 3, so we keep the 3. 0's less than 3, we keep the 3. 1 is less than 3, 2 is less than 3. We do this calculation again. What's the minimum between our left and our right? Our minimum is 0. 0 minus our current P though is 1. 0 minus 1 actually gives us negative 1. But we don't want to add that to 0 because we can't have negative water. So then we just skip it if the total water above this P is ever less than 0. So our total stays at 0. Nothing happens. We reinitialize our values and we move our P over. So then we do our calculation again. Now when we go to our left, we see that 1 here is greater than our current max left. So then we update this value here to 1, but 0 is not greater than 1, so max left stays at 1. And then we go right. 2 is greater than 0, so then we update this max right value to 2. 1 is not greater than 2, we keep the 2. 0 is also not greater than 2, we keep the 2. 3 is greater than 2. And then we check the 1, 3 is larger. 0, 1, 2, all smaller than 3. 3 is still the max. Now that we have both of our maxes, we get the minimum between the two of them. So the min between 1 and 3 is 1. 1 minus our current height of 0 is 1. So we add that to our total, and total goes up by 1. Then we reinitialize our P as well as our initial values here. And now we just do this step for every single remaining value in the array. It's pretty tedious because Again, I'm just replying the same logic over and over again, but I think you get the idea of what we're trying to do. It's probably good at this point for you to do the rest of this array and do the same steps that I was repeating here, just so that you get an idea of what the logic and the rationale behind everything is. And then what I want you to do is I want you to try and take this idea and see if you can come up with a code for capturing what we've just come up with. I'm going to do it in the next lesson, but it's good to try yourself every time, because you'll find that by trying it yourself, you get a deeper understanding of what we're trying to do with this solution. So if you don't get a chance to try it, that's perfectly fine. We'll go through it together in the next video. Welcome back, everyone. In this lesson, we are going to turn that logical solution we came up with into a code solution. Now, I've also included the final code in a REPL in your resource folder already. The reason we did this is because from this point forward, some of these questions are going to be much more extensively written than what we're used to. And there's going to be more variables that we have to keep track of, so it might be better if you have access to the final code and it's easier for you to follow along. Now, I'm still going to be writing it all here for you just so that you know what the process is going to be like in the actual interview and what your thought process should be when you talk it out and come up with it. But the most important thing is that you're able to follow along with everything we're doing, and it might be better if you have a reference to the final code to see what it is that we're actually doing. So let's actually just jump right into it. You'll see here that I have not only our function that lets us calculate the water at a current point, but also I've initialized the function. So here heights is going to be the array that we pass into this function. So what we want to do is we want to initialize a total water that we're going to want to return. So this is just some value that's going to initialize at 0, and it's going to allow us to keep track of how much water we found so far. Now, what we also need is we need to initialize that pointer that goes across the array and calculates using this function the actual water amount. So what I'm going to say, though, is that let's say we get into this P here. What we'll need to also remember to do once we have that value is we need to figure out how we're going to scan left and how we're going to scan right. So let's actually just do the first P first, which we're going to do with a for loop, because we need to iterate through every element. So here I'm going to say let P equals 0, P less than heights.length, and then P++. So nothing here has changed. Now for the part where we scan all the way to the left and to the right, we're going to need 2 pointers. And each pointer is going to start at the current value of P. So let's say we've scanned all the way here to 1. Well, the P on the left and the P on the right are both going to start at this value and then go left and right respectively. And we also need some other variable that's going to keep track of the max value that we've seen so far. So it's going to go right, for example, and say, is 0 greater than the current value, which we're going to initialize also at 0? No, 0 is not greater than 0. Is 3 greater than 0? Yes. So we keep track of 3. Is 1 greater than 3? No. Is 0 greater than 3? No. Is 1 greater than 3? No. Is 2 greater than 3? No. 3 is our final max. So here we need 4 things then. We need that let left P, which is going to be equal to P. We need that right P, which is also going to be equal to P. And we need a max left, which is going to be equal to 0, and a max right, which is also going to be equal to 0. Now what we're going to do in order to actually iterate left and iterate right is use while loops. So here I'm just going to separate them into 2 different while loops because the logic is going to be a little different. Now here I'm going to say as long as left P is greater than or equal to 0, then I want to run this code block. And here inside I'm going to say that the max left using the current value at left P is going to get calculated. So it's going to be equal to math.max, which we remember is a math function that comes with JavaScript by default that lets us select the maximum value between what we pass to it. And I'm going to pass in what we currently have stored as max left, and then our current value at left p. Next, what we're going to do is we're going to decrement left p. So this is going to move left p one value to the left. And then as long as left p now is greater than 0, it's going to run this code inside of our while loop again. And that's all there is to it. Now what we're going to do is we are going to rewrite this, but for our right side. And here we're going to say, while our right p is less than heights.length then we're going to do the same thing. We're going to say max right is equal to math.max of max right and then our heights at right p. And right is now going to increment instead of decrement. So it's important to remember that because it's easy to just be copying your code over word for word and you'll notice that you'll get an error. So just remember, left p decrements because it's going to the left, right p increments because it's going to the right. So now that we have our max left and max right, we need to calculate and store the current water that we have so far. I'm going to say const current water is equal to our calculation. So we need the minimum value between the two maxes that we have. So let's say we need the max left and the max right. And then we're going to subtract our current heights at our current p value. So here what we're doing is we are just subtracting it from where this p currently is. And what we're also doing is we're now just using this function. That's all that code is doing. That's the current water calculation that we have right here. Now what we're going to do is we need to now see and figure out whether or not we want to add it to our total water. So here we can just use an if statement. We can say that if our current water is greater than or equal to 0, then I want to add that value to total water. So I'll say total water plus equals current water. And then with that, we just now need to close our code because we've done everything. We've gotten the current water. We've decided whether or not to add it to total water. There's nothing else we need to do with our current p value. So then we close off our for loop right here. And then what we're going to do is now we're going to return total water. Close off our function, and that's it. This is the code. So there's a bit more logic that we had to consider because of our left moving p and our right moving p, and then the final calculation. But it's actually quite simple once you look at it step by step. So what I want you to do is take this code, whether it's in the REPL I gave you or the one that we just wrote, and I want you to walk through using this original array to figure out if we actually end with our final answer, which is 8. So make sure that the code that we've just written works and you understand every step that's happening. Then this will take us to our next step, which is an exercise for you to test our code with our test cases. So we didn't come up with too many test cases, and most of them are those 0 test cases, so you'll run through the logic really quickly, but it's still a good exercise to know and understand every bit of the code that we've written and the logic of where everything flows. So do that, and then in the next video, we are going to tackle space and time complexity. So I'll see you in the next video. Welcome back, everyone. So here we're back in LeetCode and we're looking at the question trapping rainwater. This is number 42 on LeetCode. It's the exact question we've just done. Here I've just pasted our code solution into the editor right here, and we're going to submit and see how we do. So here we see our runtime is pretty bad, but our memory usage is pretty good. Our memory usage is above 90%, so that's pretty optimal. As for our runtime, we're in the bottom 10%, maybe even a little worse. And what we have to do is understand why. So let's go back to our code. What we want to do is identify the space and time complexity. So looking at the time complexity first, we can see here that we have our for loop, which iterates this p-value across the entire array one time. But when we iterate through, what are we doing to every element? Well, here we can see that we have two while loops, and these while loops iterate to the left and to the right of the array. And what they do is they actually touch every element on their respective sides. So our left pointer is iterating across the entire array from P all the way to the end. And then our right pointer is doing the same thing, iterating across every element all the way to the right. So if you were to add what the left P and the right P do, is they iterate across the entire array, meaning that they touch every single element one time. And we do this for every single iteration of our p-value due to our for loop running across the entire array. So what we see is that our time complexity is actually big O of n squared because it's n times n times. So that gives us a pretty bad time complexity. But what about our space complexity? Well, let's look at all the values that we're storing. When we look at total water here, we see that this value is pretty static in the sense that it's not a scaling storage. We also see that for our left P, right P, max left, max right, these are also non-scaling memory using variables, meaning that they only store some one value that might change, but it doesn't increase at all. Even if our inputs increase, neither of these values increase. We can say the same thing about our current water, which is a single calculation. And then total water updating, well, it's not an array, it's not an object. There's nothing here that's actually growing. So we add all of these together, and all of these are big O of 1. So even if that's the case, we can see that our space complexity is O of 1. So that is why our memory was so good on LeetCode, but then our time was so bad. So how can we optimize this solution? Well, let's go through those steps that we're already familiar with, that we've learned so far. If we look at time and we look at space complexity, we can try that technique where we see if there is a space complexity optimization that we can do, where we increase the amount of space we use, but that'll somehow bring down the time. But let's logically walk through our code and see if that even works. So here we can see that our total water is not something that can benefit from storing multiple values. It just stores the final answer, so there's no benefit here in changing how this is being stored. As for our for loop, we only have one, but the internal double while loop, is there any optimization here using any of these pointer values that can actually, say we were to trade this for something like an array or an object that scales, would that improve what we're able to finally get to? Well, not really either. Here we can see that the whole logic of this entire block is just to get the calculation for the water at that current point of P. So that's pretty much what all of this is doing as well, because this actually gets the amount of water above our single point. And then what we do is we finally add it to the total water. So this block of logic here is the only thing that we could think about whether or not we can optimize with our space. But there's nothing really here either that would make sense to make a scaling memory using data model. Instead, we got to think to that second array question we did, which is where we use the two pointers. Now let's just refresh ourselves on what it is that the two pointer technique did. The two pointer technique was where we initialized some pointer on the left and some pointer on the right, and then we conditionally tried to figure out what rationale was there for us to move one of these pointers inwards? And while we were moving them inwards, we were collecting some information that we had determined based on our equation. So here, we actually see that we have pretty much the exact same pieces in order to do so. In fact, we're already using 2 pointers right here. We have 2 pointers initialized and some rationale that decides whether or not they move. The only difference is that they move outwards rather than inwards. As for the actual formula, we also have a formula right here, and this formula calculates some value of water at a given point. So is there a way for us to combine these 2 things together so that instead of iterating pointers outwards, we iterate pointers inwards? Well, in order for us to do that, we have to think about what this rationale is doing, this code right here that we have written, and see if we can reverse engineer that into this 2-pointer structure. And to do that, we're going to have to think about the logic a little bit more clearly. Let me just clear up some of this code so that we have a better idea of what I'm talking about. So I've cleared away some of the code, and I've left us with our original test array, our current water calculation equation, and then the graph representation of the array. What we need to do is figure out how to implement 2 pointers and how to derive the logic required to properly transition from this current equation that applies to 1 pointer to 2. So to do that, we need to think about the 2 pointers. What are the main things we need to identify in order to properly implement this technique? Well, the first one is that let's say we were to instantiate a pointer on the left and a pointer on the right. We need to conditionally move these pointers. They don't just both move in at the same time. We have to think about some reasoning around why we would move one over another. Now, once we move a pointer, we're in some new iteration of our solution. So once we're in that iteration, meaning that we have access to both the values at the pointers, but also the values that we've seen with these pointers, what are we going to do in order to get closer to our final solution, which in this case is getting the accumulated water inside of this array? So we can actually get both of these answers by looking more closely at the equation that we have. But this equation applies to the 1 pointer. So let's just quickly review it so that we understand and see if we can break it apart and apply it to this 2-pointer technique. So we know that we iterate over some 1 pointer that scans across the array. At any given point in the array, this pointer then sends out a left pointer and a right pointer across the array in their respective direction in order to figure out what is the maximum values that form the relevant container. The most important thing to understand here is that the reason why we send out the pointers is to figure out the 2 walls that actually form the final container for us to get the water at this current p-value. So if we think about that, let's think about how we can apply that to our 2 pointers. So let's get rid of this first pointer here, and let's put our 2 pointers back. Let's say p left and p right. If we think about the rationale behind this, the only thing that we know if we have a pointer on the left and a pointer on the right is that we have most likely 2 walls. If we have the 2 walls available to us, what can we derive using these 2 pointers when they point at the 2 walls? Well, technically, we can't actually figure anything out because when our pointers point to the walls that we think must form a container, we know nothing about the information on the inside of these 2 walls. As you remember, the water content can be easily affected by any heights inside of the 2 walls that form a container. So imagine if we had, let's say we were using this wall here. Let's not pick this PL, let's pick this one so we can actually form some kind of wall. If we pick this value, so this one and this one, we don't actually know what's inside here. Until we scan into it with either of these pointers, we have no idea what the values of the heights in the middle are. I know we can see it here, but just imagine if we didn't know. Because our code definitely doesn't know until the pointers actually touch those values. So inside of here, it could be all very large values that form in such a way that using these 2 walls as containers, no amount of water can be held inside. That's a possibility. So that means that we can't actually use these 2 pointers in order to single-handedly figure out what the walls are for some container and the water inside. What we can keep track of, though, is the maximum values that they have respectively seen for each side. Meaning that we keep track of every value that PL has seen when it scans through, and we keep track of the maximum value that it's seen. That is doing the same thing here. But what we now need to decide is, what do we do with that max left and max right value that it's seen so far? So we know that we want to keep track of a max left and a max right using the 2 pointers, but how do we decide which one to move? Well, what we also know is that using these 2 pointers, we had a very similar question in our last max container water question, where the smaller of the 2 walls was the one that we would move because it was the only one that had a chance to actually impact the amount of water that was being stored. Well, it's actually going to be the same logic in this question, but it's going to go a step further. Now, the reason why we want to move the smaller value between the 2 pointers is because when we look at this equation, we know that this equation is calculating for some current value, which before we represented with some pointer P. Now that we don't have P anymore, we actually need one of these 2 pointer values that we have to take over that responsibility. The responsibility in this case is the one value that this equation gets applied to, which means that the pointer that we do pick is going to be the one whose water we calculate for. It's also going to be the one whose height we use as current height. Now, we need to join these 2 ideas together, because our logic dictates that we need to decide on the smaller value between the 2 to be the one that moves inwards, but we also need to use the smaller value as the actual current height for this calculation. And you'll see why once we actually step through the logic. So here, let me just move our pointer back. And what I'm also going to do is I'm going to initialize some max left value, which is going to start at 0, and some max right value that's also going to start at 0. And what we're going to do is we're going to logically walk through this. Between this 0 value and this 2 value, which one's smaller? Well, this 0 value is. So we know that this is the lesser value that we need to operate on. Now, what we also need to decide now is, do we try and calculate the amount of water for this value? Or do we try and update our max left? The reason why we need to consider this is because for this value to be the actual one we decide to calculate the water for, we need to have a max left value that is bigger than the current value. This value can only have water above it if some wall to the left of it is actually greater than it itself. This logic is not exact same for the right side, because the moment we knew that this right value, this far off right value, no matter where it is, it could be right here or it could be here. It doesn't matter. We know this value is bigger than this value. That means that we know that this wall can be a wall on the right side, but we don't know if there's a wall on the left side yet. And the only way we can figure out if there is a wall on the left side of this value to form a container that allows us to calculate any water here is if this current value is smaller than the max left value that we have. And here we see that 0 is not smaller than 0. So then nothing happens then. We can update max left equal to itself, which doesn't really change because max left is currently 0 anyways. All we do is we move the pointer over. So if that was confusing, we're going to go through more examples and hopefully that'll become more clear. So here we're going to see that now max left is at 1. Between the 1 and the 2, which one is smaller? Well, the 1 is smaller. So again, we know that this 1 is going to be the one that we operate on. Now we also have to decide, do we calculate water for this value? Well, using that same logic, we know that we have a right wall. This value we knew was larger than this value, so for sure this can be a wall. What we also now need to figure out though is there a left wall to this current value? Is the max left greater than our current value? It's not. So there's no possible way a wall could form on this side to give any water above this element. So what we do then is we update max left with the current value. So now there's a value here which is greater, which is 1. So we're going to update max left to 1, and then we're going to move our pointer over again. And now we once again ask, between our left value and our right value of 0 versus 2, which one's smaller? The left side, 0, is smaller. So now we know that this is the one we operate on. We decide, do we get current water or do we update max left? Well, we know now that we see that our max left is greater than our current value. So what we do then is we take max left and we subtract it from our current height. Now you might be wondering, why is it that we didn't do this check between a max left and a max right? Well, there's no need to, because we know that as long as we're moving the pointer that's smaller, we're always working with the lesser of the two values. The lesser max is always going to be on the side of the element that's moving. So here we know for sure that the right side is going to form a wall. In order for this point to be moving, any value that we've iterated through must be smaller than the other side. So now we know then that this side for sure is going to just take the max left value and then subtract it from this value, because whatever side we're operating on is going to be the return from this min statement anyways. So then we just take max left and we subtract it from the current height. So 1 minus 0 gives us 1. So then so far we have a water value of 1. So let's also keep track of a total water so far that we've seen. So far total is equal to 1. Then we move this value over. There's no need to update max left because max left was larger than our current value. There's no way max left would have been bigger with our current value anyways. So then we move this value over, and now we see, okay, between these two, which one is smaller? Well, they're actually equal. So here we have to consider, in a case where both values are equal, which side should we move? In this case, let's just keep moving the left side. You can actually decide to move the right side. It has no real impact on the solution. You just have to choose one of them. In this case, I'm going to choose to continue to move the left side. So we say, okay, so we're going to move this left side again. And we're going to ask, do we calculate the water or do we update the max left? So what we do, as we remember, is we compare the current max left versus our current value. Is the max left bigger than our current value? It's not. So then we need to update max left with our current value of 2. So I'm just going to update this to 2. And I'm going to move this left pointer over. Now that we're at this 1, we once again check and say, which between the two values is larger? 2 is larger, so then the blue left side is the one we operate on, which is a height of 1. And we have to decide, do we calculate the water or do we update the max left? In this case, we see that max left is larger than our current value. So we take max left and we minus the current height using that same logic where we know the right side wall is formed. So we don't even need to do this min between the two maxes. We know for sure this wall must be greater than what we have. The only wall that has an output is going to be the left max, which is this 2. So yes, they're both equal, but then our logic will still stand because it's still going to be this side of the wall that impacts the overall height of this water level that it could be. So we take this max left of 2, we subtract it from our current height of 1, we end up with 1, and we add it to our total. So total becomes 1 plus 1, which gives us 2. And then we move our pointer over, and we do that same logical step again between the left and the right side. Which one is smaller? Well, the left side is smaller, so we know that this side is the one we operate on. We take this value and then we say, okay, we get the max left. We want to calculate current water for it because it's smaller than max left. So it's max left minus the current value, which is 0. So 2 minus 0 gives us 2. 2 plus the current total of 2 gives us 4. Total updates to 4. And then we move our pointer again. And now the left pointer is at 3. So now we once again ask, between the left and the right side, which side is smaller? The right side is now smaller. So we now know the right side is the one that we need to move or operate on. So we ask, do we need to calculate the current water for the right side or do we want to update max right? Well, here we see that 2 is not only greater than max right, But we also know logically that there's no possible container that can be formed so that we can calculate water here because there's no elements on the right side. So then the right side moves over. So right side moves over here. Max right then gets updated to our value that we just saw, which is 2. And now we once again ask, okay, between this value and this value, which value is smaller? This value is smaller. So then we say, okay, do we want to calculate the water for this side, or do we want to update the max right? Well, we see that this value is smaller than max right, which means that we can form a container on any element on this right side, which in this case is the max right value, so this value. We know the left value must be greater than this value in order for this value to have moved over, so we don't even need to check the min between the max left and the max right. We know for sure that whatever element we're currently on the left side is greater than what's on our current element that we're looking at, which is this right value. So then it becomes the max right minus our current height of 1, which gives us 1. So we add that to our total, which now gives us 5. And then we move this value over again. And once again, we check between the left side and the right side. Which side is smaller? The right side is smaller. So the right side is the one we want to operate on. So if this is the one we want to operate on, then let's calculate whether or not we want to move and update max right, or if we want to calculate the current water. Well, we see that our current value is less than any max right value that we have. So then we know for sure that we can form some container. So then it becomes the max right minus our current height, 2 minus 0, which gives us 2, which then we add to our total, bringing us up to 7. That means that now we move our value once again over one more time, and we do one more check. Between our left value and our right value, which one is smaller? The right value is smaller, 1 is smaller than 3. So then we know that the right value is the one we operate on. So now we decide, do we want to update max right, or do we want to calculate current water? Well, the max right is currently larger than our current value, so there's no need to update max right. We need to calculate the current water. The current water then becomes 2 minus our current height, which gives us 1. 1 added to our total gives us 8. So now we know that the total value is 8, and we're done moving because now these two values have bumped up against each other. For this movie to move over, they're equal to the same value. We have our answer. We've calculated the total water in here. Now, I know this was a much longer video, but this is a very, very important video because here we see the difficulty of what the logical steps might take in order for us to go from a brute force to an optimal solution. This one required us to make a lot of deeper connections in understanding how we went from that one pointer example into this 2-pointer technique, where we broke apart our 1-pointer formula to still work for this 2-pointer one. It required us to understand deeply how these 2-pointers could help us form some container for values on the inside, but then figuring out which of these 2-pointers would actually be the value on the inside that we could calculate for was the challenge. So knowing that we could store some max left, max right value, but also that the pointers themselves had to in place take the role of what P did as the current value that we were looking at for this calculation is that big logical derivation that we have to make. So if this was challenging, please watch this video again because making those leaps is something that we do have to work on. It's the hardest thing in these technical interviews, in my opinion. But the more we practice, the more we'll be able to make these mental connections and the better our brain gets at taking what we have and then thinking deeply about what we currently do and seeing if we can apply it to other techniques that we have learned. So hopefully you can now understand how this works and try and figure out if you can code the solution yourself. This is definitely a great challenge to see if you truly understand all of the logical nuances of this solution. So maybe rewatch this video in order to refamiliarize yourself and see if you can write the code. I definitely endeavor you to make that challenge to code it yourself. If not, we're going to do it in the next video. And I'll see you in the next video. Hello everyone and welcome back. Hopefully you got a chance to try and code out that optimal solution. It was a great challenge because it really makes you look and think about how you break apart all those little complex pieces of logic that we came up with and then organize them in your code. If you never got the chance to do it, I highly suggest you still try it before watching this video. We're going to do a lot of these coding exercises throughout this course, so the more you practice, the more it will reward you in the end. If not, it's perfectly fine. We're going to do it ourselves right now. Here I've included the REPL for the code, just in case you want to use it as a reference or if you want to read through it first yourself, just to get an idea of how to do it before we walk through it together. But as always, this REPL is in your resources folder, so you can use it as a reference or you can just code along with me. Both are fine. Let's get to it. So here I have initialized the test array we have, as well as instantiated the function that is going to represent our final solution. Now, before we actually code it out though, let's just quickly write down the steps of logic that are important to guide us when we're writing this code. This is actually very crucial when your solutions are very complex and have a lot of conditions, because it's easy to get lost about where you are when you're coding it out. So let's just remove the necessity of us keeping that in our own minds by writing out some logical steps here. So the key things to remember is that the first thing we have to do is we have to identify between the left and the right pointer which one has the lesser value. So we're going to say identify pointer with lesser value. Once we have the pointer with the lesser value, we're going to ask, is this pointer value less than or equal to the max value on that side? Because depending on what that answer is, we're either going to update the max on that side or we're going to get the water and add it to the total. So this is a very important thing to identify as well in your logical steps, is we're going to say, is this pointer value lesser than or equal to the max on that side? Now, if this is true, then we are going to update the max on that side. If it's not the case, then we will get the water for that pointer and then we'll add it to the total. Once we've done this check, we need to move the pointer inwards. Now this will be for whichever respective side we're on. That we'll figure out in the code itself. And then the fourth thing is we're going to repeat this for the other pointer. So once we have this, what we're going to do now is use it as a guideline to guide what we're going to do. So the first thing we have to do is we have to initialize the values for our left pointer, left max, right max, and the total. So nothing new here. So we're going to say let left equal 0, right equal height dot length minus 1. Because as you remember, our indices start from 0, so the last value is going to be the length of the height minus 1. Then we need a left max, which is going to start at 0. A right max, which is also going to start at 0. And a total, that's also 0. Once we have these values, we now have to think about how are we going to write some block of code that will continue to run until these pointers bump up against each other. And while each one of these values might move, we also need to perform some logic inside of there. Well, this looks like the great place for a while loop. So let's do that. We're going to say while left is less than the right, meaning they haven't overlapped yet. we're going to perform some logic. And in here, the first thing we have to do is step number 1, which is identify the pointer with the lesser value. And we can do that with an if statement. So we'll say if height at left is less than or equal to height at right. There we go. So once we've figured that out, which one's the smaller one, we now have to move on to step 2. We have to check, is this pointer value lesser than or equal to the max on that side? So we're going to do that with another if statement. We're going to say if height at left is greater than or equal to the max left. If this is true, then what we're doing is we're updating max left, as we see right here. Yes, update max on that side. Now, we're also going to do the other one. No, then get water for the pointer value added to the total. So we'll do this all down here. So this first one inside of this if condition is just to update the max on this side. So we'll say max left is now equal to height at left. Then we have to say, if this is not true, then otherwise we are going to add and calculate total water. So here I'm just going to say total is plus equal to the max on this side minus our heights at this value. So in case you're wondering, the big thing here, as we remember, is that once we've decided that this side is the one to operate on from this check, remember in our logic that we know that the other side, the greater side in this case, is definitely a wall. That's why we only need the max left on the side that's smaller in order to figure out what the limiting wall is going to be to subtract from our current height in order to get how much water there actually is. So this is all we need. Once we finish with this else statement, we need to do our step 3, which is move this pointer inwards. So here what we're doing is we're moving the left pointer inwards. So we got to increment it. And then we need to move on to our last step here, which is repeat the code for the other pointer. So we got to just write the same logic, but for the right side. So this else statement is for this if block right here, just in case you get lost in all of these nested ifs. So here what we're going to do is we're just going to repeat the logic. And the first thing we got to decide is the current value at the right side now, assuming it's the lesser between the left and the right, is this value greater than or equal to the current max on the right? Because if it is, then we're going to update the max. Otherwise, then we'll add the water. Logic's the exact same. So here we'll just say if heights at right is greater than or equal to the max right, then we're going to say that max right is equal to heights at right. Otherwise, we're going to calculate for the water and add it to the total. It's going to be max right minus heights at right. Then we're going to move this pointer inwards. So right minus minus because it's on the right-hand side. And then in the end, we're just going to return our total. And this is our function. So by having these steps laid out at the top, we were very easily able to figure out what each of our code was going to do. This while loop is just going to iterate over the pointers until our pointers touch each other. This if condition decides whether or not we're going to operate on the left pointer or the right pointer by deciding on which one is smaller. This if condition then decides, okay, if we're operating on the left one because the left one is smaller, then we got to decide, are we going to update the max or are we going to calculate for water? And then this right statement is the exact same thing in the other side on this else block. And then finally, we return the total. So I know there's a lot of if conditions and it might seem a little confusing. If it does, just practice a couple times and it gets a lot easier. But here we have our optimal solution. So let's analyze the space-time complexity. Well, here we see that in our code, all we're doing is we are really only iterating over the array one time. We're touching every element once because this while condition will always yield some pointer moving inwards, whether it's the left moving towards the center or it's the right moving towards the center. And on every iteration, we're not really doing any additional calculation by touching other elements in the array. We only focus on the element we're currently operating on. So through this, we've managed to achieve a time complexity of O of n. Our space complexity stays the same. We have these 5 static values that store some one value in memory. Those values may change, but they don't scale. So we can say that our space is also still O of 1. And here we see we have a great solution. A time of O of n is phenomenal. A space of O of 1 is as good as it gets. And this is a great solution that we've come up with. It was really difficult to come to though, and I want everyone not to get discouraged. These questions are remarkably difficult for a reason. In fact, this was an array hard question. And the fact that you were able to now deeply understand the reasoning and the logic in how you would solve such a hard problem is a great accomplishment that you should really be proud of yourself for. This was definitely not easy, and when I was learning this, it was exceptionally difficult as well. It was not an easy thing to understand all of the framework and all of the mental steps required to get from even the question to a brute force solution, let alone the steps required from a brute force solution to an optimal solution. So I want everyone to be very proud of themselves, and I want you to understand that this is meant to be difficult. This is a challenging topic, and it's supposed to be hard. So I just want everyone to take a minute and be proud of themselves. Now, I want also everyone to take a step here and take all of our test cases and run through the code, just so you better understand what each line of code doing. Because every bit of code in this solution encapsulates some step of logic and some assumption that we made in order to get to the final solution. It's not enough to memorize this. You need to deeply understand how this solution works and then how you can code it yourself. And this is a great chance for you to rewrite the solution again, just to make sure that you understand all of the steps to do so. What I'm going to do now is just endeavor you to practice and practice. In fact, even re-practice this question if you have to get to the brute force, code the brute force, from the brute force, get to the optimal, code the optimal. It's only valuable to help you deeper understand all of the nuances of how you get from step to step to step. At the same time, I just want to say I'm proud of all of you, and I will see you in the next video. Welcome back, everyone. So here we're just going to test our new solution inside of LeetCode. We have pasted in the solution that we had just coded in the previous lesson, and now we're just going to submit. And we see that our solution's runtime is in the 99th percentile. Our memory usage is at 65th percentile, but we know that just by looking at what we're storing, we're not actually exceeding O of 1. So don't let these numbers totally throw you off. Sometimes you might submit and you'll see such a variance in the runtime. It can sometimes be 48 milliseconds, sometimes it might be 64 milliseconds, which would put us somewhere in the 50th, 60th percentile. But that's not to say that our solution is not running at the most optimal rate. So most of this is just more so to demonstrate to you that LeetCode will run our code against a bunch of test cases that they're running. In fact, if you go to the submission details, you will actually see that they will tell you how many test cases they ran our code against. And here we see we ran it against 315 of 315 test cases. So the main idea is just to make sure that our solution is comprehensive and covers all of these edge cases that they've thought of that perhaps we have not. although we do cover that step quite extensively in terms of coming up with the questions that give us our edge cases, which then drive our test cases. So generally speaking, LeetCode is just a good way to double check our solutions against not only test cases, but also just that our code is doing what we think it's doing. Additionally, one added thing to mention is that when we go back to this, your values and your percentages don't really matter that much. LeetCode is not the perfect solution when it comes to evaluating this. The key is always going to be your own ability to break down your solution in terms of space and time complexity and where it sits on the chart. So just always keep that in mind and don't let these percentages completely throw you off. With that, we're done with our array questions and we're going to move on to the next topic. Hello everyone and welcome back. So up until this point, we've worked exclusively with arrays and we've really been working on this two-pointer model in our last two questions. So the two-pointer technique is a great technique because it is such a good combination of understanding how logical and abstract thinking can be applied to this technical tool as long as you understand how to use it. Now, this tool is actually very useful throughout not just array questions, but other similar data models. And we're going to learn them, of course, throughout this course. This next data model that I want to focus on is actually called strings. And strings are pretty much the same thing as arrays, but there's a couple nuances to them and how they appear in technical interviews. But we're going to stick with arrays for a little bit longer, just to make sure that we have worked and built a solid foundation of our critical thinking model, but also that we truly deeply understand how these different technical techniques work with arrays because they will show up again in different data models. So with strings, when we learn about them in programming, we see them as a primitive type that is a sequence of alphanumeric characters, meaning that they can contain letters from A to Z, or they can contain numbers. When it contains letters, it doesn't necessarily have to be lowercase, it can also be uppercase. And strings can also contain all of these different elements combined together, as long as they exist between these two quotations. But another way that we can see strings is we can see strings as arrays. Just imagine that each character in the string is an element in the array. The reason why this similarity exists is because they are linear, right? They're these one-dimensional left to right data structures. And also the order of the characters in the string appear pretty much the same way as the order of elements in an array, and that order matters. So when you see string questions show up in a technical interview, it's pretty much just some variation of an array question. But the main difference here is that the string questions are going to have more to do with pattern matching, or they're going to make us use some kind of critical thinking about concepts that involve strings in the real world. The techniques that we apply with arrays and the critical thinking that we apply to arrays is going to be very similar with strings, but we're going to have to grow our thought process a little bit. And this next question is actually a great example of how this abstract thinking with strings might appear in questions. So the question asks, given two strings S and T, return if they equal when both are typed out. Any hash that appears in the string counts as a backspace. So if this question is confusing, let's just quickly run through an example of what this question is asking for. So let's imagine we were given this string CB hash D. Now, this question talks about typing it out. So imagine if we were to type this out from left to right. We would type C, B, and then when we hit the hash, what we're going to do is we're going to hit backspace. So we're going to delete the B, and then we're going to type D. So this is what that string CB hash D turns into, and that's that final version that actually counts and what we're going to want it to be. So imagine we were given two strings in this format, string S and string T. If we were to type this out, we know that the hash is going to delete the B with the S, leaving us with AC. And with string T, that hash beside the Z is going to delete the Z, and then we're going to end up with AC. So when we're given these two strings, we type them out per se into their final form as we see, and then we see that they do match, meaning that we're going to return true in this case, or false if they don't match. So now that we understand the question, let's verify the constraints. So this question is a little tricky, so there's actually quite a bit of constraints that we have to make sure we understand, more so having to do with this logic of the hash. So the first question we might ask is, what happens when two hashes appear beside each other? In this case, we delete the two values before the first hash, which is pretty much what you would expect if we were to hit backspace twice on a keyboard. So here, let's just take this string AB hash hash and the string that it finally becomes. So here, when we type the first A, we would get A. When we type the B, we get B. When we type the first hash, it would delete the B. And then when we type that second hash, it would therefore delete the A, leaving us with an empty string as the final form of this AB hash hash string. Once we know that, what happens to hashes when there is no character to remove? In this case, the interviewer might respond, it deletes nothing then, just like backspace would. So again, let's imagine we were given this string A hash hash B. If we were to type this out, we would first type out the A. The first hash deletes that A. The second hash would delete nothing because there's nothing in the string. Third hash is the same as the previous one. And then finally, when we type B, B becomes the last string. And this becomes the final string format of A hash hash B. Now, the other question we might ask is, are two empty strings equal to each other? In this case, yes, consider two empty strings as equal. So here we can see that if we were given an S of X hash, Y hash, Z hash, and a string of A hash, that with the first S hash, the X would get deleted by the first hash, the Y would get deleted by the second hash, and the Z deleted by the third hash, leaving us with an empty string as the final format. And with T, it's the same. The hash deletes the A, and we would also be left with an empty string. And in this case, both of these characters then match, and therefore we have a true to return from this question. Now, another important question to ask is, does case sensitivity matter? Because with strings, you can't just assume that a large uppercase A is the same as a lowercase a. And here we might see, yes, it does. Lowercase a does not equal uppercase A. Now, this is actually good for us because by default in almost all programming languages, comparison between characters, lowercase and uppercase, if they're the same character, often yields false. So when you compare a lowercase a to an uppercase A in JavaScript, you're going to get false. If this question asked us a different thing, and let's say when we asked this case sensitivity question, they say, no, it does not matter. Assume that a lowercase a and an uppercase A are equal. What we would normally do is just take any strings and lowercase the entire thing, because case sensitivity in that case doesn't matter. Whereas here it does, so we can just rely on the default behavior of our programming language. And with this, we have enough of our constraints so that we can move on to the next step, which is where we write out some test cases. And that's what we're going to do in the next lesson.
Welcome back, everyone. So now we have all of our constraints. Let's think of some test cases for this question. Now here I will show you all of those constraints that we came up with, and we can use them to guide some of the examples that we're going to come up with. So the first one we want to come up with is our best case test case. So let's just think of an example where it's very easy to get the right answer. We probably already saw it when we first explored the question, and we can do something simple like A, B, hash, Z. And then we can also have another string where it's A, Z, hash, Z. And what we know is that both strings are going to return AZ, and this should return us true. So we'll just write what we expect it to return as well. We also want to make sure that we account for a case where we do not get the right answer. So let's say we get a string where it's A, B, C, and then hashtag D. So we know that what this string will return is ABD. And then we can also put an answer here that seems correct, but is not actually correct. So let's say ACC, hashtag C. We know this should not be correct because this T string will return ACC. So this should give us false. What we also want to do is return a case where we have empty strings as the return. And we also want to make sure that by doing so, we're able to account for
multiple characters that might not be the same string, because all we really care about is the final output. Not all of these strings should be the equal length, just so that we account for it. So let's say we got x hash, y hash, z hash, which as we know will return an empty string. T here will just be a hash. And here we want to return true because both cases will give us an empty string. Another case we might want to account for is one where there's multiple hashes in a row. We want to make sure our solution doesn't do anything that we don't expect it to. So here let's assume that we get a string where it's A, hash, 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 and then B. And let's say T here is just B. No hashes, no need for it. Let's just say that this should return true. And then our last case that we want to account for is in terms of case sensitivity. So let's just make a variation of our best case test case that just simply accounts for uppercase and lowercase. We want to make sure that when it's uppercase versus lowercase, it doesn't return true. And if it's the same, then it does return true. So we already have a case here where we know that if everything's lowercase, then it'll return true. We just have to make sure that we have a false case where if, let's say, we have A, B, hashtag Z, and then let's say T here is lowercase a, B, hashtag Z, what this should return is false. And the reason for this is because this will return a Z like this, and this one will return a Z like this. So we see that the A's are not equal, and therefore we'll get false as the answer. So now that we have our test cases, let's think of how we can solve this logically. Now here we have our two strings in our best case test case. When we want to think about logically how we would solve this, the first thing to come to mind is probably to convert each of these into their final form, and then just simply compare them and see if they're equal. Logically, the most obvious way we would do that is if we were typing this ourselves. We know that what happens when we type is we go from left to right. And when we build out that string in our minds, what we're doing is we're saying, okay, if we're focusing on this string right here, A, B, hashtag Z, then we know that we start with A, and then we write the B. And now if we encounter this hashtag, what we're going to do is simply just remove the B, and then move on to the next character, which is the Z. And then once we hit the end, we have no more characters to add. We have our final string. We do the same for the string AZ hashtag Z. And we say, okay, first we have the A, then we have the Z. Now we encounter a hash, so we're going to get rid of this character, the last one. We're just going to backspace one time. And then we would just add our last character, which is another Z. And then we hit the end of the string and we've built our final string here. So now that we have our two strings, what we can do is just compare the characters in the respective positions of each string. Meaning, does the first element in this string match the first element in the second string? Well, it does. And then we check again, does this character match this character? It does. And we hit the end of both strings so we know we have the correct answer. If it were such the case that any of these characters didn't match, then we know that we have to return false because, of course, final strings are not equal. The other thing we might notice is that, let's say one string was longer than the other string. We don't even need to do this comparison. All we have to do is just compare the lengths of each string. And if output string of this side is bigger than the output string of this side or smaller, doesn't matter as long as the lengths are not equal, then you also know that the final output strings are not equal and you also return false. So this is pretty much all the rationale we need to capture. You might be wondering, what about multiple hashes that are accumulated in such a way that, let's say we were given this string where we had A, hashtag, hashtag, hashtag B. How do we account for a case where we don't do anything additional? Well, you just have to remember that when we're operating left to right, if there's nothing to remove, then you just simply move past it and don't do anything. The other thing to account for is that in the actual code, which I'm going to challenge you to write because the rationale and the logical steps here is quite simple. I want you to code it yourself first before you move on to watching me do it. But one quick hint I'm going to give you is that you don't need to use strings. You can easily use arrays here. So for example, instead of outputting a final string here, we simply output an array where we say, okay, the first character, not a hash, let's just push in A. The second character, not a hash, let's also put in Z. And then the third character, oh, this is a hash character. So what we do is we pop the last value out of our array. So we're just going to remove this Z, and then we move on to the next character, which is Z again, and we say, oh, okay, let's just push it in. Have we reached the end of our string? We have. Well, then we have our final output. We would do the same thing on this side, and this side, of course, would also return the same array as we saw earlier. So this would also be AZ, and then the check remains the same. We compare the lengths first to see if they're different, and if they are different, then we return false. Otherwise, what we do is simply check. We would say, okay, does element 0 in this array match element 0 in this array? It does. Does element 1 in this array match element 1 in this array? It does. Have we reached the end of the arrays? Yes. Well, then we return true. So that would be the solution. I want you to code it out yourself and see how you get with it. And in the next video, I'm going to show you how to do it as well. I'll see you in the next video. Welcome back, everyone. In this lesson, we are going to code out the logical solution we came up with in our previous lesson. As always, I have included the REPL file for you in your resources folder, and you can use it to follow along while we write out our solution. The reason why I've included this time is because for this solution, we're actually writing two functions. So I don't want you to get confused if when you open that REPL file and you see there's two blocks of code. The first function is actually a way for us to demonstrate that we are good developers. And the reason why we can do that is when we think about these two strings and what we need to do to them, we have to transform them into that final form before we actually compare them and give a response as to whether or not the final versions of these strings are actually equal. So as developers, we always want to practice that principle of being dry. Dry standing for don't repeat yourself. So here we know that the code that is going to modify this string is probably going to be the exact same code that's going to modify this string. So what we can do is write a generic function that we can pass in any string, and that string will check for these hashes and remove the respective characters before them, and then return an array that will represent the final characters that have not been removed. So here, let's just initialize some generic function called buildString. And it's going to be a function that receives one argument, which I'm going to call string. And what we want to do is we want to initialize the final output array. It's going to start off empty and we'll fill it accordingly. So I'm going to say const built array is equal to this empty array. Now what we want to do is we want to iterate over every character in the original string that gets passed in. So we're just going to use a for loop here. And we want to say for let p equals 0, p less than string.length, p plus plus. Now, because we are starting from the left and going right, what we're going to do, and the logic around this is we're going to say when p is at a character, if it's not equal to the hash, then push this character into the array. If it's equal to the hash, then we want to pop out the last element, because we know that as long as we see a hash, the last element that went in is the one that needs to be removed. We don't actually care what it is at this step once we have a hash. All we know is that we just want to pop the last element out of this final array. So here we're going to say if string at p does not equal the hash. So let's write our first case, which is where it's not equal to the hash. Then we want to push the right value into this built array. And we'll say dot push here for string at P. What we'll do then is otherwise in this else statement. So if string at P is equal to the hash, then we just want to say built array.pop. And if we remember, what pop does is it just pops out the last element in the array. So with that, we have written our for loop, and we just have to remember to return our built array. And that's all this function does. Very simple. And now we have to utilize it in our final solution. So let's write our final solution code. So here we're going to initialize our final solution function, and I'm going to call it backspace compare. And this is going to be a function that receives S and T, the two strings that are being passed into it. And what we need to do before we actually run any of our logic is we need to convert S and T into their final forms using that function we just wrote above. So I'm going to say const final S is equal to build string passing in our S string. And we want to do the same thing for final T. We're just going to call build string passing in the original T value. So with this, we now have the two arrays that represent the finished format of these strings that we can now compare. Now, if we remember, we can do one quick check first to see if the lengths of these two are even the same or not. Because if they're not the same, then we know for sure they can't be equal. Because one string is either longer or shorter than the other, they don't match. So we'll just say if final S dot length does not equal final T dot length, then we return false. And this is actually a very common technique that we can run when it comes to these return Boolean type questions. We want to make sure that we check for every condition that would cause us to return false. Because what this means is that if we have passed every one of these conditions that might cause our function to return false, then we know for sure that we have a match and we can return true. So that's why what we're doing here is we're just writing all of the logic that will compute whether or not these two strings don't match. If they do match, the way that we check for it is when they've passed all of this code that we've written, checking for a fail match. So let's continue with that. So we know if the two strings are the same, then we now need to iterate through both strings using one pointer because they have the same length. So we'll say else, if the lengths are the same, then we want to loop through it with one pointer, and we'll just use a for loop. Let p equal 0, p less than final s dot length. You can choose either one here because we know the lengths are the same anyways. P++. And then we say if final s at p does not equal final t at p, return false. And you see here again, this is the other condition we check to see if our case would fail. So the reason, again, why we do this is that now that we have both of these checks, which are the only ways that when we have these final strings, for this to not be true, meaning that for these two final strings to not be equal. It's either the lengths don't match or it's the values aren't the same. If these both pass, meaning that this if condition does not quantify, then we let it continue and it iterates through the rest of the two strings using this pointer. And then we just close it because we don't need anything else here for our checks. There's no other logic we have that would cause this to fail. So once we've run through this code, then now we can finally return true because we know that if our code has run through all of this logic, then it must be true. And this is our function. These two functions together form our final solution. So I know it looks like a lot more code, but it's actually much simpler because what each thing is doing is pretty straightforward. This function simply just builds the string very simply by iterating through this string, checking for values, and if one value equals a hash, then just remove the last value that we added. This final solution simply just gets those final values that we've just computed, and then we just check whether or not the values are equal. And that's really all this logic does. So the code and logic itself is definitely not as complex as what we came up with in the previous questions. Now is a good chance to check for any errors or typos or any spelling mistakes in your code. And also, once you've checked and your code seems right, it's a good time to run through all of our test cases inside of this code. So take the test cases we came up with, run through them, make sure you understand what every logic is doing, and make sure you also know what variables are being instantiated and how they're being changed. In the next video, we're going to evaluate the space and time complexity of this function, and then we're going to figure out if we can optimize the solution. So I will see you in the next video. So let's evaluate the space and time for the code of our brute force solution. So here when we look at our function, we know that we're getting two inputs, and each input does have some impact on the final output. But how that will be is inside of our code. But that gives us a hint that there's probably going to be two input variables that will impact our space and time complexity. But let's first look at time complexity. When we look at final S and final T being generated by build string, we have to look and also evaluate how this function impacts our time complexity. So looking at our build string function, it's a pretty simple function. It gets one single input, and what it does is it runs a for loop here over every element in the string. So that's the only part that might scale with the input, meaning that this has a O of n time. Now, as for the actual function s and t, because s and t might have variable lengths, meaning that the lengths of these two variables can be completely different, when they're passed into build string, yes, it's O of n as far as this function goes, but because each one can have a different length, it can be a different n value. N just represents the arbitrary length of the input for this function. So here we can say that the time complexity of running string s through our build string function is O of some variable that represents the size of s. So let's use a here. We have to do the same thing for t, and we'll say that this is O of b. So b here represents the size of the input of t. These just represent the lengths of these strings. So with that, we have O of a plus b so far, because we have to add these two values together. They aren't being multiplied on top of each other. When we look inside of the rest of our function, we see that this code here is just one simple check. So this is O of 1. This has no impact on making our time complexity any larger than what we have, so we can ignore it. When we look at this for loop, we have to think about the worst case scenario. Let's assume that neither s nor t had any hashes in them, which means that the built string that gets returned from our function is the same size as the original variables. And that's kind of what a and b represent. They represent the worst case scenario that these strings have to be iterated through their entire size, so they're these exact same input size as what they came in as. We can imagine a case where if both s and t were as large as they were when they came in, then this for loop is just going to loop over the largest between a or b. But this means that the worst case of this for loop is either O of a or O of b. So now if we were to combine this statement here with the two time complexity statements we have above, we end up with either a time complexity of O of 2a plus b or O of a plus 2b. Either case, we would drop the constant 2's and we yield the exact same O of a plus b. So that's our time complexity. What about our space complexity? Well, when we look at space complexity, we look at our build string first, and inside we see that we could be building some output array that, in the worst case, might be the size of the string itself, assuming that there's no hash characters. So even in that case, what ends up happening is that our space and time complexity is the exact same here. It's still O of A and O of B, assuming A and B are the input sizes of S and T respectively. So then when we look at the rest of our code, we don't generate any more variables. So then our final space complexity is also O of A plus B. So time is that one, space is that one. So now that we know the space and time complexity, let's run this solution inside of LeetCode. So here we are inside of LeetCode looking at question 844 backspace compare. This is the question. Here I have pasted in the code of our brute force solution. So let's submit and see how we do. Here we see that our runtime is around 48 milliseconds, which is faster than 97% of solutions. Our memory usage, though, is 66.67%. So we know that in terms of the time complexity we want to achieve, we've achieved what must be around the fastest possible solution. As far as memory usage, though, we could do a bit of improvement here. This then brings us to our next step, which is, can we optimize our solution? So we know that it must be the space complexity, and our current space is O of A plus B, A and B being the sizes of the two input strings respectively. So we need to figure out if we can bring down this space complexity. And I'm going to cover my solution in the next lesson, but I challenge you to try and solve this yourself because we know that what we're trying to do with our solution is bring down the space. You might actually come up with your own solution that's different from mine, and it might be just as good, if not better than my solution. And that's incredible because that means that you've really managed to work on this logical and abstract thinking that we keep talking about in this course. I'm going to give you 3 hints though, and those hints are going to revolve around my solution. So the first hint is that I want you to utilize the original strings. In our current solution, we take the strings and we build out a new array which we use to compare. But I don't want you to do that, at least not in my solution that I'm going to teach in the next lesson. I want you to utilize the original strings that come in, and that way you don't actually have to create a new memory-consuming data structure. So that's the first hint. The second hint is to use the two-pointer technique that we've learned extensively in our previous array questions. Remember, with the two-pointer technique, the main logic around it is just deciding when to move the pointers and what to do on each iteration. You can actually move both pointers at the same time, or you can move them independently. The idea is just you have to figure out the logic around it. And this leads us to our third hint, which is start from the end of the strings. So far, all we've done is start from the beginning of the string. I want you to start from both the ends of the strings as far as the actual final solution goes. What that will actually look like is that you're going to imagine you initialize the 2 pointers on the ends of the strings, and instead of going left to right, you go right to left. And you want to iterate over that somehow to end up with your final solution. So those are my 3 hints, and good luck everyone. This is a great challenge. I'll see you in the next video where I show you how to do it. Welcome back, everyone. Hopefully everyone got a chance to try their hand at coming up with an optimal solution. Now remember, with a lot of these technical interview questions, there are many ways that you can come up with a solution, and they might all have the same space and time complexity, meaning there exists multiple versions and variations of an optimal solution. In this lesson, I'm going to show you what I would do in order to come up with an optimal solution working off of our brute force, but also adding some of that logical abstract thinking that we've been talking about this course thus far. So when we looked at our brute force solution, we knew that where we needed to optimize was in our space complexity. When we had it, we were coming up with a O of A plus B space complexity because A represented the size of our string S and B represented the size of our string T. We would then take these respective strings and run them through some code that would give us back some kind of scaling data structure, which in this case was an array, that would hold the final format of the string after transformation. Transformation being which characters do we remove if there are hashes in the string. So here we know that ABC hashtag D becomes ABD, so we returned ABD. And similarly with string T, it's the same idea. It becomes ABD here. So we had two of these arrays that would both hold whatever the final output of these strings were. We would then compare the characters inside of these arrays in the exact same position in the arrays to see if we had a match. If we did, we would return true. If we didn't, we would return false. But the key here is to realize that the question really is only asking us to return true or false. We are choosing to create these data structures, these scaling in-memory data structures, in order to help us get to this final answer. But the question itself does not require us to even create these data structures in the first place. So that is our first hint, that if we know for certain there's no real need for these other than the fact that our solution depends upon it, our brute force solution in this case, then maybe there's a way for us to remove this. Because if the question required us to return these arrays instead, then there's no way around it. You have to create them in your code because the question expects you to create them as part of the answer. But our question is simply asking us to return true or false depending on the condition if these two strings, when typed out, have the same output. So that might be a way to bring down the memory, is to remove these and find some other way to figure out whether or not it's true or false that these two strings are equal when transformed. So we'll talk about that next. But first, let's just get rid of these arrays here. So knowing what we know now, perhaps what we can think about is some of those hints I gave you, which is about using the two-pointer structure. If there is a way where we can think about, if we had 2 pointers, one pointer pointing to an element in S and one pointer pointing to an element in T, and then just comparing those letters. Because if you were to break this problem down into smaller problems, when we matched the characters in the arrays, we were matching them character by the position that they were in. So similarly, we can move that out and just use the strings that we are given as the actual structure that we should compare against. Because we're really just comparing these strings anyways. And we can compare whether or not the characters are equal in some position P. In this case, maybe P1 and P2, so I'm more clear here. Is the character at SP1 the same as the character in TP2? Now, if we go from left to right, this becomes problematic because if we were to say this character at P1 here and this character at P2 right here in the same place, let's say right here. If we were to compare these two, we know that this would not be true just upon evaluation. But then if we were to look out a little bit and think about the strings themselves, we know that this hash is going to delete this C, and we know that these two hashes are going to delete these two values. So this hash is actually going to delete this Z anyways. So just by comparing these letters, this is not going to work because our backspace deletes backwards and our pointer moving left to right is always going to be 1 or 2 steps behind. In fact, it could be multiple steps behind depending on how far down multiple hashes might be. Because a row of hashes is going to delete a row of respective characters. But if we go from left to right, we won't see those hashtags until much later. So we know that our logic cannot work this way. Instead, what we can do is, knowing that the hashes delete from right to left, then we just move our pointers and start them from the right instead of starting them from the left. So here we can initialize P1 at the end of string S and P2 at the end of string T. Logically speaking here, because we're starting at the very end, meaning the right side, we know that there are no characters after this character that we're currently pointed on, because it's the last character, which means that if this character is not a hash, then this character ends up in the final string. This D is the last character right here in our final string. Whatever this character is means that this character must be in the final string. This then means that we don't have to worry about this character being deleted. So we can compare this character at P1 with this character at P2 because both of these characters must be in the final string format that gets transformed from whatever the string is. So that means that if the string at P1 and the string character at P2 match, then we know we can move our pointers forward to check the rest of the strings respectively. If it does not match, then we know that we got to return false because these characters, if they don't match, means that the character in the final strings don't match, which means that we have our answer about this being false. If they match, what we're going to do is we're just going to move the characters one forward, or the pointers. So in this case, P2 is going to move here, and P1 is going to move here. Now, what we do when we encounter a hashtag is we think, okay, there's no point in us comparing these hashes because what these hashes do is they delete a character. So what we can then say is that here, I want to move my pointer over by 2. Because what we need to do is we need to move over to the C and then over again to the B because the C is going to get deleted, which means that the logic and rationale here is that I want to remove these two characters logically speaking, without actually modifying anything in memory. So the easiest way to do that is just to move this pointer over by 2. But we're actually not just going to skip P1 all the way over to B, which is 2 places over, because what we need to see is that if this character here is a hash or if it's a character, as we see in our string T. So I know that here I just moved it over, but let's just evaluate why we got to do it step by step. So here we know that we have P2 pointing to some hash value. We can then say that P2 needs to move left over by 2 characters. So we're going to move it over once first. So P2 is going to move over and consume a step. This means that P2 moves over by 1, and we have one more step to make. From here, we then evaluate, is this character a hash or is it a letter or some kind of string character? In this case, it's another hash, which means that this has to delete another value to the left. We do not simply delete this character with this first hash. We kind of group these two values together in a way to see how many characters to the left are there actually to delete. So because we have another hash, we have another 2 characters to move over to. So we have to add 2 to the number of steps we have yet to make. And here we then move P2 over again because there's 3 steps to be taken. So we move it over by 1. And then this 3 goes down to 2. So then we ask, is the character at P2 a hash? It's not. So we don't need to add any values to the number of steps we have to take. We can now just move it over by 1 and decrement the count. So now we ask again, is the character at P2 a hash? It's not. So once again, we see how many steps we have left. We have 1 more. So we decrement it by 1, and then we move P2 over. And now we see we have no more steps to take, so we've accounted for all the hashes from when we first saw our first hash. And now P2 and P1 are both in their final places as far as the strings that might have had any hashes before it. So we know for sure then that wherever P2 is and wherever P1 is at a character that will end up in the final string. So here we see that B and B are in, and we can say then, okay, P1 and P2, do these characters match? They do. So then we can now move P1 and P2 over once again. We check, do these final characters match? They do. So we know then for sure we've explored the full string on both sides, and we can say that conclusively we know that this should return true. The final format of these 2 strings do match. And that is the technique for using 2 pointers as well as leveraging the strings that were input to us as a way to evaluate whether or not we have a matching string after the final transformation. The key to the logic here was realizing that these hashes would be moving a character to the left. So in order to account for it with pointers then, we have to account for it by starting from the right of each string. So that's really the big logical jump that we had to make while using this 2-pointer structure. And we see now that with this optimal solution, we aren't actually storing anything in memory. So chances are we've managed to bring down our actual memory usage. So with that, I want you to try and code out the solution that we came up with. I'm going to show you in the next lesson, but I wanted you to try it first. I'll see you in the next lesson. Before we code out our optimal solution, I want to remind you that we have the final code inside of our resources folder in some REPL file. If you check your resources folder and open it up, you can always use it as a reference while we're writing this out. Diving into it, here I've just initialized the function and I've placed the 2 strings we want as reference. The first step to our optimal solution is initializing these 2 pointer values that point to the last index of the character in the string. So here we can say let p1 equal s.length minus 1, because length minus 1 is the index of that last character. We're going to do the same thing for t, and I'm going to call this p2, and it's going to be equals to t.length minus 1. Now, what we want to do is we want to write some kind of conditional loop that will do the evaluation and decide on what to do with P1 or P2. The difference here is that we kind of need code to govern each one's responsibility, even though it's similar. And you'll see what we mean once we actually write it. But one big thing to remember is that we want to check for false cases first, because we might know with this character whether or not this function needs to return false. Because if these characters don't match, then we know we return false. But if they do match, we don't know that we can return true. We have to check the rest of the string first. So that's why we're going to do a condition check for false when we compare these characters. So what we're going to say is that while P1 is greater than or equal to 0. So in this case, we want to make sure that P1 is within the indices of these strings. If it's past, then technically P1 is done being calculated for. But we also want to say or P2 is greater than or equal to 0 as well, because we want to make sure that we're counting for both these cases. If there's a chance that one of these strings is significantly longer than the first one, even after both these strings are transformed, we want to make sure that when P2 advances, let's say P2 is the longer string. If P2 advances and P1 is already at the end, then what's going to happen is that it should be some kind of comparison that returns false, because P1 is done. There's no more characters. And if T still has characters, then of course we return false. So by wrapping this while condition here, we can see how that will happen a little later as well. But this is just the condition of how we're going to satisfy to make sure that these 2 strings are also equal, even in their final forms. So let's just say that here we're doing this while check, and what we want to do now is we want to write a condition that checks whether or not P1 or P2 are pointing to hashes. So here we'll say if s at P1 is equal to a hash, or t at P2 is also equal to a hash. What we're going to do is just say for this if condition, if any of these characters point to a hash, we don't want to compare the characters yet. Because if any of these compare to a hash, we have to move these pointers. We don't want to compare unless we know for certain P1 and P2 are pointing at characters that will definitely be in the final versions of the strings. So by writing this if check, we then step in and write our code for both P1 and P2. And here we'll say if s at P1 is equal to a hash. So this is the code to govern this first P1. We will say let back count equals 2. Now, back count is going to be how we decide how many units or how many indices we need to move P1 to the left by. Now that we've initialized back count, we want to say while back count is greater than 0. Then P1 is going to minus minus. So we're going to shift P1 over. But remember, we still have to check whether or not this character that P1 is pointing to is a hash. Before we actually check that, we do have to decrement back count as well, because we have moved P1 by 1 already. So we have consumed one of these back counts. So here we can just say back count minus minus. Now is that check to see if the new value that P1 is pointed to is also a hash. So we say if s at P1 is equal to a hash, then back count is equal to back count plus 2. And then we close off our while loop. Now, if you're curious as to why here we just do this check and then inside this block we do this check again, it's because when we realize that we're pointing to a hash, we need to move this pointer until we're technically resolved with moving the pointer due to how many hashes there might be in the string. Only if they're within the amount of pointers that we're moving as far as the string is concerned. So here we can see with this string, when P2 moves over to the first hash right here, there is one more hash to account for. So we can't just move that pointer to where the final position will be. Let's say we do account for this one. From this point on, we need to get to this B. But what happens if this Z or this value right here, instead of being a B, either of these were hashes? Then we technically need to still keep moving our pointer over until we're done removing characters. And that's what this block of code here represents. So that's why we do it in this way. We want to do this all in one move or one block of logic when we first encounter our first hash. So this is pretty much the logic for this block of P1. And now what we want to do is we want to do it for P2 as well. And the code is pretty much going to be the exact same. So here we just say if T at P2 equals a hash, then we're going to do the exact same thing. We're going to initialize a back count variable here. And it's going to be equal to 2. And we'll say while back count is greater than 0. Then we want to decrement P2. So we want to shift it over by 1. We want to also decrement back count. And then we do that same thing. We check if the value at T at P2 is equal to hashes. Because if it is, then we are going to increase back count here. By 2. We close off these functions. And this is the logic that will decide what happens if we're looking at a hash. When we're finally done moving our pointers due to having encountered any number of these hashes that are grouped together, we then consider what happens now if it is a regular character, which means that we're at the else section of this if statement right here. So we need to write the else right here. And here we'll say else. We have a character. So this is where we evaluate. Are these characters equal to each other at P1 and P2? Because we know we've moved our pointers to the right position where the characters now must end up in the final string. So we say if S at P1 does not equal T at P2, then we return false because we know for sure the two strings are not the same at this character. If they are the same, then we have to check for the remainder of P1 and P2. So P1 is going to remove or move over by 1. P2 is also going to move over by 1. And then our code is going to run through this entire loop again and check if there's a character or it's something else like a hash, and then it has to do all of that logic above again. And once we're done evaluating this, we know that if all of these conditions have passed, then we've reached the very start of our string. We've compared those characters. P1 and P2 are now no longer in positions in this string because they've moved all the way over, compared the characters, moved all the way over, compared the characters. We're done comparing. These strings must therefore match, and then we return true. And now we have our final code. It's always good now to just double check for any typos. We want to make sure that we have closed all of our braces as well, because when we have so many nested conditions and all of these while loops, it's very easy to miss a brace or have added an extra brace. So just double check through your code to see if you've misnamed any variables when you were referencing them or you have any additional braces. I'm going to do the same. So here, let's just see that we have to keep track of the fact that we have these two braces on this while and this if to check for. But I'm going to check this block right here. So this if matches this brace, this while matches this brace, this if right here matches this brace. So this block of code is fine. Then this if matches this brace, this while matches this one, this if also matches this one. So this code is also good in terms of braces. This else matches and starts a new bracket, so that if condition that was up here is what that matches for. Inside, we see that this if matches here, this else matches here, this brace matches this else, but now we suddenly return true. I am indeed missing a bracket for this while loop here. So I'm just going to add it, and this is my mistake. So I'm just going to brace one more closing brace, and then we're going to return true. And then close off our original function. And here we see the importance of double checking for any errors. In an interview, if you make a mistake, that's perfectly fine. You just want to make sure that you check afterwards and show diligence on making sure your code is clean and correct. So with this, we have coded our final solution. In the next video, I'm going to walk through the space and time complexity of this function as well as the LeetCode, just because this video is getting a little long. But I do want you to double check and see for yourself if you know what the space and time of this code is. It's always good to practice these exercises for yourself, but I'm going to do it in the next lesson. So I'll see you in the next lesson. So in the last lesson, we coded out our optimal solution, but what's the space and time? If we start with time, when we look at this code, we are initializing 2 pointers here. How often do these 2 pointers move though? So here when we look at the actual code for our while loop, we see that inside of either condition, whether or not P1 or P2 is pointing to a hash, inside of here we see that if it's pointing to a hash, we do move P1. If it's not pointing to a hash, so we hit this else block, we're also going to move P1 or P2. So both our pointers always move in every iteration of our while loop. They can only move in one direction as well. They're always being subtracted. So this means that they are definitely always moving to the left. Sometimes they move multiple times to the left, as we see inside of our if condition here, where if our while count is significant, then we actually do move P2 multiple times. But regardless, what ends up happening is we touch every single element only once. So from this, we can tell that our time complexity is O of A plus B. A and B here represent the total size of each string S and string T respectively. So our time complexity is still O of A plus B. So this is the same. What about our memory? We were trying to optimize our memory. So let's evaluate our space complexity. And here we see that we initialize P1 and P2 as these singular values. They're no longer scaling data structures like objects or arrays. And all they do is they just advance. They simply change the value and move, but they're always this singular value. Looking through the rest of our code, we see that we're not storing any other scaling data structure that would consume increasing memory based on input size. So we can see now that we have optimized our memory, so our space complexity is now O of 1. So we have really optimized our solution. Now let's just jump into LeetCode and see how our solution compares. So here we are back in LeetCode with question 844. I've pasted in our optimal solution, so let's just submit it and see how we do. And here we see that our runtime and memory usage is actually really good. We hit 100% on both of these fields. Now, I did mention that these values can change quite frequently. As long as you submit multiple times, you'll see these numbers bounce around constantly. But the fact that one of our submissions hit 100% for both tells us that we're about as optimal as we can get with this solution. Of course, evaluating space and time in big O notation yourself is the best gauge to see whether or not you can optimize any further. But this at least helps us see that our solution is about as optimal as it can be that we concluded when we did our own space-time evaluations. So now that we see this, let's just quickly reflect upon this string question. This string question has really shown us that as far as strings and arrays goes, they are very similar. The only thing harkens back to that thing I mentioned early on when I introduced this question, which is that with string questions, sometimes you have to abstract it to some real-life example of strings that might not occur for arrays. In this question in particular, it was the idea of backspacing. Yes, you can always delete elements with arrays, but you really only see that very frequently when we're typing, because we type out strings. So it's easy for us to think about what it's like to backspace and remove a character. In this case, we had to take that logic and then apply it to a technical technique that we've already explored with arrays, which is the two-pointer technique. In this case, we had to unravel what this question was asking us about backspacing. So where do we place our pointers? The idea that each of our pointers went to each of these two strings, the fact that we had to conditionally decide what we were going to do on each iteration of these pointers, and then how many units are we even going to move with these pointers? There's all these little steps that we had to consider just for this optimal solution. And this is going to be a pattern you're going to see come up a lot when you do this course. Even just thinking about our two-pointer technique usage in the 3 questions we've just done, not just the string one, but the last 2 questions we did, we notice that it's very different between each question. Yes, the idea about figuring out where the pointers start, which direction they move in, how they move is similar, but how they actually end up being implemented when we actually code our solution drastically differs. And that's going to be the most important thing that we'll notice through the rest of this course. Of course, I'm going to teach you all of the different technical techniques and tools that you have available to you when coding, but how you actually end up using those is going to be the main thing that we are learning, because the core to this course is that we're understanding this logical framework of how to break down problems, abstractify the right things, and then apply them into the context of all of these little steps that we have to do to finally build towards an optimal solution. That is the most important thing to learn from this course. So hopefully you saw through this question kind of the big general direction that we're moving with this course, which is to learn this logical breakdown process of these problems and then working on our abstract and critical thinking. So with that, let's move on to our next question. Welcome back, everyone.
So we're moving on to our second string question, and this type of question is actually very common as far as string questions go. There's always a bit of variance that I'll explain later once we take a better look at what the question is and what are the nuances to it. But this question is also going to teach us a new or slightly more advanced version of the two-pointer technique that we've learned called the sliding window. So sliding window, we'll talk about once we actually look at the optimal solution, but let's just explore this question first. So the question asks, given a string, find the length of the longest substring without repeating characters. So what does this mean? Imagine that we're given this string, ABC, CABB. When we look inside of this string, can we find a smaller string where it's the longest one that all the characters are unique inside of it? Well, there's actually two. The first one is the ABC. ABC forms a length of 3, and then the next character of C, of course, repeats the C. So 3 here is the longest we found with this first substring. Then if we look a little further, we also see that there's CAB, which is 3 again. And this, even though there are two substrings of length 3, means that the longest substring we can form inside with unique characters is 3. So even though there's 2, the longest substring we could form is 3. So hopefully that makes sense. I know that there's a little bit of nuance here between how many substrings there are, but even if there's multiple and they all have the same length, just return that length. Now that we know what the question is expecting from us, let's move on to the next step, which is to verify the constraints. Now here, there's actually a very interesting constraint that we have to make sure that we understand early on when we're doing string questions. And this is always a good question to ask. The question is the string contiguous? Now, I know that contiguous term, you might not be familiar with it, but this is a term that actually pops up quite frequently in string and technical interview questions, and I'm going to break down what it means. But first here, the right answer to this question that the interviewer might say is that, yes, look for a substring and not a subsequence. I'm also going to tell you what a subsequence means. So when we look at a substring versus a subsequence, remember that we are trying to also right now define this term of contiguous. Contiguous just means that the characters that show up are sequential and do not have any breaks in between them. So imagine the string A, B, C, B, B, D. If we were to split this into two examples, the same string, and we want to look at a substring variation versus a subsequence variation. In a substring, the characters do not have any breaks between them, meaning that A, B, and C as a substring within this string is sequential, side by side, and therefore contiguous. Therefore, this means that a subsequence is the opposite of this, that you can have breaks between the characters. And here we see a subsequence could be A, B, C, skip, skip, and then the D, meaning that it skipped the two B's in between. And this forms a subsequence of A, B, C, D. So this example of a subsequence is one where it is not contiguous. So this is an important thing to remember. We'll definitely see more examples later on throughout the course, but this is an important thing just to remember, and it's always good to ask. When you see them wanting you to find a substring or match a pattern of a substring inside of a string, just double check to see if they mean a contiguous substring or do they mean a subsequence. With any string question, it's also always good to ask, does case sensitivity matter? It's just good to always double check. In our case, we're going to say no, just assume all the characters in the string are going to be lowercase. So with this, we have enough so that we can move on to our next step, which is to come up with some of our test cases. So let's move to the tablet and do that next. So the very first test case we should come up with is our best case test case. And here we're just going to use that same string that we originally saw when we introduced the question. So A, B, C, C, A, B, B. And here, if you remember, there are two strings inside that have a length of 3. There is the ABC and the CAB. Either way, the correct answer here is 3.
Another example that we want to see maybe is one where there are multiples of the exact same character, and the longest substring we can form is 1. And then finally, perhaps what we want to see is just an empty string as our null case, and here we just want to return 0. There are also multiple ways that we can come up with other examples to make sure we cover, such as what happens when we have overlapping substrings. So for example, we can come up with a case where we have, say, A, B, C, B, D, A. So here we see that there is the substring ABC, but there's also a substring CBDA using the C from the previous substring. So we want to make sure that when we come up with our solution, we account for any overlaps that might occur between multiple substrings. So with this in mind, we know that the correct answer then is 4, because that CBDA is the longest substring we could form. Now that we know our test cases, I want to challenge you to come up with your own brute force logical solution. You can even try and code it yourself as well. The idea is just that you want to practice now that you have a good idea of how these problems and how our steps work. So just challenge yourself to try it out, because once you practice it and you want to hit those walls and maybe you can't figure it out, or even if you can figure it out, it's all good practice in this process of us preparing. So I'm going to tackle this in the next lesson. So I'll see you in the next lesson. Welcome back, everyone. So let's figure out a brute force solution for the string that we have. What we want to do is we will probably want to figure out a logical solution that just works and not worry about optimizations until later. We want to just get out a solution as fast as possible. And looking at the question, the most obvious way that we can do this, where we figure out what's the longest substring we can form without repeating characters, is to generate every possible substring without repeating characters, and then just take the one that's the longest. The easiest way that we can do that is just start from the left and then build out a substring until we see a character we've seen before, take the length, and then just keep track of whichever one we've seen that's the longest thus far. We've actually done an array question that was very similar to this, except this time we're just changing the logic a little bit about that fact that we need to find substrings without repeating characters. So let's just keep track of the longest value that we have seen thus far. We can initialize it at 0. And then we just need to keep track of any characters that we've seen inside of this process as we're building strings. So we'll start with the first character A, and we'll say, have we seen A before yet? We haven't. We haven't actually seen any characters. So we'll just add A in. We will say the longest substring that we've seen thus far then is now 1. So let's just replace this 0 with the 1. And then we'll advance and add the next character to our string. So now we're at AB. Have we seen B before? We haven't. So we can add B in. And now what we'll say is that the longest thing we've got here is 2. Is this longer than our longest substring that we've seen? It is. 2 is greater. So we can replace this and we can move on. We'll then add C to this substring. And we'll say, have we seen C before? We haven't. So let's add it in. And now we have a length of 3. Is 3 longer than the longest value we've seen thus far? It is. So we'll update our longest again to 3. And now we then advance again and we add the B. Now we check, have we seen B before? We have. So then we know that we have to restart. So here, I'm just going to clear this out. I'm going to clear our cache. And then we're going to advance and start from B now. And now starting from B again, we check, is B inside of our map? It's not. So we add B in, and then we check and say, what's the longest string here? It's 1. Is 1 longer than the longest value that we've seen thus far? No, 3 is the longest. So then we just don't update longest and we move on. We then add the C and we say, have we seen C before? We haven't. So now we do this calculation again. What's the longest string we've seen thus far? It's 2. Is this longer than any of the longest substrings that we've calculated? No, 2 is smaller than 3. So then we don't do anything with it and we move on. And we add the next character and we say, have we seen B before in this new substring? We have. substring then must be over, and then we reinitialize this map that we're using to keep track of the character we've seen, and we advance to C. And now we say, C, have we seen it? We haven't. So now we add the C. We have a length of 1. Is 1 longer than our longest value that we've been accumulating? No, 1 is less than 3. So then we increment a character. And then we say, is this B? Have we seen it before? We haven't. So we add it. We add to our count. We now have 2. Is 2 longer than the longest value of 3? It's not, so then we don't need it. And then we add the D, and we say, have we seen this D before? We haven't. So now we have a new calculation of 3 here. Is 3 longer than our longest? It's not longer, it's the same. So either way, we don't update. And then we add another character, and we check, have we seen the C before? We have. So then we know we have to reset, and then we simply recalculate starting from this new B. So we see, have we seen the B? We haven't. We add the B. We have a length of 1. 1 is a lot longer than the longest value of 3. So then we add the next value of D. Have we seen the D? We haven't. We add the D. We have a new length of 2. Is this longer than the longest value we've seen of 3? It's not. So we add the C. And have we seen the C before? We haven't. So we add it in. We have a new length of 3. Is 3 longer than our longest value? It's not. So then we increment one more time to A, and we add it in here to A. And now we check and say we have a new length of 4. Is 4 longer than 3? It is. So we update the longest that we've seen, and then we add the 4. And now at this point, we've reached the end, so we have to reset again, and we do it for the rest of these strings. Now, I know at this point you might be thinking, why would we keep continuing? Because technically speaking, whatever must be after here, if we've reached the end, must be longer than anything else we can generate. If we made it from B all the way to the end, it doesn't make sense to calculate any other strings here because they must be shorter if we manage to make it to the end from this value. That might be an optimization that you might want to make, but at the very least for now, we see that we should calculate the rest of these values regardless, just for simplicity's sake. Let's not think about optimizations. And you can just do those calculations mentally. It's very obvious to see what steps we're taking here. But this would be our base solution. And we would just return that the longest string we have is 4. So here we have a pretty brute force, easy to do solution. And I just want you to quickly code it out and see, because this should be pretty easy for you. The main thing here might be just this object that you use to store your scene characters. You just have to think about how you're going to set up your code so that these reset in the right way. But I endeavor everybody to try it out. I'm going to show you in the next lesson. And if you even want to see your solution versus mine without watching me code it out in the lesson, you can always just check the resources folder in the next video, because I will include the REPL for you of what code we're going to write to code out this solution. And I'll see you in the next video. So let's code out that logical solution we came up with in the last lesson. To begin with here, I've just initialized our string as well as the actual function definition. Inside of this function, the string that we get as the input, I've set as the variable s. What we're going to do first is just this quick check when it comes to these types of questions. So when we think about what we need to say logistically about the length, let's say we were to receive some empty array or some array with any single character. When we look at this, we know logically that the moment we see an empty string, we should just return 0. And whenever we see a string with a single character, well, we know that this can be the only longest substring that can be formed from the string. So what we can say is that as long as the length of the string we receive is 0 or 1, then we can just return the length as the actual answer. If it's a length of 0, we can return 0. If it's a length of 1, then we return 1. So this is just a quick little optimization we can make early that checks for these edge cases. So here we say if length is less than or equal to 1, then we just return s.length. And we want to be looking for these little optimizations we can make because it makes our code run a little faster in any of these edge cases so that it doesn't have to run through our logic. Now, our logic can probably also account for these cases as well, but it's just faster to do this check. Now, when we begin, we have to remember that the first thing we want to do is initialize that longest variable that is going to keep track of the longest length of substring that we've encountered thus far. So here I'm just going to initialize longest, and it's going to be 0 to begin with. Now, when we think about what it is that we wanted our solution to do, we are going to initialize some first pointer. So here I'm going to call it the left pointer. And this pointer just keeps track of the character that we're beginning with. And then we create some right pointer that is actually going to be the one that checks whether or not the current character that the right pointer is on is already seen before. It's also going to be the one that moves over and accumulates the actual length of the substring that we're checking for. So in this case, when this right moves over and then it moves over again, thus far it's accumulated ABC. When it moves on to the fourth C, it's going to see that this C is already inside of this substring. So then it is just going to reset, and then the left pointer is going to move forward to the next string, and then this whole thing is going to restart again. So when we think about the actual code, here what we want to do is we want to initialize the left pointer. And this left pointer is going to iterate over every single character in our string. So here it's a great time to use a for loop. Very similar to how we did in a lot of our previous array questions. So here I'm just going to say let left equal 0, as long as left is less than s.length. And then it's going to just be left plus plus. Now inside of our for loop, let's think about what we want to do with the code when it comes to our initial stage of length. So in this iteration, what we need to do is we need to initialize some hash map that's going to keep track of the characters that the right pointer touches upon. Here we want to do this, and we want to make a new one for every single instance that L moves. Because when R checks and sees that there's a duplicate, L is going to move, and we want to clear away the previous hash map. So here we're just going to initialize it right here. Because the great thing about a for loop is that this code runs clean for every time left increments. So here I'm going to say seen characters, or seen chars here, is equal to this empty object. And then I'm going to say current length is equal to 0. So this current length is just going to tell us what the length of our current substring is. Then what I'm going to do is I'm going to now initialize that right pointer with a second for loop. And this one is just going to go for let right equal left, because remember, we want right to start where the left currently is pointing to. Then I'm going to say that as long as right is less than s.length, then right is going to increment. Now, once we're inside of this for loop, what we need to do is we need to actually keep track of the current character that the right pointer is on. And here I'm just going to initialize it as a value because I can think about how we might use this multiple times. And it's just more clear for us. So here I can say that the current character is equal to s at right. Now I'm going to conditionally check if we've seen this character before using the seen chars object hash map, and I'm going to check for this current character. Now I want to first check to see if it doesn't exist. So if seen chars, so I'm going to put this bang here, which means if this is false. So if seen characters at current character, meaning this character doesn't exist, then I'm going to increment the current length by 1. And I'm also going to set seen characters at this character to true. By doing this now, whenever a character is seen before, so let's say it's A, if we do this check right here and seen character sees that this value of our current character is true, then it's not going to satisfy this if, and it's going to do the else block that we're going to write later. But once we've updated current length and once we've set seen characters to this current character, we're also going to now update our longest. And we're going to say that the longest value that we've seen is going to be the math.max between the current length and the longest value we've seen thus far. So that's just what we're going to pass because we want the greater of the two values to be the one that we're actually storing. Once we've done that, we can close our if block here because we know that that's all we need. And then this else block is going to say what happens if the seen character has seen this current character before. Well, what we're going to do is we're just going to break out of this loop because all of the logic that we actually need occurred here already. This break is just going to exit us out of this for loop and allow left to increment by 1 and restart this whole thing again. So we just have to make sure we're closing the if. We're going to close this right for, and then we're going to close this left for. And with that, we just make sure that we return the longest value that we've accumulated thus far as the actual answer. And this is our function. So now that we have our solution, what I want you to do is just evaluate the space and time complexity of this function, as well as run your test cases through this function just so you make sure you understand everything that's happening. In the next video, I'm going to be doing just the space and time complexity, and then I'm going to talk about how we can actually optimize the solution with that new technique I mentioned, which was the sliding window technique. But I actually challenge everybody to try yourself and figure out if you can come up with some kind of optimal solution. Because from here on, this brute force solution we might have noticed is very similar to some of the array questions and their brute force solutions that we came up with. So the first solutions tend to be quite similar if we've noticed this trend now between strings and arrays. Generally, when we're just testing for all variations of some kind of solution where we're trying to find, something that is composed of some smaller portion of the array or the string, this solution style where we just generate all of the variations is pretty common. It's actually a really good way just to get a solution on the board. So this brute force is always a good step to practice just so that you get an idea at the very least whether or not this style of a solution even works for these problems. But moving on to the more optimal solutions, that's where it gets a lot trickier and more of your critical thinking is really going to be flexed. But either way, we're going to do that in the next lesson. I just want to endeavor you to try it first yourself. I'll see you in the next lesson. Welcome back, everyone. So here we're looking at the code representation in a REPL file. We just came up with this code in the previous lesson, and now I'm going to evaluate the space and time complexity. So let's start off with the time complexity. We see here that we have a for loop that will increase with the size of s, and we also, inside of this for loop, have another for loop that will also scale with the size of s. So we know that for sure with two nested for loops like this, we have a time complexity of O of n squared. So I'm just going to put that as a comment here. O of n squared. As for the space complexity, we see in here that we have a scaling data structure. So this one is our hash map. And we know that as we accumulate characters, we can put characters into this hash map. And in a worst case, we can imagine where we're storing pretty much the full size of the string on multiple iterations. It might not be the entire string every time, but it can get pretty close. And the most important thing is that it can scale with s, because for every time this for loop runs, there's a chance that we store another new character inside of the seen characters hash map. Based on this, we can tell that at least for this for loop, it will be O of n. Now remember, every time this left pointer actually increments, it resets again. So even though this scene character might get built out multiple times, and every time it might approach the full size of S, it is getting reset and it's not cumulative. So we can say that space is O of n. So with these two things in mind, let's actually run this code in LeetCode. So here we are in LeetCode, and I have pasted in our coding solution. This is question number 3, longest substring without repeating characters. And let's submit and see how we do. So here we see that we're pretty much in the very bottom when it comes to space or time complexity. But we could tell that that was probably the case because of our own evaluation on space and time complexity. We knew that our time complexity was O of n squared, and our space complexity being O of n, we can at least see here that we can definitely bring it down as well. So these are two good hints as far as using LeetCode goes. That gives us an idea that we can probably optimize both space and time. And I'm going to show you how we can do that before I challenge you to try it out yourself. The reason why I want to show you something first is because there is a new technique that we're going to learn, which is a variation of the two-pointer technique we've learned thus far, called the sliding window technique. Now, you can actually try and figure out if you have an idea of how to solve this question yourself in terms of an optimized version of a solution before I even teach you this sliding window technique. But if you want to tackle it after I've taught you the sliding window, that's perfectly fine too. So in the next video, that's what we're going to focus on. So I'll see you in that video. Hello everyone and welcome back. In this lesson, we are going to learn the sliding window technique. The sliding window technique is actually very similar to the two-pointer technique that we have used extensively already in this course so far. The main difference is when and how to apply these two techniques. The sliding window technique actually has more requirements than the two-pointer technique as to when it can be applied, but we're going to explore all of that in this lesson. To begin with, let's look at a brief definition of the sliding window. So here we see that we want to form a window over some portion of sequential data, then move that window throughout the data to capture different parts of it. If this is confusing, let's look at some examples and break this definition down. So let's first start with this sequential data. Sequential data just means data where the order in which the data appears is important. And we know this is the case with both strings and arrays. Strings and arrays capture data in some kind of sequence, and the order of that data matters, whether it be the characters in the string or the order of the elements in the array. Both of these represent sequential data. The only other data model that has this sequential data is linked lists, which we're going to learn in a later lesson. But you mostly apply the sliding window technique on strings and arrays and even linked lists. Here, what we want to do is we want to form some kind of window over a smaller portion of this data. So here, imagine that we were just going to look at these two characters A, B. That is the window that is just capturing a smaller portion of the whole string data. This window can even be larger or smaller. It doesn't matter. The window's main idea is that it's capturing a portion of it. Don't think of it as some kind of fixed window size. That window size can even change dynamically as the code is running. The other thing is that then we want to move this window throughout the data and therefore capture different parts of it. If we see it with this array, we're doing the same thing. We're just capturing these two elements at a time. And this window doesn't have to move one step at a time. It can even jump multiple steps. We can also even take steps back if need be. The main idea here is just that we want to look at some smaller portion of this sequential data. Our code is then going to do something with this small portion and then decide whether or not we want to move the window forwards, backwards, or even increase the window or decrease the size of the window. The technique here is just the idea that you want to capture some portion of this data, and the logic you write around it is really all that matters. The concept itself is quite simple, as you've seen here. But let's just quickly look at an example of an easy question so that we can understand this better and how to apply it. So let's imagine that we were given the question, given an array of integers, find two contiguous integers that form the greatest sum. So here let's focus on that word contiguous. Contiguous means that these elements need to be side by side. They cannot be broken apart. We saw this when we were looking at our substring versus subsequence. And here, what we want to do is find two integers that are right beside each other. So what we might do in order to implement a sliding window technique is we might try and capture two elements at a time and calculate their sum. So starting from the left, the 1 and the 3 are adding to 4. And then we slide this window over. 3 and 7 give us 10. 7 and 9 give us 16. 9 and 2 give us 11. And 2 and 4 give us 6. So the largest numbers here are 7 and 9 as a contiguous pair that give us 16. And that's the answer. So how we might implement this in code is we might initialize 2 pointers representing the left and right boundaries of this window. So here the left and right would be pointing to the indices of the elements that represent the respective bounds of this window. So 1 and 3 here add up to 4. We then slide this window over, moving both of these pointers over, and get the elements here. 3 and 7 give us 10. 7 and 9 give us 16. 9 and 2 give us 11. 2 and 4 give us 6. So the 7 and 9, same as we saw earlier, form the largest pair. So here you can definitely see how the sliding window technique made it much easier for us to solve this problem. Now we'll definitely explore harder problems and more complicated applications of this sliding window technique throughout the course. But at least right now, I hope you understand what it is that the sliding window technique aims to help us achieve. And hopefully now you can think of all these new logical use cases for this new tool that you've learned. Now, jumping back to our substring question. Can we optimize our existing brute force solution? I mentioned in the lesson before we learned about sliding window that we want to actually implement sliding window as part of our optimization. So I want to give you a couple hints as to how to do it. You might be wondering how to implement it if I have not yet shown you any code around the sliding window technique. Well, this is actually a great chance for you to take the concept that you've learned in the sliding window lesson and apply it and just see if you can even implement it. Because a lot of the learning here is going to revolve around you fighting with the concept and then trying to apply it yourself in the code. Also figuring out when to implement what logically in the steps that we've laid out in terms of coming up with the solution without code first and just thinking about using the idea of the sliding window is what will give you leaps and bounds of experience in solving these technical problems and performing these optimizations. The first hint I'm going to give you is use a sliding window to represent the current substring. So here, you want that sliding window to be the actual substring that we're evaluating. Whenever we increase the actual size of the substring that we're looking at, we want to then make the window a little bigger. And this leads us to our second hint. The size of the window will change based on new characters. So whenever we see a new character that we want to add to the substring, then we increase the size of the window. Any character that we've seen before already in the substring should therefore then shrink the size of the subwindow. So that's another big hint. The third hint is that our seen characters hash map should keep track of what characters we've already seen and the index that we saw them at. So I want you to combine these three hints together into figuring out if you can come up with a logical, optimal solution combined with the sliding window technique. Good luck, everyone. I'll cover this in the next lesson.
Welcome back, everyone. Hopefully everyone got a chance to grapple with the sliding window technique and figuring out how they can fit it into an optimal solution for our substring problem. I know it's a really difficult challenge, especially with a new tool, but this is the best way to learn a new tool, even when all you know is the high-level concept of what it should do. By taking it and trying to apply it yourself, you're really working your critical thinking and trying to figure out if there's a way that you can fit it into an existing solution. Even with a new solution, trying to frame it through the lens of this new sliding window technique might reveal to you a lot of key insights that you would not get otherwise. So that's one of the big benefits of just always trying to tackle these questions yourself and using the hints I give you and trying to use them as a way to come to a better solution. But in this lesson, let's actually do it together. I'm going to show you how to implement sliding window here. And I'm also going to show you how we can logically come up with the solution and reasoning together. So with the sliding window, we know we want to form some kind of boundary. And what we want to do is use a left and right pointer to represent those boundaries. And here we're going to use them to represent the actual string that we are building, or at least the substring. We're also going to keep track of the longest value that we've seen thus far. And we still need to keep track of some kind of hash map that holds all of the characters that we've seen thus far. One of the key differences that we're going to do, though, is we are going to keep track of the character we've seen and the index in which it appeared. So here's what we're going to do. We see that our right pointer is pointing at the A. So we want to store the A inside of our hash map and give it the index that it's at, which is 0. We then calculate what's the longest substring we have right here. It's just the A, so it's 1. But this is longer than the longest substring we've seen thus far, so we're just going to store it here as 1. And then we're going to advance the right pointer forward. Now when we look at B, we check our hash map and we say, have we seen B yet? We haven't. So let's add it in here. And now when we look at our string of AB, it's a length of 2, which is longer than anything else we've seen. So we're going to increment that, as well as move the right pointer over by 1. We do the same thing for C. We haven't seen C yet. We store it in our hash map and we give it the value of its index, which is 2. And then we have a new longest string of ABC. So we update the longest value and we're going to increment the right one forward. Now it's interesting because we see this B, and when we check our hash map, we notice that we have seen it already. So at the previous index of 1, there was already B. But before we start removing anything or checking anything, let's first just focus on this new substring that we formed. And let's see what logical conclusions we can derive about it. Looking at this new B, we know that the B that we've just seen is the first time any duplicate characters have appeared in this substring we've been building thus far. Every other character is still unique. So any character up until this B can no longer be part of our substring because our substring has to be contiguous. But any character after this B must be unique, at least up until this B value that we have here. So up until our substring right here. What we can therefore conclude is that if we were to move this left pointer over to where B is +1, so this C right here, we know that this string formed from L and R, the 2 pointers, must still be unique because the B is the only value that was a duplicate. So what we then do is replace the index in our existing cache map with the index that the new B is at. Now you might be wondering, what do we do about this A? Well, let's actually think about that later. For now, we know that this new string is unique, but the new string has a length of 2, so we can't actually update the longest string. But let's just keep moving forward. What we then do is we say, okay, we're done with this right pointer. Let's move the right pointer over. So now when we look, we check our hash map for a new value D, and we see there's nothing. So we add D in here, and we add its index. And then we say, what's the length of this new substring from L to R?
It's 3. It's not longer than our longest substring, so then we move this right over again. Now we encounter this A, and what we see is that this A already exists in our hash map, but the index is before our left pointer. So we actually don't treat it as something that we've seen already. Yes, we've seen it as far as our right pointer having scanned across this entire array and having seen this A before, but because the index is before our left pointer, we know logically it is something that doesn't concern our current substring anymore. Because we know that when we moved our left pointer, this is the new left boundary of our window. Any characters that we might have seen before this left window are not part of our current substring. We know that for certain. So we can say then that what we need to do is just update this value to the new A value, but we can still consider the length of our substring as one that has all unique characters. So here I'm just going to update this A over to this new index value. And we see that CBDA has a length of 4, which is longer than anything we have seen. So now that we have this updated, let's move our right over. And now when we check, we say, okay, have we seen this A before? We have. Is the index value of this A that we've previously seen greater than our current left pointer? Yes, our current left pointer is pointing at index 2, 0, 1, 2. 6 is greater than 2, so we know that the previous A value we've seen must be within the substring we're building. So what we then do is we move the left pointer over to this current value that we have of 6 plus 1. So then our left pointer is going to move right beside our right pointer. And then when we calculate the string size, we have a string size of 1, just this 1A. Then this is not longer than our longest value, so then we just move this right pointer over. And now when we check and see this C, have we seen it before? Yes, at 2. But is this 2 greater than our left pointer? It's not. This left pointer is pointing at index 0, 1, 2, 3, 4, 5, 6. So 6 is greater than 2, so we know that the C is not part of our current substring that we're looking at. So then we once again just update our C value to the new index value of 7. And now our right pointer has bumped up to the end of the string. So from here, we can just return this longest value that we've stored because we know this is the longest substring that we were able to form. So through this, hopefully you now understand how to implement sliding window in this question for an optimal solution. You'll notice that we've only touched each element at most one time with the right pointer. So hopefully you know enough to figure out how to code out this solution. Remember that the main challenge is going to be keeping track of this hash map that stores the characters we've seen thus far, the index where we've seen it, and then double checking whenever our right pointer encounters a character that already exists in the hash map that the index value associated to that character is greater than the value that our left pointer is at, because the left pointer represents the start of the current substring that we are building out. So try and code it yourself, and as always, I've included the actual final code in a REPL file in the next video's resources folder. If you just want to compare your current solution against that one, in the next video, I'm going to explain how we code it anyways. So I'll see you in the next video. So let's come up with the code for our optimal solution. Here you'll see that I've just initialized our function and I've included the optimization for any string that gets passed in of length 1 or 0. This is the same one as our previous brute force solution. We're just going to keep it here as well. What we're then going to do is we are going to think about what we need to initialize. So remember that we need both a hash map as well as a left and right pointer. So let me just write that down here. And we also need to keep track of the longest value that we've seen this far. So here, let's just first initialize our scene characters hash map. And I'm going to initialize it as an empty object. And then we're going to need our left pointer, which is going to start at 0, as well as our longest scene string. So I'm just going to call this longest, and I'm also going to initialize this at 0. Now, what we need to do is, when we really think about it, we really just need this right pointer to scan across this entire string. It's never going to go back, but it's always going to advance one character at a time. It's based on the iteration of our code. When this right pointer is at some character, we decide whether or not the left pointer is going to move. So we can actually just handle this right pointer moving with a for loop. And we can say for let right equals 0, right less than s.length, right plus plus, and now we're inside of the execution context for this right pointer when it's at some character. So the first thing we want to do is we just want to store that character that it's currently at, because we're probably going to use it more than once. So let's say const current char equals s at right. And then what we want to do is we want to check and see if this current character that we are currently looking at with our right pointer exists inside of our scene characters hash map yet. Now remember that this scene characters hash map is going to store a key value pair, where the key is going to be the character that we've seen thus far, and the value is going to be the index of that character. So what we're going to get back when we actually check against this hash map is either an index or undefined if that character has never been seen yet. And let's just store that value inside of another variable. We're going to call that previously seen character. So prev seen char is equal to seen at our current char. So this here will be either undefined or a number, which represents the index. Then what we want to do is we want to check if this previously seen character value is greater than or equal to the left value. If there is a value, then we want to make sure that it's greater than our left boundary. If it's not, and there's no value, then it's going to be undefined, and undefined compared to anything is still going to return false. So here we're just going to say if this previously seen car is greater than or equal to left. So if the value is seen and it's greater than or equal to our left boundary, then what we want to do is we want to bump this left boundary to that value plus 1. So let me just quickly remind us why that is the case. So let's say we have our right boundary at this second C now. So we know that inside of some kind of hash map, we've already seen A at 0, B at 1, and C at 2, which is just these characters that the right pointer has seen thus far. Once we see the C value, we see that our C is at 2, which is the last time we saw it. So we know that the only way for us to continue forming some kind of unique substring is to move this left pointer all the way here plus 1. So we need to join it with the right value here. Like so. So that's just what we want our code to do as well. We're going to say that if previously seen character is greater than or equal to left, left is now equal to the previously seen character plus 1. And that's all we're going to do in there. What we're going to do next is just replace that value in the scene hash map at the current character that we're on with the current index. Because regardless of what the conditional logic is, we always want to update that value in our hash map anyways. Then what we're going to do is we are going to set the longest value now equal to the maximum value between the longest value that we've stored thus far or the current substring. And we can get this current substring value by taking the index of our left and right pointers, subtracting the left one from the right one, and then adding 1. And let me explain to you why we have to do that. So here, let's imagine that our right pointer was here, and our left pointer was here. So let's just say this is 0, 1, 2, 3, 4. So when we look at this string, we know that it's 4 characters long. But 4 minus 1 is equal to 3 because our index starts at 0. So what we have to do is just add an additional 1 in order for us to get the proper length of this substring. So this is going to then be right minus left plus 1. And that will give us the length of our current substring. Once we have this, we now can close off this for loop, and we just return the longest value, and we have our solution. So this code just captures all of that logic that we came up with for this optimal solution of a sliding window. And as we see, as far as our space and time complexity goes, this for loop is the only thing that is going to scale as far as iterating over multiple elements in the size of our input. So if the string gets longer, our for loop is going to get bigger as well. It's going to iterate over more elements. But that's the only thing. So we know here then that our time complexity is O of n. As for our space complexity, let's look. We still have this scene hash map, and this scene hash map might end up storing the entire size of the string. Because we can imagine if the entire string was unique, then we just end up storing every single character. So here we're going to say that our space complexity is O of n as well. So with this, we have our space and time complexity, and we've improved our time complexity here compared to our brute force solution. So hopefully this made sense to you. You can always compare and reread this code and see if you can even code it yourself again without looking at this code, now that you've seen me walk through it. It's always good just to get that extra practice on the same question numerous times, so you make sure you understand every little nuance of logic. In the next video, we're going to run this code in LeetCode and see how we perform with our new solution. Hello everyone and welcome back. We are going to spend the next few lessons focused on learning palindromes. Now, palindromes is a very crucial pattern in string questions, and it's also a very common subproblem. Subproblems are not exclusive to string questions. In fact, there are subproblems in almost every single interview question. But in string questions, subproblems are the most repetitive in the sense that you'll see the exact same version of a subproblem show up in varied and different questions. So let's first understand what is a subproblem. So a subproblem is a problem we have to solve along the way to solving the main problem. And a question can easily have one or multiple subproblems. And oftentimes, the solution to those subproblems helps us get to the solution for our main problem. Let's think back to the last substring question that we did. When we're given a string, find the length of the longest substring without repeating characters. We have just done this recent question, and here let's break out the main problem and the subproblem. So here the main problem is finding the length of the longest unique substring. That was the main problem. By solving this problem, we had our solution. The subproblem here was a pattern matching subproblem in strings. And the specific pattern that we were matching was unique substring. So here what we were trying to do with pattern matching is we needed to identify a substring within the main string that fit a specific pattern. And the specific pattern here was unique substring, meaning that we were looking for a string that had no repeat characters. So here, we had to identify and figure out how to solve whether or not we knew a substring was unique. Once we had that, then the main problem that we were solving became easier, which was trying to find the length of the longest unique substring. By identifying the solution for pattern matching a unique substring, it made it much easier for us to solve figuring out the length of the longest unique substring. So this is how subproblems and main problems show up in questions. Here we're just focused on string questions. Now this brings us back to palindromes. Palindromes is a very common subproblem in strings. There are some string questions that are exclusively solving palindromes, but a lot of the times palindromes is thrown in as a pattern matching subproblem in a string question. And it's a very common pattern matching problem because of the complexity that it adds to a question. So we are going to focus on breaking down and understanding all the insights when it comes to pattern matching subproblems. And then we're going to learn a couple questions about how these show up in string questions. So the first thing, let's just define a palindrome. A palindrome is a string that reads the same forwards and backwards. And looking at an example of a palindrome, we can see that this string ABA reads the same from left to right as it does from right to left. It's just ABA every time. A smaller string with just a single character is therefore also a palindrome because just like with ABA, it reads the same from left to right and right to left, just the character A. If we look at a more complex string, such as this one, race car, we notice that it's made of two words and there's a space between the two words. But if we just focused exclusively on the characters in this string, we'll see that it's always RACE-CAR, whether you read it forwards or backwards. If we look at an empty string, we'll notice that this empty string is also still a palindrome, because by definition, this string is the same whichever direction you read it in. If we were to take a more complex sentence, such as this one that says, a man, a plan, a canal, Panama, this is still a palindrome, because despite the fact that there are these symbols here, and these characters are uppercased, as well as the fact that there are spaces in our strings. Now, 99% of the time, when your interviewer asks you to identify whether a string is a palindrome, they want you to ignore all of those things and focus exclusively on just the alphanumeric characters in a string. So if we were to take that last sentence, what we would want to do is perform some kind of transformation on it in order to remove everything here that's not important and leave just the characters. We probably also want to lowercase everything just so that when we do the comparison, it's also going to give us the correct equivalence. And what we want to do then is once we have this final string, in order for us to determine if this is actually a palindrome, we have to apply some kind of logical technique here. So what we could do is initialize a left pointer on the very left and a right pointer on the very right. Knowing what we know about palindromes, and for them to read the same left to right and right to left, these outer bound characters must be equal. And as we move our pointers in, we should find that each character is also equal. So here we'll see that this A and the A are matching, the M's are matching, the A's are matching, the N's are matching, the A's are matching, the P's are matching, the L's are matching, the A's are matching, the N's are matching, the A's are matching, and then they both converge on the C, which is of course the same character. So now we know this string is a palindrome. What we'll notice is that our left and right pointers converged on the same character. And the reason this happened is because the length of this string is odd. If the length of this string was even, then what would happen is our two pointers would be pointing to the two most center characters in the string instead. Everything else about how we did the comparison stays the exact same. So that's just one thing to note. The interesting thing is that this strategy of initializing the pointers on the outside of our string and then converging and comparing the characters as they move in is only one strategy of how we might solve if a string is a palindrome. There are a couple others, and it's important we know them all because not every technique works in every palindrome question. And we'll explore that a little later. But let's look at another method. So let's take a new string. What we would do with this new string is we would just initialize left and right pointers, but from the very center this time. And because this string is odd, we would initialize it in the very center character. So it's pretty much the same thing as our previous solution, but just in reverse. So now we would just expand our characters outwards. So now we would just expand our pointers outwards and compare those characters. And as we see, all these A's are the same, so we know we have a palindrome here. If we had an even size string, we would initialize on the two center characters and do the same thing of just moving them out, comparing the characters, and then seeing if we have a palindrome, which we do right here. So this is pretty much just the reverse of that first solution. Another one that might be useful is if we were to look at this string of race car. We know just by looking at this that this is not a palindrome because the two center characters is an E and an A. So those two characters don't match. But how we might do this is let's first transform this string into one without the spaces. Because we know that this string must be the same forwards to backwards and backwards to forwards, what we can do is actually create a duplicate of this string in reverse. So here you'll see that this second string on the right is just the same as the first string, but flipped. And now what we do is initialize two pointers on the left and the right strings of their first characters and just compare these characters here. We'll notice that once we get to that middle character, we see that this E and the A don't match, so we also know that this is not a palindrome. So these are three different techniques using pointers that we could use to identify if a string is a palindrome. And you might be wondering, why do we need to know three different solutions? As I mentioned earlier, depending on the context of the palindrome question, it may be much more difficult to use one of these three different solutions. So it's good to know all three and figure out which one is easiest to implement depending on the question. So now that we understand palindromes and some of the techniques used to actually identify palindromes inside of strings, let's actually take a look at some palindrome questions. The first palindrome question we're going to do is a very basic one that's pretty much just going to ask us to implement those three solutions we learned. The question is just going to be that if we were given a string, determine if it's a palindrome considering only alphanumeric characters and ignoring case sensitivity. So as we've discussed, this question is pretty much the exact thing that we were learning in the last lesson, where we looked at three different approaches we had to determine if a string was indeed a palindrome. For this question, we're going to receive a string very similar to the one we saw before. We just have to make sure that because we are only considering alphanumeric characters and ignoring case sensitivity, that we go through that conversion we did in the last lesson as well. I'm going to show you how to do it because this question is very simple. In fact, we can pretty much ignore if there are any constraints for this question since it's very clearly laid out to us what we want to do. So from here, let's just jump right into writing out some test cases. The first test case we want is just going to be the very basic string that we know for sure is indeed a palindrome. So let's just do something like this. We also want to include a string which is even in length that's also a palindrome, so our code accounts for both odd and even string sizes. Next, what we want is a fail case, so let's do something where we know it's definitely not a palindrome. Let's also account for a case where we just have a single character and an empty string. Additionally, let's make sure that our solution accounts for only alphanumeric characters and it also ignores case sensitivity. So here, let's just also include that long string that we were converting in the previous lesson. So here that string is a capital man, comma, a plan, comma, a canal, colon, Panama. And just to be certain, let's also include all of the answers we expect to return. So remember, our solution is supposed to determine if the string is or is not a palindrome. So it's going to return true or false. For the first one, it should return true. The second one should also be true. The third one should be false. The fourth should be true. The fifth should be true. And the sixth should also be true. So now that we have our test cases, I'm going to show you one quick thing about how to transform your string, which at this point is probably going to be this one, and how you can convert that into the version where it doesn't have any of these capitals here and any of these spaces, as well as removing these commas. And in case there are any other symbols, there's actually a way that you can remove all those as well. I'm going to show that to you now. So here we have our test string as well as the initialized function. We're going to receive all of our test cases in as this variable s, one at a time, of course. And this s is going to be the string that we have to validate whether or not it is a palindrome. So I am going to challenge you to implement a solution using one of the three that we learned in the previous lesson, and you're just going to try and code it out yourself. What I'm going to show you first, though, is how you can make sure that this string is in the format where it is only alphanumeric characters, meaning that we're going to remove any spaces, any commas, any colons, and any other symbols, as well as making sure that all of our characters that are capitalized are lowercased. If you want to take a crack at it before I even show you this method, you're perfectly allowed to do that as well. But I'm just going to show you because that's going to be a little bit different from anything else we've done before. In order to do so, what we have to do is actually replace these characters that we don't want in our string with nothing. So to do that, you can use a method called replace. In JavaScript, this is a method on a string. But in every language, there is a string method that does the same thing. So here what I'm going to do is I'm going to replace this variable s inside of our code with our modified s. The reason we do this is because we want to save memory. By utilizing the original memory, we're not instantiating some new data structure that'll scale. So I'm just going to say that s is equal to s.replace. And then here, what I'm going to put is a regular expression, a regex expression. Now, regular expression is just some combination of characters that matches some kind of search pattern in strings. If you don't know regex that well, don't worry about it. It's really not that important in the interview, as long as you mention that if you wanted to do something like this, such as transform a string using this replace method, you know it needs a regex pattern. But let's say you don't know regex offhand like that, because it is quite complex. You can just mention if you could put some expression here and just assume that what it does is it achieves what you're looking for. Usually they'll be 100% okay with this because no one expects anyone to memorize regex or know how to do it offhand. But here what we would do is just write this regular expression with a slash and then this open bracket, tilde, capital A to Z. And then we're going to say lowercase a to Z, 0 to 9, /G. So I'm just going to briefly explain to you what this regex pattern is, so at least you know what's happening. These slashes here designate the actual pattern we're going to match. This square bracket designates the actual group of characters that we are going to define so that our string knows what it's looking for. This tilde symbol here means that it wants to capture everything that is not in this group that will follow the tilde. And the actual group here is uppercase letters from A to Z, lowercase letters from A to Z, and the numbers 0 to 9. So what this string means in total is it wants everything that is not alphanumeric characters, regardless of case sensitivity. So then when you take this in as a whole, what we're saying then is that we want to replace any symbol, meaning anything that's a non-alphanumeric character that we've defined by our regex pattern here. We want to replace it with an empty string. So that's how we end up replacing anything that is not alphanumeric. Then what we're also going to do, because this regex does not actually care about case sensitivity, it leaves them as they are, is we want to lowercase everything here by using this to lowercase method. And now what happens is this S is now the version of this string without capitals and without any spaces or any symbols. So now you have the string to work with. What I want you to do is take this code we have here and try and implement your own solution. You can implement it the way that you feel like might be an idea for you, or you can implement any of those 3 solutions we came up with in our previous lesson, whether it be initializing the actual pointers on the outside and going in, initializing the pointers in the center and going out, or reversing the string and then comparing those respective characters. Whichever one you prefer, implement it just to see. In fact, I would suggest you implement all 3 to see the differences between the 3 and evaluate the trade-offs yourself. I'm going to show you what they look like in code in your resources folder, because we'll have all 3, and I'll give you some quick notes on it in the next lesson. So enjoy the challenge, and I'll see you in the next lesson. Hello everyone, and welcome back. Hopefully you just tried to code out those 3 different approaches we had to determining if a string is a palindrome. Here I've included all 3 of the REPLs for these 3 solutions. They are labeled as 2 pointers from the outside, 2 pointers from the center, and compare against reverse respectively. So inside of each of these REPLs, the code is actually very simple, so I'm not really going to go through it. The logic is the exact same as what we had come up with in the previous lesson, it's just that we've implemented it in code. Any place where I found it might be a little bit confusing as to why we were initializing certain variables the way that they were, I did include comments. So definitely take a look at that if you are confused. Now, the reason why I'm showing you these 3 different approaches to determining if a string is a palindrome is because palindromes are oftentimes not just a palindrome question, in the sense that you get a question where you're given a string, you have to determine if it's a palindrome or not. That is too basic as far as palindromes appearing in string questions. Oftentimes what happens is that palindromes appear as a pattern we have to match inside of a string question, which means that palindromes appear as subproblems to string questions' overall problem. So we're going to explore what that means with some questions, but the main idea here is that you will be expected to figure out something about this string question where a palindrome is involved, which means that you have to decide which of these 3 methods is the best approach to helping you solve the subproblem of figuring out if a string is a palindrome. It may not be the overall problem, but it's going to be part of it. And that means that one of these 3 solutions is oftentimes going to be better than the others at helping you figure out how that subproblem of the string being a palindrome, getting to an optimal solution for the overall larger problem. So if that's confusing, don't worry about it. We're definitely going to explore some cases where it becomes more obvious what I'm talking about. So it's actually going to be the case with the first question that we're going to do, which is very similar to this original question. So let's take a look at it. So the question we're going to look at is called almost a palindrome. And the question asks, given a string, determine if it is almost a palindrome. A string is almost a palindrome if it becomes a palindrome by removing 1 letter. Consider only alphanumeric characters and ignore case sensitivity. So this question is very similar to the last one we did. The main difference here is that if we were to imagine we were given this string, race a car, if we converted this into the format where we remove any special characters or spaces, we see that the center two letters do not match. They, at the very least, do not allow us to say that this string is indeed a palindrome. But by removing one letter, which in this case, if we were to remove the A, we would end up with race car, which gives us indeed a valid palindrome because it's the same left to right as it is right to left. So this would pass this stipulation. The other thing that we need to actually think about if we were to look at this though, is that we could have also removed the E. We did not have to remove the A. If we remove the A, we have race car as we saw. But if we removed the E, we get RACACAR, which is still a palindrome because it's the same left to right as it is right to left. So with this string, it did not matter which of these two conflicting letters that we removed because whichever one we removed still yielded us a palindrome. So this string indeed is almost a palindrome. This is not always the case though. Let's take this string here, ABCCDBA. When we do our check, we see that the A's match, the B's match, but this C and this D don't match. So what we can do here is we can generate two strings. The first one we generate by removing the D. We end up with ABCCBA, which is of course a palindrome. But if we remove the wrong character here, which was the C instead of the D, we end up with ABCDBA. Here what we can see is that the two center characters conflict. They are not the same. So we know that this generated string is not a palindrome. So what we know then is that when we are skimming through our characters in our given string, when we find that two characters do not match, we have to decide which of these two to remove. Or at the very least, we have to remove both and see what the final string becomes. Because removing one of them does not guarantee that the remaining string is actually a palindrome. So that's a thing we have to count for in our solution. We have to remember that because two characters are conflicting, that means there are two possible generated arrays from removing one single character, because removing either one of them generates a different string. Now let's take a look at another case where we have this much more longer string, ABCDEFDBA. Here, if we were to scan through, we see that the A's match, the B's match, but this third character, C and D, do not match. So as always, we can generate two different strings. The first one is we remove the D on the right and we end up with ABCDEFBA. So we know the first two characters and the last two characters were already matching. Our third characters now still do not match. Even with removing the D, the C and the F that has taken the D's place does not match. So this is not a palindrome. Now, if we remove the C instead, what we end up with is ABDEFDBA. And here we see the third position characters do match, but the inner two characters don't match. So this means that regardless of which character we remove, we do not end up with a palindrome after. So this string that we've received is not a almost palindrome. By removing one character, we were not able to create a palindrome. So then in this case, we would return false. So these are pretty much all the cases we need to account for with our solution. Now with that in mind, let's verify the constraints. The first and probably only constraint we have, since this question is very similar, is that do we consider a palindrome as an almost palindrome as well? So if the string we receive is already a palindrome, is it technically almost a palindrome? And here we say yes, return true if the string is already a palindrome. So if we scan through the string and we notice that it's already a palindrome, we can just return true. We didn't need to remove a character, so technically speaking, a palindrome is also an almost palindrome. And with that, we have enough to write out some test cases. So the first one we have is where we only need one character. Now remember, we're going to receive strings that don't have spaces in it, so here we can just write it out in such a way that we don't have any spaces in it and we've already compressed it. So instead of race a car, it's just going to be the same characters but compressed together. So from here we know that this should return true because regardless of whether the E or the A you remove, this will end up being a palindrome once you remove one of these characters. Now the other string we want to also account for is going to be the one where we only remove one character in order to make it work. So here, A, B, C, C, D, B, A. If we remember, as long as we remove the D in this case, right here, we will end up with a valid palindrome as well. So this is also going to yield true. The other one that we have to account for is our fail case. So here we can add the string A, B, C, D, E, F, D, B, A, which we remember when we see this conflict between the C and the D, even if we remove either of these characters, we still end up with a string that is not a palindrome. So this is going to be false. The other two cases we do also want to account for is our edge cases, where we receive an empty string and a string of only one character. So both of these should also yield true. What's interesting is that we can also return a string with just two characters, and this will also return true, because if we remove the A, we'll end up with a single string of B, which is still a palindrome, and if we remove the B, we end up with a string with just the A, which is also a palindrome. So these are going to be our 6 test cases. So now I want to challenge you to take these test cases and try and build out a solution yourself. Come up with the solution, code it out. You can go straight for the optimal solution here if you like, because this question is a little bit straightforward. It's going to be pretty similar to what we achieved in the original valid palindrome experimentation, where we looked at the 3 different solutions we had for determining if a string was a palindrome. This one's going to be very similar. So if you can figure out the trick here, I've already kind of explained it to you. Once you find the conflict of 2 characters that don't match, you want to generate both strings and just validate if either of those are palindromes, and then from there return true or false, depending on if either is a palindrome or if neither is a palindrome. So with that, please try it yourself, code it out, and then I'm going to show you how I do it in the next lesson. Hello everyone and welcome back. Hopefully you got a chance to try and come up with a solution and code it yourself for our almost palindrome problem. In this lesson, I'm going to show you how I would do it. The first thing that I would do is look at the question and realize that the palindrome definition portion of the question, which is where we identify if some string or substring in the problem is a palindrome, is only a subproblem. So this goes back to what I was mentioning earlier about how palindromes appear in string questions, but mainly as subproblems, not as the main problem itself. So yes, our question is similar to us trying to figure out if we have a valid palindrome or not, but it's not the whole picture. The key thing that we're trying to figure out is looking at the string. Is there a conflict in such a way between 2 characters where by removing one of the characters, we end up with a palindrome? That's actually the key thing we're trying to solve, is figuring out which characters in this string have the conflict, and then figuring out how to generate the new versions of the strings with those characters removed. We then need to check if either string is a palindrome. So here we can see that once we've generated our 2 strings, we definitely need to leverage one of those 3 solutions we have for figuring out if a string is a palindrome, because we're going to have to use one of those 3 solutions on the 2 generated strings. The other thing that we notice is that if this string is by default a palindrome, meaning that we don't have to remove any character, we have to have some way of checking to see if that's the case. So that gives us a big hint. Knowing that this string can be a palindrome means that we can probably utilize one of those 3 solutions as a starting point to figure out an optimal solution. So with that in mind, let's use process of elimination to figure out which of those 3 is most ideal to start applying to this string question. So the first thing we notice is that if we were to use the reverse string method, what we do is we generate a reverse of this string. And what we do is we then compare the values. So here it would be A, B, D, C, C, B, A. Our solution then uses an equality check to see if these strings are equal. And we can see that they already are not. We know that the D and the C will conflict. But our solution, because it's an equality check, doesn't actually give us that information. We can visually see because we know this string is not a palindrome. But we can already tell that this is not going to be the right solution to work with because it gives us no information about where the actual conflicting characters are. And we know that that's a key piece of information we need because we need to generate strings once we know the conflicting characters. So from here then, let's actually explore the other two options because we've eliminated this reversal comparison solution. So the other two options we have is to generate left and right pointers either from the center of the string or from the outside of the string. If we think about that, we know that the center generation is a little bit more complicated because we do have to account for whether or not the string is odd or even. And if we think about it in those terms, that solution is ever so slightly more complicated. It doesn't actually affect the space and time complexity, but here let's just use the left and right pointers from the outside for simplicity's sake. We can easily go with the other one, but because this one's a little simpler to implement, it gives us less moving pieces to work around with because we have to still transform the solution a little bit in order for it to work to this new current problem. So let's say we go with that solution, where we initialize a left pointer and a right pointer on the outside edges of the string. We compare these two values, the A and the A, and we see that they're equal. So then we move the pointers inwards here. And when we compare these new characters, we see they're still equal. They're both B. So we move the pointers again, and now we see that we have a conflict. The C and the D conflict. So what we then do is we want to generate new strings, removing either of these characters. So here we're going to generate A, B, C, C, B, A from removing this D right here. And then we're going to generate our other string by removing this C. So we end up with A, B, C, D, B, A. Now that we have our two strings, we need to figure out if they are palindromes. So how we can do this is, remember with our original string, we've already checked these characters. So we don't need to check these characters anymore because they are not the ones that changed. The ones that changed are in the position of left and right. So at the indices that the left and right pointers in our original string is pointing at. So we can just continue from there and just do our checks from here while continuing to move inwards. Now I know that here we only have two characters left, but if there were more, you would just check these characters, keep going in, check the characters, keep going in. And from there, you can just say, if whatever is remaining inside of this string, if they match the palindrome pattern matching, then we know that this is a palindrome. If they don't, then we know it's not a palindrome. There's no more characters we have left to remove. So from here, we see that this is indeed matching. So this string is a palindrome. This one doesn't match, so it's not a palindrome. But because this one is, we have our answer. So we know that this is indeed an almost palindrome, because one of the strings from the character we removed became a palindrome. So I want to challenge you to code out this solution. I will give you a hint. The key is going to be around passing this original string into some kind of function that will then check whether or not we have a palindrome by passing not only the string, but also the current left and right pointers. And one of these pointers needs to be the one that is technically removing the character by shifting inwards. Hopefully that's enough of a hint, and I want to challenge you to try it out. In the next lesson, I'm going to show you how we're going to code this solution. So here we are inside of our code, and we are going to code out that solution we just came up with. So what we need to do is we need to initialize some left and right pointer that will point to the outside of our actual string. So we can begin by initializing a left variable here, which is equal to 0, as well as a right variable that will be s.length minus 1. Then what we're going to do is we are going to pretty much copy what we had in our original solution when it came to determining if a palindrome was valid. And using this method, we just say while left is less than right, then what we're going to do is we are just going to check to see if they're equal. So here we're going to say if S at left does not equal S at right. Here what we're going to do is we are going to do that check that determines if the new versions of our strings where we have moved one of the characters is actually now a palindrome. So here what we're going to do is we are going to write a function. So let's do that first. I'm going to call this function valid subpalindrome. So here we can do that by writing it up here. So here I can make this new one valid subpalindrome. And this is going to be a function that receives 3 properties. It's going to receive the original string, which is this S that we are passing around. It's going to get the left pointer, and it's going to get the right pointer. So essentially what's happening is that in our original function, we've initialized this left and right pointer. And these pointers start moving inwards comparing characters until they hit this character and this character, which is where we know the conflict exists, in index 2 and index 4. What we're then going to do is we're then going to pass in the pointers as well as the original string into our valid subpalindrome function, which will then check the remaining characters. And the way that we simulate skipping a character is by moving one of these pointers over as the left value we pass in for one call of valid subpalindrome. And then in the other call of valid subpalindrome, we're going to pass the right pointer, except it's going to be one closer this way, so that we've respectively skipped that character, which is essentially the same as removing the character. So let's write this out and get a better understanding of what's happening. Because here we get the left and right values, we don't actually need to instantiate them. So we just pretty much write the rest of our actual check. We say while left is less than right, we are going to check here if our S at left does not equal our S at right, then we return false. If it's not the case, then what we do is we move left and right closer. So we're going to increment left and we're going to decrement right. And then if all of this is the same, then we just return true. Meaning if all the characters have matched, then we know we indeed have a valid palindrome. So that's our valid subpalindrome function. And now what we're going to do is we are here inside of our original function again. And here what we're going to do is we are just going to return either or of both of these function calls to seeing if they are equal. So here we just say return our call of valid subpalindrome, passing in the first S with our left value incrementing by 1, as I mentioned. So this is the same as shifting the left pointer over by 1, essentially skipping that character. And then we keep the same right. Or calling the function again, valid subpalindrome, with our other value. So here we're going to still pass in S, except we're going to pass in left and we're going to pass in right minus 1. So if we get true for either of them, this whole function will return true. If we get false for both of them, then we're going to return false for the whole statement. So this represents us trying out removing either of these characters and then testing if the new strings that we get from both are going to be palindromes. And then we just finish off this statement and we say the same thing as before. Left is going to increment, right is going to decrement. Then we close our while loop and we return true if everything else actually matches. So here we actually see that this function is pretty similar, if not almost identical, to our two-pointer from the outside solution for determining if a string is a palindrome. The key insight was to notice that we just needed to modify the actual check inside when two characters don't match for the first time. We then return a subfunction call with the OR statement to determine if by shifting the pointers by one in each direction respectively, we were able to find a palindrome with the remaining characters. So here we see that it harkens back to what I was talking about with palindromes being a subproblem. The main thing was to notice that this modification here was the main problem. But we really were just leveraging one of those three palindrome solutions and then tweaking it and figuring out what we could do to make it work. This isn't always the case where you're 100% going to base it off of one of these solutions, but the solutions do help give you some insight as to how you can tackle the problem. So with this, we have a pretty good solution because we know that as far as space and time complexity goes, with time, we're really only touching every element once at most. We don't touch the same element more than one time, nor do we have any nested loops. Even inside of here, we do one additional check with the valid subpalindrome call, but this one continues from off where the left and right pointers are, and maybe here you end up duplicating some additional calls on the same letters in the sense that if left and right touch all the way through and then they find that there's a conflict, we then call this next subpalindrome and they touch more characters, perhaps the same ones that were already touched in this one, but it doesn't really impact time that much. So here we say that our time complexity is O of n. As for space, we're not storing any scaling data structures that take up any scaling memory, so we know that our space complexity is O of 1. And this is actually about as optimal of a solution as we can get. The reason why we didn't have to explore any brute force solutions with worse time complexity first is because we were able to make the key insight right away once we learned those three possible solutions we had for valid palindrome. And then from there, we were just extending one of them into this solution, so we had already done the critical thinking up front. And this is a good point to note. Sometimes you don't need to go for the brute force in order to get to the optimal solution. A lot of the times, if you're able to notice the key insights early on, or at least follow some hunches that you might have, you can actually end up with the optimal solution the first time. Especially with more practice, you'll notice a lot of these patterns repeat themselves. So you actually do get an inkling as to where your critical thinking wants to take you, and you can come up with an optimal solution without doing the brute force, which is great because you save a lot of valuable time. Because remember, the interview is within a certain time frame. And a lot of these optimal solutions do require us to really think them through, which always takes time as well. So if you can save yourself time by going straight for the optimal solution with the key insights that we're able to make, then we are able to get a lot more time to make sure that our solutions are correct. We double check for any errors. We're able to test our code a little bit more thoroughly. And in general, it's just a better practice. Now, we are going to learn more about strings and palindrome subproblems in string questions later in the course when we focus on a new technique known as dynamic programming. Right now, it's a little bit too early for us to introduce it into the concepts while we're trying to build a better foundation. So we're going to move on to the next topic, but we will come back to this. So for now, hold tight and I'll see you in the next lesson.
Awesome work! You've taken a first solid step by tackling these string and array problems. But this is just the beginning. If you want to learn how to ace any coding interview, check out Yihua's full FAANG interview bootcamp course, where you'll go beyond strings and arrays and confidently learn how to tackle any coding question that gets thrown at you with the right strategies, frameworks, and skills top companies are looking for. If you enjoyed this crash course, please drop it a like and leave a comment with your questions, thoughts, or feedback down below. That's it from me, and I look forward to seeing you inside the Zero to Mastery Academy.